Welcome to the Open Hardware Summit 2022. I am Alicia Gibbs-Seidel, and I am the Executive Director of ASHWA. You have probably seen me at quite a few of these events, and I am super excited this year to announce our summit chair, Lee, who is going to take it away from here. Thanks, Lee.
Hello, everyone. Welcome to the summit. I am extremely excited to have had the opportunity to work with this amazing community this year. It's my first year chairing the summit, and it's been a year of stop and start already, and we had really hoped to be in person, but it's also a really great opportunity to share digital space with so many of our global community. So thank you to the community for making events like this possible and blowing us away with some amazing submissions, sharing all of our events, and just general engagement about the summit up until now. And this obviously would not be possible without our community. The range of talks we've selected for this year cover social, environmental, technical, and policy issues surrounding open hardware. And we hope that they work to increase the depth around the conversation the community is already happening. Many of these talks push the boundary of open hardware and collaboration, which is super exciting to see. So before we continue, I just want to take a minute to introduce all of our other team members that have worked super hard to make the summit happen this year. So we'll start off with Claire.
Hello, my name is Claire, and I'm this year's Summit Talk Chair. It's been an awesome opportunity and truly career-changing and life-changing. I really, really appreciate it. It's a dream to work with all of these people and to see you all here. I'm really excited. Let's have a great day. I'm going to pass it off to Sid.
Hey, everybody. I'm Sid Dermay. I'm the Ada Lovelace Fellowship Chair today, this year, not just today, which was actually a new position put together for this year. So we've been able to do some really fun programming for our fellows this year since we had to change the way it looks a bit. And we're just really excited at all the support we've received from our sponsors and the work that we've gotten from our mentors. And it's just been a really fun experience for our fellows this year. So thank you, everybody, for your support on that. And I'm going to go ahead and pass it off.
And I also want to say thanks Strafe, who is our awesome community manager. And they have worked so hard in reaching out to the community and making sure our messaging is on point and just getting the Discord set up. All of the work that you see on Discord is all Strafe making this happen. So yeah, thank you so much, Strafe. And to, of course, Alicia, our fearless executive director leader. So it's been great to work with you and our board of directors who are always working behind the scenes to make this real. And our panel of reviewers, it was an extremely tough choice to select the talks we have this year. And I'm really proud of what we've put together. So you can follow us on Twitter at OH Summit. And there are links to join the Discord, and there are links to our YouTube channel, which you've obviously seen if you're here. And we will be taking questions for each of the talks through Discord. So there's an individual channel that you can go to and ask questions and also continue the discussion with the speaker and with the rest of the community after that's done. Of course, this wouldn't be possible without all of our sponsors, many of whom are also members of the open source community and producers of open hardware themselves. These folks provided all the gear for the awesome goodie bag, which is still available through Eventbrite if you missed it. So we are going to send out one final batch of goodie bags after the summit. This is also the fastest way to enhance your 2022 sticker collection. I'm really excited about all of the stickers I've been able to add to things with this. And this year we also have a mug and bag and all of the branding designed by Dusan Milic. And they also feature all of these adorable open source creatures. So we are gonna also have Discord demo tables, and they are dispersed throughout the day. So the full schedule is in line with our speaker schedule on the website. And you can drop into these Discord rooms. Some of them are voice channel, some of them are text channel. They will be open, but we will have dedicated times throughout the day where you can go and hear what these folks have to say about their products or about their community. All of our talks are also going to be recorded, so if you miss something while you're in one of the demo rooms, don't worry, we've got you. And then after the event, we are going to have an after party with Trivial Dispute, and it's going to be tech trivia at 8 p.m. Eastern time. And if you want to find a team for the event, then we have a Discord channel as well, so you can find your tech trivia team. So now I'm going to pass it off to Nadia Peak, who is going to MC the event.
Thanks, Lee, and thank you, all of you, for organizing our virtual summit this year. It's been really amazing to see it all come together. And our first keynote speaker for today is Ashley. Ashley Jane Lewis is at ITP, and one of her pieces of trivia is that she's taught more than 3,000 young people how to code. So really excited for Ashley's talk. Welcome, Ashley.
Hi, everybody. Oh, this is like so magical. I've never given a talk on StreamYards before, but there was just like a really fancy animation that really outdoes Zoom in front of my eyes. Hi, everybody. I'm Ashley Jane Lewis. I'm really excited to talk to you all today, and also to just be in community with all of you who are here as speakers and attendees. It seems like it's going to be a really spectacular lineup. In classic fashion, I've prepared too many slides, so I am going to get started right now, and hopefully we will get through everything. But I want to be really mindful of time as well. All right, some slide sharing magic. Hopefully you can see my slides at this point. Okay. Okay, well, I don't see all of you, so hopefully if you don't see my slides, someone will interrupt me. But I'm Ashley Jane Lewis. I'm here to present a few tools for reimagining the future. This is not an original title. This is a play on a title by a very important person in history, which I will get to in just a moment. So just a little bit about me. I'm a new media artist. I am a creative technologist. I'm also a Black futurist. It's a category of art, category of technology, a category of science that really thinks about the ways in which we're writing ourselves into the future, imagining the future, and creating artifacts through technology, through art, through exhibition, through talks, through writing of that future in order to secure the future for Black people. I'm just going to flip through a couple of different slides of my work. I focus mainly on multi-species survival, which is very broad, but just allows me to really sink into my interests and passions around activism, around science. This is from GenSpace, a really beloved science lab in New York, around technology, and allows me to really think about imaginative ways to talk about the future and really pragmatic, practical ways to actually walk towards those futures as well. So I've provided this kind of lens on a consulting basis for many different places around the world, also as an educator in many different contexts, and as well as in my art practice that uses a combination of technology, hardware, software, performance art, fabrication, and installation. Some vintage work that I think, was some of the precursor to this. I'll drop some of these into the Discord. I've had the pleasure of working for similarly minded folks at ML5, P5, the Processing Foundation. I did go to ITP, which was mentioned at the top of the call. And most recently, my work has been featured in this large campaign that Google produced around a demonstration of different ways that people are using technology, mostly in the Black community, focusing on 5 Black women and the different ways in which they're fusing their activism practice to their technology-driven practice. So as a broad lens, that's a bit about who I am. I have a lot of different inspirations for my work. I've chosen 3 to just present to you today. There's a lot of really incredible work on this topic. So if this is like Afrofuturism is like a new headspace for you, especially from the context of hardware and technology, hit me up. I can give you like a list of like 700 people you should check out. But for today's purposes, because we only have 30 minutes, here are some folks that I really try to keep in mind. For a long time, I think my practice was sort of divided into a bunch of different pieces that felt really disparate. And these three women really helped me through their writing and through their art see them as interconnected in new ways. So I'll start at the edge, actually, the far edge, with Adrienne Maree Brown. I think that this quote is really exciting because it helps put into perspective a lot of the activistic work that people are working through and the kind of imaginative tools that you need to do activism-driven work. So Adrienne Maree Brown says, "I believe that all organizing is science fiction, that we are shaping the future we long for and have not yet experienced," which is kind of cool to think about, the idea that like through protest or through grassroots organizing, or even through just trying to take a stand at your workplace or community space to create a better near future, that you're using an imaginative tool to embark on a space you haven't yet seen inside of your ecosystem. So I thought that that was really exciting. It really helped me think about the ways I was imagining science fiction and activism separately and tying them together. And then the one on the left edge, Audre Lorde. I love this quote. I mean, if you're a fan of Audre Lorde, you'll know everybody says this quote all the time. But the master's tools will never dismantle the master's house. And as an activist who works in pursuit of freer futures for Black people, there's a point of friction in doing that through technology that I think is really important to me. It's really a productive point of friction. Most of technology is used in ways to oppress people who look like me, people who believe the things that I believe. And so in many contexts, being a technology-driven artist who's trying to work on Black futurist models and demonstrations is contradictory. And I think that that's really important because it's also very like grounding and helps me try to make sure that I'm reconsidering all the ways that my work interacts with perspective and potential harm. And then this quote in the middle, Octavia E Butler, who is our surprise extra presenter of this talk. This is her quote. "I was attracted to science fiction because it was so wide open. I was able to do anything, and there were no walls to hem you in and no human condition that you were stopped from examining." So I wanted to focus today's presentation on just expanding some of the ways that we at this conference and in this discipline can learn from a thought leader like Octavia Butler to continue to, course correct, I suppose, our work in the direction of, open accessibility, anti-racism, and just like generally designing things that are for everybody. So Octavia E Butler, if you've never heard of her before, I can hold up like 10 books. I'll hold up this one because everything else is like stabilizing with objects around me. She's a science fiction writer, Black, queer, female science fiction writer, often touted as one of the writers who really blew the genre open for Black people. She wrote books like Parable of the Sower, Parable of the Talent, Clay's Ark, Xenogenesis, also known as Lilith's Brood. And she was also the origin of the phrase, "Make America Great Again," which is very funny. Very funny when you think about how that phrase has taken a wild left turn. And obviously her context was not the same as the context of the former president of the United States. Her context was actually using it as a slogan that a dictator would say on a regular basis, which always makes me wonder if somebody didn't read to the end of the book, somebody from the PR team of the previous president of the United States, but who's to say? Maybe he is a fan of Octavia Butler too. Today I wanted to talk about rules for predicting the future. So Octavia Butler had, a long writing career that really took off, unfortunately, after she died. But she wrote the Parable books, which at the beginning of the pandemic had a huge boom of popularity, largely because they seemed to be predicting many of the struggles that we were going through and continue to go through today. And so, a lot of people often speculate, like, what would Octavia think of the situation that we're in and how we got ourselves here? And it is a bit eerie that her books were set to take place between 2024 and now. But fate or whatever. But one of the really interesting pieces of writing that I love to return to is collection of thoughts that she assembled for Essence magazine in the year 2000 called Rules for Predicting the Future. We're going to like kind of sit with these rules today. And so the book that they're inspired by, A Parable of the Sowers, was originally published in 1993. But, you know, these are things we should return to on a regular basis. So Rules for Predicting the Future. I just want to read you this excerpt from that article, and then I'll tell you why we're even talking about this here today at the Open Hardware Summit. So this is between a student and Octavia Butler, like a conversation excerpt from around the year 2000. So the student asks, so do you really believe that in the future we're going to have the kind of trouble you write about in your books? A student asked me as I was signing books after a talk. The young man was referring to the troubles I had described in Parable of the Sower and Parable of the Talents, novels that take place in a near future of increasing drug addiction, illiteracy marked by the popularity of prisons and the unpopularity of public schools, the vast and growing gap between the rich and everyone else, and the whole nasty family of problems brought on by global warming. I said, I didn't make up the problems, I pointed out. All I did was look around at the problems we're neglecting now and give them about 30 years to grow into full-fledged disasters. Okay, the young man challenged. So what's the answer? There isn't one, I told him. No answer? You mean we're just doomed? He smiled as though he thought this might be a joke. No, I said. I mean, there's no single answer that will solve all of our future problems. There's no magic bullet. Instead, there are thousands of answers, at least. You can be one of them if you choose to be. So why are we talking about this here today? Well, when Lee asked me to be keynote for today's conference, you know, I took a look at the previous keynotes, the previous talks that have shown at Open Hardware Summit of the past. I also took a look at the theme of today and really just noted how much technology for social good there is in the lineup, how many people here are trying to create things that are not just providing more access by the nature of their work being open, but also trying to create more accessibility, trying to create more education opportunities, trying to create more creativity inside of a field that can sometimes be sterile. And so I feel like what we're doing at the undercurrent of our work is working on a future we haven't seen yet, is imagining together like what benefit could come from having like more creative antennas, which I know is a talk coming up, or more responsibility with the way that we manage our waste in hardware, or more educational opportunities for people who don't have access, for communities of color, for women, for queer folks. And so if we imagine, Adrienne Marie Brown style, that all of the work that we do in pursuit of a future we haven't been able to see around us is a pursuit in trying to develop a future, to create a future, then it feels like there's actually quite a great tie between the Open Hardware Summit and some possible rules for predicting the future, some considerations for designing the future together. So, surprise, Octavia Butler, showcasing at the Open Hardware Summit. It's also just like important for us, I think, as people who are engaging in technological fields to consider drawing wisdom from characters that have not had like a lot of space in this kind of spotlight, often like Black, female, queer characters. So this is what I want to propose we do. So I have taken a look at each one of the rules. There are only 4 that Octavia Butler has written in Essence magazine in the year 2000, Rules for Predicting the Future. I've made a slide for each one, a little excerpt from for you from the article. I want us to sort of look at each rule, and then I want to show you some tools that I've used to engage with that rule, particularly tools that have helped to activate that rule in ways that collectively sort of reimagine the future. And then I would love for you, audience engagement opportunity, to drop some of your tools related to that rule into the Discord channel for this talk. Don't be boastful. Being boastful is super boring, but rather like, let's think of this as like a way to sort of aggregate different methodologies. Tools can be technologically driven, of course, but also tools can be social structures, tools can be syllabi, tools can be educational workshop parameters, tools can be outreach methods that have been able to give you audiences that are not normally served in this context. And then, the long-term goal, number 4, the long-term part, is making work that helps collectively reimagine the future, considering these rules. So I'm going to jump out of the slides for just 1 second and show you this keynote. So, yes, there's lots going on already. So this is the channel in Discord. It's called Keynote, and with each tool that we come up with, each rule, we'll just, drop some links, some methodologies, some considerations into here, and hopefully at the end we've got like a nice big pile of resources. Sound good? I can't see you, so I'm just going to assume it sounds great to you. And so, just to think about it a little deeper, I think this excerpt is also really meaningful and helps us sort of, contextualize what the point is at all, which I'm sure you're already a part of because of the work that you do. So why try to predict the future at all if it's so difficult, so nearly impossible? Because making predictions is one way to give warning when we see ourselves drifting in dangerous directions, because prediction is a useful way of pointing out safer, wiser courses, because prediction, most of all, our tomorrow, is the child of today. Through thought and deed, we exert a great deal of influence over this child of tomorrow, even though we can't control it absolutely. So it's best to think about it, though. It's best to try to shape it into something good, and it's best to do that for any kind of child of the future. And so with that in mind, let's jump into the first rule. Rule number 1 is learn from the past. And so this is I think, a really meaningful rule that in the work that I have seen in the technological field, we often ignore. And so this one, I think, is also possibly, a reason why many of the guest speakers are here, because they're seeing things that have taken place in their industry that they would like to change. Octavia Butler, in a very humble sense here, writes, "Of course, writing novels about the future doesn't give me any special ability to foretell the future, but it does encourage me to use our past and present behaviors as guides to the kind of world we seem to be creating. The past, for example, is filled with repeating cycles of strengths and weaknesses, wisdom and stupidity, empire and ashes. To study history is to study humanity, and to try to foretell the future without studying history is like trying to learn to read without bothering to learn the alphabet." So yeah, I think that this is really exciting, and some of the ways that I have tried to learn from the past and the present in my work in working with technology is through a lot of data visualization, to be honest. I think that the act of kinetic sculpture is really meaningful to connect with people. So for about a year or so, I spent time connecting with activist groups in New York and Toronto to aggregate data on the folks in the Black community who we've lost due to police brutality. And so this is not perfectly sourced data. A lot of the data that's out there is not reflective of the true volume of people who have been lost to this particular kind of violence. But the act of talking to people allows you to get more information, get more names. And this piece was kind of born out of that practice. So this piece uses an electronic component called Programmable Air, which is designed by Amitabh, a peer of mine at ITP, to inflate and deflate the lungs of this hanging structure in homage to each person who has died by the hand of police brutality, each Black person who's died in this way over the last 10 years. So it slowly inflates and deflates these lungs with this hardware. And this was a real group effort. I really couldn't have done this without a lot of the data from ethnographers at NYU and from a variety of community groups who would prefer to remain anonymous for obvious reasons. But it takes about 12 days to witness this piece in full, which is jarring given that it's about 5 minutes to inflate and deflate each on behalf of each name. And so, this kind of articulation helps us really learn from the present and the past by witnessing it, by having to endure the time that it takes to witness this kind of work. Before we go to rule number 2, I would love, again, for you to talk about ways that you've helped activate information about the past, like how has the work that you've done helped to illuminate issues that are present and past that allow for us to sort of like get more context of lesser known data, lesser known histories, lesser known issues, to be able to inspire people to take more action. So if you can drop those into the Discord, that would be great. We can take a peek at it at the end. Rule number 2, respect the law of consequence. And so Octavia Butler also had this really famous quote that goes something like this. This is part of it. All that you touch, you change. All that you change changes you. The only lasting truth is change. And so in this excerpt that I've screen capped here, she talks a little bit about this conversation she had with a doctor. But I think one of the things that's really meaningful about the law of consequence is considering like prospective harm, considering electronic waste, considering the consequence of the work that we're making. Does what I want to create need to exist? Who is it for? Who might it harm? And all of these wonderful things that are coming up throughout the day in the talks that are within the lineup. I'm really excited because it, I think, is going to create a wonderful basis for considering new parameters of respecting the laws of consequence. Some of the ways that I've done this, again, definitely not alone. One of my favorites is through the work of ML5, led by Dan Schiffman. We spent a lot of time considering what a machine learning platform would look like should it really be a testament to its slogan, like friendly machine learning for the web. Who is it friendly to? Who is it not friendly to? Who does it respect? Whose bodies does it consider? Whose bodies does it protect? Whose identities does it consider and is tested for? And really just like, what is our responsibility as people who build machine learning platforms? What is our responsibility to the public who very like openly know that these systems are often used for harm and used in ways that like oppress Black people, people of color, just frankly don't even work on those platforms. So we spent a long time considering these things and building community codes of conduct that allow for us to really hold some kind of relationship with our actions. Considering the uses of technology, writing new licenses and community agreements. And so, though this isn't like the most imaginative demonstration of how you go about considering the laws of consequence, I think that creating frameworks for people to be really imaginative is also a really meaningful endeavor. So this created a lot of space for people to like mindfully engage with machine learning in their creative practice. And I think that that's really exciting to me as a creative technologist and a Afrofuturist who really wants to see the future like actually get to the envisions that I have in my imagination. Just a little thank you to the contributors who are also a part of this lineup. In a more artistic sense, this piece also aggregated by a bunch of data that was provided by some collaborators in part of a creative group in Jamaica who had some data for me. This was an imaginative speculation on what it might be like to be a Black person eating food from our home country that makes us feel tighter to our culture, while also trying to avoid all of the harm that goes on in transporting that food from its origin country to your plate. And so this speculated on a future where people of color are building these tanks for the food and the seeds that they want to eat, tricking the plant inside into thinking it's in its home country. So it was live, pulling information from different APIs. So this is a little Jamaican orange tree. If it was hot in Jamaica, it'd be hot in this box. If it was daylight there, the lights would be on. If it was humid there, then the humidity would, the little humidifiers at the bottom would go off. If it was raining there, there'd be water pouring down. And so, yeah, just really thinking about consequence through the act of art is like such an exciting thing. And I feel like something we can really do with imagination at play, with stakes, but with also like great creativity to think about like parameters outside of what's normal to us in order to hold less conflict and oppressive structures in the way that our work gets executed, in the way that our lives are executed. So once again, the reminder is that this is respecting the laws of consequence. Drop your art practices, your methodologies, your syllabi, whatever you think is relevant for rule number 2 into the Discord. Making great time, which I think I probably just jinxed by saying it out loud. Rule number 3, be aware of your perspective. I love this rule because I think that this is the thing that is the most difficult to do because we all come with different biases. But a lot of our technology is really designed by people who don't look like me. A lot of our technology is also, oddly enough, stemming from science fiction writing. And around 70% of the technology that we use every day is inspired by science fiction writing. So Octavia was super humble in the way that she talked about her relationship to real life. And like, little did she know that in reality, science fiction plays a huge role in the way that we see ourselves, the way that we live our lives out loud. And so if the status is around 70% of tech coming from science fiction, then the question I return to a lot in my work is who's writing science fiction? Therefore, like, who is writing the future? And so being aware of your perspective and understanding your influence is really, really important. It's also a great means of like stress, because it often means that you have to spend a lot of internal time like figuring out where your biases are, which identities you're omitting, which identities you're prioritizing. And one of the best ways to combat that is just to work with lots of people. This seems really obvious, but in reality, I think most of us prefer to work alone. If I'm being honest, I'm sure if you're being honest, that's the way you feel too, or at least in tight groups, or at least in groups of people who you know quite well. This was something that was like really exciting and also nerve-wracking for me to sort of unprogram in my brain, deprogram, around 2020, in the spring of 2020, after the murder of George Floyd. A bunch of speculative designers got together to think about the state of the world. I mean, I'm describing it very poetically, but really it was like a series of panicked texts about what is happening and how we can get involved. What's the role of an artist in the time of such great conflict? And one of my speculative designer friends, Kadra Mensa, mentioned to me that perhaps it would be worthy to maybe it would be worthwhile getting together with other folks to say to ourselves, well, after this incredible hardship on the Black community, with all of the popularity of defunding the police around us, we should really figure out like what we want instead, like what we as people of color want instead of police. So this is like, New York was talking about defunding the police, Minneapolis was talking about it, Toronto was talking about it, LA was making some significant strides. All of this is a bit wild to think about in hindsight now because we haven't seen an extraordinary amount of action. But at the time, summer of 2020 felt like there was momentum to move through some actual financial shifts that might have, prevented the murder of George Floyd. And so this group of people got together overnight to create a world building activity online, an open call for anybody prioritizing Black identities who wanted to take real world stakes and imaginative play and think about designing new worlds together. So how can we create a packet of like open source worlds that clearly articulate what a future could look like without police? What does our community look like? How do we keep each other safe, knowing that police do not do that in effective ways? And so we put this call out. We're like, it would be great if we had 20 people apply. And we had like 400 people overnight apply to this opportunity. And we ended up running these sessions for almost a year and created 60 open worlds, by the definition, with illustrations, with articulations through writing about what these worlds would look like, how communities would hold each other in these worlds. And it was designed by close to 600 people, like 590 of which were Black people. And so it was an incredible year. So many incredible guest artists who have also made huge contributions to the worlds of technology and hardware and science just jumped on board to participate. Stephanie Dinkins, who has been working on Black AI in creative pursuits for quite a long time. Miriam Kaba, she's like easily one of New York's most famous activists. She wrote We Do This Till We Free Us. Ruha Benjamin, who wrote Race After Technology, Fred Moten, who won the MacArthur Grant last year, Omari Solfinger, who works with prison abolition and creative theater, and Ayo Konsende, who's a reclamation artist, Black futurist artist, all guest lectured, reviewed worlds, helped contribute to the development of these worlds. And then these worlds were passed off to artists. I'll show you here, like Megan Aguirre, who created visuals that attributed some aesthetics, some ways for us to help imagine how these worlds might be in action. This is another world imagined by Intelligent Mischief. You'll have to look at the packets of world to know the context for this, but here's a little teaser. This is IK, a classmate of mine, but also a participant in this workshop. She's holding up a score that she really quickly copied from a piece of music that Duke Ellington wrote. She's describing to us the ways in which Duke Ellington creates foundations of sound so that certain notes can take higher auditory risks and then be supported by this like pillow of sound, and how we can use this as a metaphor for how we might imagine supporting at-risk community members in our neighborhoods. So this one, as a reminder, let's go back to the top, being aware of your perspective. So if I had designed these worlds on my own, they would all really, uplift the myth that Blackness is a monolith, that we are also operating in ways that are just like serving one kind of identity. But by bringing on hundreds and hundreds of people, you get such a more robust understanding of what the issues are, where we stand, what kinds of imaginative properties we could use to change the circumstance that we're in. So I learned so much this year, in the year of like summer 2020 to summer 2021 in running this project. And those worlds also go on to live in many different ways. Like policymakers have used them to make decisions. Educators have been using them in classrooms around the nation. People have been using them to design community gardens. It's really been exciting to see how they've taken off. Last rule, number 4, we're almost done. Count on surprises. So this is a really interesting rule because there's one way to read into this, which is very whimsical. There'll always be unexpected things to consider. And there's also, maybe a more timeline-centered, budget-centered way to look at this. By counting on surprises, you might also lean into a practice that is less rushed, that is like not going to throw away the EDI pursuits or the open access pursuits because there's not enough time or because the budget runs out. Like, how do you cement some of the challenges into your work so that you like leave space for surprises as you continue to work on these things? I think one of the like most tumultuously surprising projects that I've worked on is the Slime Tech Lab. This is it. It's a mobile science lab that my collaborator Ayo Konsende and I, who's pictured in the slide from Investing in Futures Beyond Policing, we built this lab in order to hold conversations with Black communities about difficult subject matters like immigration and borders, with our third collaborator, Slime Mold. And so this is Slime Mold. It doesn't grow this fast. This is a accelerated video. But this collaborator has all kinds of really interesting properties. If you're familiar with Slime Mold, you'll know that lots of laboratories focusing on machine learning and artificial intelligence have been using Slime Mold to just test the efficacy, the efficiency of their machine learning models, because it has such an efficient way of navigating the world. It also has lots of beautiful models of mutual aid, where it shares its nutrients to the weakest cells before the strongest cells eat. Has all kinds of expressions of gender. So there's a lot of really exciting reasons to work with this organism beyond the fact that it's beautiful, as you can see. So the Slime Tech Lab, we also designed a sensor and a camera function and some code that would allow for us to measure the movement and the patterns of the slime mold within these little terrariums that we designed. We hauled these little sensors all over New York to hold these workshops, to teach people a little bit of code, to talk to them about collaborating in ethical ways with biology, to think about our consequences of working with the biological world, and also to write stories that help us express the kinds of challenging nuances of being a person of color in a world that isn't designed for you necessarily, in thinking about borders, immigration, and general survival. This sensor was originally showcased in 2019 at Sketching in Hardware, and has been something we've been able to sort of adapt and roll with. These are some prototypes, hence this tape over here, to be able to just sort of think about really meaningful ways of engaging with challenging conversations with technology and with hardware design. These plans are also open source as well. So counting on surprises, the reason why that project is so surprising is because if you think working with people is a way to experience things that you didn't expect they would do, working with an organism is certainly a way to experience things that you didn't expect they would do. And we're just trying to really center treating this organism with respect, because it's helping us have so many meaningful conversations. And so with each new surprise comes redesigns, comes reconsiderations, comes new ways of imagining ethical behavioral practices as a bioartist. So it makes our timeline sort of like a accordion, but we plan on that in a lot of ways to be able to keep that, to really keep that in mind, so we don't push that to the side for the very nature of deadlines. So here are the 4 rules as a reminder, 4 rules for predicting the future. We've talked about them as 4 tools, or four kinds of rules that help us imagine tools for collectively reconsidering the future: learn from past, respect the laws of consequence, be aware of your perspective, counting on surprises is really important. And these were all, again, designed by the incredible Octavia E Butler. It's been a real pleasure to talk to all of you today. I hope that this helps you sort of think about parameters that you could continue to design your work from. And that is the end of my work. If you'd like to follow me, my handle is here, my email is here, and it's been a real pleasure to open the talks for the Open Hardware Summit. Thank you.
Thank you so much, Ashley. This was an incredible talk. I echo comments from the chat. We love this. Can we just listen to Ashley all day? But we cannot, because we must also listen to all of the other upcoming amazing speakers. And next up we have Alex Glow, an amazing hackster who you might have met with her cybernetic parrot companion Archimedes, who is going to give us our next talk. Welcome, Alex. Thank you.
I really should have set up one of these to actually assist me with my talk. As you know, so as Nadia mentioned, you might know me as the video personality from Hackster.io, which is an online community of hardware developers, people publishing open source tutorials, all kinds of good stuff, which is very relevant to my talk. Sorry about the sun in my face, but this is my companion robot Archimedes. I've got Fenrir over here too, and they're going to help me talk about sustainable practices for creating hardware. So let's just share my screen real quick. That's getting ahead of the game. Okay, so hardware tutorials. Yeah, for the last few years, I've been really passionate about exploring sustainable ways of creating electronics. And an important thing to note here is that I am not an expert. I have lots of interests. You can see that I'm into companion bots, custom circuit boards, arcane tech tools, and biohacking, and also music. On Sundays, you might catch me doing a Space Song Sunday on Instagram Live. But I am not an expert. So my goal with this talk is to start conversations and learn more about things that I can add to this wiki, which is in the spirit of documentation, basically a way of aggregating all these tools and resources that I've come across through my own research over the years, through groups like climateaction.tech, and also through conversations with people. So as part of my work, I interview people every Tuesday, and I've been making a focused effort to bring people to the forefront who are working specifically on this type of thing. And I'm going to put the link out on my socials. I'm so used to saying link in the description. Afterwards, and this will be available in lots of places, put it everywhere. because what I want is for people to be able to use this to reference it in the future, and we won't just have to stare at like a dark screen the whole time. And you'll be able to go back and I won't have to just read it off to you. But yeah, so the aim is to start more conversations, gain more stuff to add to this wiki, provide actionable steps to people who are at every stage of building the hardware. So whether you're prototyping, if you're a beginner who's learning, if you're someone who's actually running a small electronics business, things like that. Even if you're a larger electronics company, there's always stuff that you can do at every level. Also, further down here, I want to provide inspiration for different projects that you can build. If you are looking for stuff to build, you know, you want to build electronics because that's your passion, totally understandable. I'm there too. But also, maybe you have misgivings about the idea. Sometimes I wake up and I'm like, should we maybe not be building technology right now? And that's definitely one of the things to talk about. But so that's part of this. I want to promote visibility of some of these interviews and people who are doing cool work in sustainable technology. And above all, the goal is to empower people with these resources to come back, learn, to provide, to share your own work and get visibility for that at every step of the process. So one of the first things that I want to talk about here is, the climate situation isn't necessarily our fault. We are, let me try to show my face. That's fine. Yeah, so there's a lot of information out there about how it's not individuals who are responsible for the climate situation. We don't, no one person is like, we don't have to solve it ourselves. I do not have to solve it. You do not have to solve it. And also, studies show that it is, the top 1% of people are producing 50% of the emissions, especially through travel and things. And, I believe it is 100 tech companies or companies are producing 70% of the world's carbon emissions. This is a problem that can also be solved through legislation, and there's some resources here around ways that you can do meaningful action and agitate for legislative change that can help with this. There's also a UL white paper that's linked in here. And so even though it's not our individual responsibility necessarily, that's something that BP popularized, the idea of the carbon footprint as shifting blame onto the individual from their own actions as a fossil fuel company. Even though it's not necessarily our fault, it is our responsibility and it's our power. We as creators of technology have the power to change this, to shift the direction that things are going. We can build things, we can change the conversation, and we can support people who live in a world of technology, whether or not they know how to use it. And I think that's a really important piece of the puzzle. And we'll get into repairability and stuff like that. So let's jump in again. Let me see if I can share. Yes, great, thanks. Yeah, so the first thing I would like to start with is like, when you're thinking about building something, ask yourself, like, why are you building the thing? If you're building it to solve a need, maybe ask yourself if there's an existing project that does what you want or what you care about, rather than manufacturing something new. There's a really cool page from iFixit that says that, the best phone, the most sustainable phone is the one that's already in your pocket. The best technology, therefore, is the one that's already being manufactured, that, we can always take open source projects and tune them and improve them and stuff, but ask yourself, do I actually need to build a whole new thing? Is there a low-tech solution? One of my favorite things, I have this idea about rumble strips, where they're just like the most elegant expression of problem solving in a low-tech way. So if you want to keep drivers from running off the road if they fall asleep or whatever, or if their attention drifts, you could build, and this exists, there's all this technology for like measuring people's sleepiness by how often they're blinking and like whether their like head is dipping down and things like that. But we have this technology, rumble strips, which is simply you stamp indentations into the road at the edges, and it creates this vibration when you drive over it. And that does so much of a better job, and you don't have to charge it or anything. So I think that the best solutions It may still involve technology, but also try and be elegant with it. Try and see like, what do you actually need to make smart? Where do you actually need to put IoT, like connect something to the internet? Could you make it lower power and more resilient and more private by not connecting it to the internet? Things like that. So while we have this techno joy, we want to get excited about technology, but there's always interesting and elegant ways to make things that also don't add extra load on the system. Are there things that you can repurpose? There's some really cool stuff around projects around repurposing old technology. Pardon me. It's very early for me, but I'm also very excited. So there's a few projects that are in the wiki that take old technology and give them new life, basically like zombies, but cooler, with new technology in them. And then, yeah, so if you're looking to solve a need, those are the ideas that you can think about. And then if you're learning or looking for inspiration for things to build, then we have some suggestions for what you can build. But let's start at the top. So we talked about every stage of the process. So I want to focus on people who are literally building and shipping hardware. There's a really cool blog post by Christina Sear, who built the Circle phone, about can a smartphone be sustainably manufactured? And she goes into all this in-depth research that she's done on materials and batteries and recycling and things like that. Can you reuse individual components? Lithium batteries. Power sources are a huge part of this. I've got some resources for that. There's a really cool laptop coming out called the MNT Reform. And I think that Lucas is actually giving a talk later on, so you should jump on his talk and see what he's doing with this modular repairable DIY laptop. And they're using types of batteries that don't use cobalt because that's a conflict mineral and it requires a lot of mining. Lithium also has issues, but you can recycle it better. Yeah, so think about enclosures and what they're made of. So much is made of the fact that PLA, or polylactic acid, is compostable, but it's not actually compostable outside of industrial facilities. So you need like a 6x6 foot cube of it and lots of high temperatures and stuff in order to make it actually compost. So there's some other options. And then also the PLA is a thermoplastic and you can reuse it by reheating it up and reforming it. And I've done a bunch of experiments on that personally, including trying to cram it down a glue stick glue gun, which worked okay. I've actually documented those experiments in a whole other wiki that I'll link here. No. Here we go, plastic experiments. So extruding it through a hot glue gun, sticking it in various molds and things like that. Other materials that you can use that are more sustainable. Jiva Materials is a really cool new technology that's coming out. They have a fully recyclable and biodegradable PCB substrate, which is very exciting. Look at that. It's made of wood, and they call it Soluboard. Sustainable materials for design. This awesome company, Lumia Soft Circuit Systems, who make beautiful soft circuits with stickers and heating pads and touch sensors and things like that. And they have a whole page on sustainable materials that they use, including a thing called ECOA, which I believe it is an alternative kind of wood. Fabrication with recycled plastic, cardboard, and more. I did an interview with Agustin Arroyo, who talks about, he has a project called Pulp It that is 3D printed molds that you can use to recycle cardboard into different shapes. And he has an example where you turn it into desk implements, like a cup holder and even a little tray. And that's one way that he does it. But he also talks about creating your own plastic for 3D printing or for vacuum forming that is based on recycling stuff yourself at home. Now, a lot of these are, that one specifically is about things that you can do on a more personal level. There's a lot of things in here for people who are running their own businesses as well. Precious Plastic has a really great set of guides. You can even go into business working with your own plastic recycling machines that they will supply. Community workspaces are a huge part of this as well. And then there's 3D printing filament. So there's a cool article from All 3DP that compares various recycled filaments. We talked about PLA a minute ago. I actually happen to have a new spool of filament from Closed Loop Plastics, which is this beautiful deep purple, sort of dusty plum color. And this is made of recycled plastic cups. And that's also in the wiki here. Yeah, so you can recycle your own PLA. You can buy recycled filament. Resin printing, I think, is a lot harder to do in a sustainable way, but you do get nice results. A big part of the idea here is not to be perfect. Nobody has to be perfect, and we're not going to all solve it on ourselves, but anything that you can change, anything that you can do is going to help. I'd like to bring out my assistant Fenrir to talk about using cardboard to prototype. So, oh, actually, both of you guys, come up here. So maybe we can show these guys a little bit larger. I'm not in charge of the viewpoint, but yeah. So Archimedes here actually is one that I designed with his little beak using and his wings using recycled CDs. So there's a cool process that you can do where you take old CDs and boil them to delaminate the layers, and then you can cut them apart with scissors without them cracking. And I've used those as accents on my little companion bot Archimedes that was mentioned before. And oh, also, this version of Archie, I tried mending him using HDPE from milk gallon jugs. So they're made of this high-density polyethylene that you can melt down. It melts a bit higher than PLA. It can be a little challenging to recycle, but you can also just cut it apart. So the left side of his beak here is actually falling off. That's a successful experiment with a null result, which is that maybe don't try hot gluing HDPE to stuff. But yeah, you can. It's repair in action. It's sustainable materials in action. And then Fenrir here was prototyped around a cardboard chassis. And if you look at him, you can still see bits of that and the goldfish container that he was made of with that orange, beautiful orange aesthetic inside. And the nutrition fact. Oh, look at that. How much iron? 4% iron in a goldfish, apparently. But yeah, you can use these as the bases of your projects while you're prototyping. Not everything has to be a gorgeous version. You can make your first one out of cardboard, lasers up really fast, and it smells nice too, which is a bonus. Let's see. Let's talk about the Jewel Thief real quick, because I'm afraid I might run out of time. Oh my gosh, it's already 7:59. Ah, okay, well, I've accidentally almost gone over time. I could talk about this forever. Check out the wiki. Oh, I can have more time. Yay. I'm going to scroll through this really fast. No, I'm going to do a live demo. I want to show you these things I've been making. So personally, one of the other things that I love to do with my projects is to make them versatile, which for me means making them so that not only does it work as a piece of hardware, but it works as a piece of aesthetic art as well. So every time that I make something, usually I try to make them wearable. So this is an Esp8266 Programmer. And whether or not these worked on the first try, which fortunately they did, but even if they didn't, I would still be able to wear them as like a cool technological earring. And yeah, so that way, like, even if you have extras, even if they go obsolete, even if they don't work, you still get to have a cool piece of technology that you're able to wear. And I wanted to show you this really cool circuit, the Jewel Thief, that I actually designed specifically for this talk because I'm very excited about it. It is a little circuit that you can use to run low power devices off of dead batteries. So this one is designed to work with this maker tape conductive tape. And this is a white LED that's extremely bright and blinds me every time I do this. Yeah, and the circuit is just beautiful because it's made with these ferrite toroids that you can salvage out of existing pieces of technology. You can grab pretty much any types of NPN transistor, grab resistors out of wherever, and stick it all together and design your own enclosures to make it into whatever kind of device you want. And you can also run this different types of things off of this. Anyway, so to wrap up, check out the wiki. Very exciting. Thank you all. Thank you, Open Hardware Summit. And I'll put the links in my Twitter, which is @Glowowski.
That's awesome. We're running slightly behind, but maybe
so
if you're available out, no, it's not your fault at all. We're just like, we've really packed it in here. But maybe there's some questions for you on Discord, so if you have a second to check those out, it would be
I'm going to
great.
put the link in the Discord, and I'll totally jump in there. I'd love this to be an ongoing conversation. Thank you so much.
Thank you, Alex. Our next speaker is Jerry Devos, who connects with Alex through Precious Plastics, coming to us not from the Netherlands, but from somewhere else.
Yeah, thank you very much. And thanks for the introduction. And in the next 20 minutes, I will basically tell you how Delft Open Hardware got started, how frustration was involved. And indeed, sorry if my connection is bad, but I need to explain a bit of the context where I am now. So let me see if I can share my slides. Yes, they appear. Thank you. So first of all, I'm currently in the Himalayas setting up a plastic recycling workspace with precious plastic. And the whole story of Delft Open Hardware basically got started with plastic recycling 5 years ago. So in 2017, I joined a project called Precious Plastic. And this is an open source project that tries to make plastic recycling as simple as possible. And back when I joined, we were just with maybe the 4 of us, and I really enjoyed working in this way. Over that year, more and more people joined, and it was a great way to be able to share the skills that I have, and with my skills, make hopefully the world a little bit better, and be able to share that with everyone. So for over a year, I was there, I helped out, made version 3 of Precious Plastic, and this was something that I truly enjoyed. But I also wanted to learn a bit more skills to make the world even more awesome. So basically what I did in 2018, I enrolled myself at the Delft University of Technology to do my master's in integrated product design. So basically inventing all possible different products. I would learn more skills and would be able to apply them to make it even a cooler world around us. But the first thing that I was greeted with when I entered the study was this document. I had to sign it, and it basically stated that every project that you would do as a student would be part of the Delft University, and if it was really good, it should get a patent and your name should be on it. And this went in against so many of my principles. Like, I wanted to be able to share anything that I would work on and have other people build upon it and me build upon other open hardware projects. So back then, basically there were 3 possible things that I could do. I could maybe accept and just try to carry on. I could reject and actually stop my studies. Or I could try and take action. In the end, yeah, it was the last thing. So I found people around me that also found it quite weird that this thing was still existing. It felt like past times, and there were a lot of like-minded people around me who had already started to work on open hardware projects, and basically together with them we started the beginning of Delft Open Hardware to be able to just do something about this and have open hardware in Delft. And for a while in the beginning, basically we were just a bunch of nerds geeking out on open hardware projects over lunch. That's what we would do every Friday afternoon. And yeah, we really liked talking about projects, seeing who was doing which project, if they needed help, or how they could develop a new project. And yeah, this got us started, and we were a group of young, enthusiastic people. And also, not much later, we also got started giving presentations and workshops. So we started to give workshops like teaching MicroPython, or there were people giving talks about their open synth that they were working on. Quick side note, this picture is from a workshop just a few hours ago about 3D printing, about open source, and about how to get started with 3D printing. So this was done today at the Delft University by our community, basically. And they really enjoyed it, and a lot of new people learned about open hardware, about open source, and about 3D printing. So that was a great success. And basically the first signs of change in the culture of the TU Delft started around 2020. So 2 years ago, when the TU Delft started their strategic plan to open science. Initially, this was mostly focused on research and publication, making open access and fair research. But then again, they also saw our active grassroots community that was getting more and more support from different people, but also professors and employees. So they also wanted to be able to support us a bit. It became easier to organize workshops. We could have posters up and these kind of things. And we could run some projects to work on open hardware. But by far, the biggest change came last year, when in 2021, I was hired as a research hardware engineer at the Technical University of Delft. So similar to a research software engineer, but then on hardware, I help students, PhDers, researchers to make the right choices in hardware, in this case, and to help them open up their projects and make it accessible wherever this makes sense. So this really makes it possible for us to develop this community of Delft Open Hardware within the TU Delft, and to support people with educational resources. And we still have these workshops and talks every month. So yeah, this really helps us to grow and to expand this community, because over time we envision that the open hardware part will become hopefully part of the curriculum at the university. And if this is maybe through a course that people can follow or a minor, that's something that we're also still figuring out. But in order to be able to grow towards this, in August, we are launching our first round of the Open Hardware Academy, where people can join for a 10-week program to help others, people can join for a 10-week program and learn about open hardware, about communities, about documentation, all the different aspects, licenses, and to help open up their projects to the world and have them do a sort of first iteration where they are able to share their projects with more people around them and be able to work together. And we think that it's very important to have other people learn these values at a young age, and to be able to have them look beyond money or publications or the amount of research that somebody did, but to be able to have them work on solutions for a common good. And we see more and more people, especially students around us, that want to work on things with a good cause, and not on a very specific niche research project that might earn them a lot of money. They want to solve the world and make it more sustainable, for example. And if you see that with plastic recycling, we can already get 40,000 people around the world excited and join that community, then I also hope that the Delft Open Hardware community inspires many more people to be able to start working on open hardware projects, open source projects, and make it possible for them to explore a new world that helps them reach goals beyond this money or really status, but research, but publications. And we also hope that the Delft open hardware community can be an example for other universities. So making it possible that other universities apply the same sort of community style building and have open hardware embedded in the curriculum, and making it possible to apply this, to bring this to a wider audience, and to be able to share this. So also all the things from the Open Hardware Academy we will be able to share online, and people are free to build upon this, use it, and try it out with their university, their school, or their high school. So with that, I would like to thank basically everybody, especially the people from our Delft Open Hardware community. They have been so amazing to work with, and in just 3-4 years time, we have been able to change quite a bit of the culture at the TU Delft, making it possible to do work on open hardware projects and to actually support them. So we hope that this can be a change for many projects around the world. And with that, I would say let's start a discussion and also see if there's questions on how this community works, or if there's any other questions. Precious plastic related can also be.
Yeah, awesome. Maybe you can tell us a little bit more about how you work on community building. I think a lot of people are probably not in Delft. And maybe there's some lessons that you have of like, oh, this is how I publicized how people could come together. I mean, how did they know you were having lunch?
Yeah. So that's a good question. In the beginning of when Delft Open Hardware got started, we could actually just have physical lunch. And we always had this one place at the industrial design faculty where we would meet up, and we actually have a flag. So that would really help for people to know about this. Over time, this has shifted online. So we still do it every Friday, and it's very chill. People can just walk in, ask questions, but also, join on a more regular basis. So that makes it very low key and entry level. And then, it's a lot word to mouth. So people talk about it and they invite people to our Telegram channel. And that's where we basically, do announcements or organize events.
That's awesome. Do you think that you as a student group have a voice in talking to maybe some of the administration of your university about the policies that they have around intellectual property and that kind of thing? What's like a way in which people might start those conversations with their universities? Yeah.
So I think, we very much started as a student project, as a student group. But now actually we got more and more people, employees and professors also interested in this open hardware, open way of working. And I think, if you show enthusiasm and if you show some examples of projects that you're working on, and if you show, what these things can mean for a broader audience, then, you easily get the attention of the board of these universities.
Cool. Well, it's so great to hear that you've been making progress on that. There's a lot of people talking on Discord about how they've had bad experiences with universities wanting to keep intellectual property and not being able to have access to things that they developed in their labs. So that's really awesome. Can you tell us more about the Delft Open Hardware 10-week program? Just elaborate a little on it.
Yeah, exactly. So in the past, we've done a lot of like workshops and individual talks, but we wanted to be able to give this more in a compact package, and to to create more of these educational resources that people can just read in or follow along with. So that's basically when the plan came to unify all of these different workshops and these different categories, and then put this in the package of the Open Hardware Academy, where we will be able to, on the one hand, give information and educational resources, but also have people discuss their projects and ask for feedback. So this will be run in August and September, and we're still figuring out some things. So we're probably in a different time zone than most of the people, so it can be a bit hard to join. But basically we're open to anybody. There's
How
a
can people find out more? Where should they go?
So for the Open Hardware Academy, there is openhardware.academy, quite simple webpage, and then you can find out more. I will put the stuff in Discord as well. And then about the Delft Open Hardware community, we have a delftopenhardware.nl website, and this also this will be changed a lot over time. So it's now a very basic, minimal website. But we will be putting more projects and more of the things that we've done on there. So that's how people can find out more and see.
Awesome. Yeah, I think a lot of people are very interested and excited about participating in your academy. That sounds great. There's another question from the chat where Sarcastic Teddy Bear says, Jerry, I ran a volunteer medical team for a year Burning Man regional event, so it's fairly straightforward to keep volunteer interest focused into a 5-day time frame and some additional days for training around the event. But how do you keep volunteers interested year round? Is there any kind of aha epiphany solution that you found to keep people engaged?
I think part of that is also a lot of this recognition and reward. Now a lot of people are focused on making research and publications, especially within the university. But we also try to be able to give them exposure within the university to show that these people are part of the open science program, that they are working into a better solutions, and to have them basically show how cool they are.
So making sure that you're elevating your volunteers and giving them exposure and access to a platform. That's awesome.
Yeah.
Well, I think there's a lot of other people that want to ask you questions in your Discord channel, Delft Open Hardware. So if you have time to check that out, that would be awesome. We're going to skip ahead to the next speaker. We're actually going to invite on Leon Anavi first. Leon, are you out there? Who's going to talk about open source tools for making open source hardware? Because why are we using proprietary software for making open source hardware? Thanks for jumping on early.
Hi, Nadia. Thank you very much for the introduction. Today, in the next 20 minutes, I'll be talking about open source tools for making open source hardware. My name is Leon Anavi. I'm based in Bulgaria, in Plovdiv, Bulgaria, and I'm a software engineer. Yeah, you heard it right. My full-time job is as a software engineer, although I've graduated from Technical University. However, I have been interested in open source hardware, and I have been involved with open source hardware for the past 10 years. The past 5 to 6 years, I have been actually making open source hardware on my own. So let's talk about the benefits of open source hardware. We all know what open source hardware is. After all, this is the Open Source Hardware Summit. But let's focus on the benefits. Open source hardware is good for giving confidence that the design will be available if the original manufacturer stops production or stops selling it in certain regions. This could be caused by the worldwide situation or just by a poor business model, and that may cause the original manufacturer to go out of business. With open source hardware, the customers have this insurance that the design is there and they can manufacture it or someone else can manufacture it. Furthermore, with open source hardware, the bill of materials is public. So if a manufacturer designs to make something that costs 10 or 20 times more than the prices of the bill of materials, then anyone can say, hey, I can do this. I can manufacture this on my own and I'll save some money. Furthermore, with open source hardware, we can repair and maintain the hardware that we buy. Open source hardware also enables customization and integration of third-party products. Let's say that you have a very complex product with multiple ingredients. So you can rely on certain parts for this product on established, trusted, existing open source hardware devices, and you can integrate them in your product, of course, depending on the open source hardware license of these modules. So open source hardware is about sharing knowledge, educating students, and getting feedback and contributions from the community. Later on, we'll discuss this in more details. So obviously, open source hardware is pretty cool. And the open source hardware movement is having a momentum for the last several years. So many companies and individuals are saying, hey, we make open source hardware, but is it really open source? And here comes the role of the Open Source Hardware Association, which not only makes this awesome summit, but they run a free certification program which lists products that comply with the understanding for really open source hardware devices. So next time when you're buying open source hardware, double check if this device is actually listed and certified by the Open Source Hardware Association. And if not, ask the manufacturer and the creator of the project to certify it, because it's free and pretty cool. So there are several important questions that I would like to focus on in this talk. Does it make sense to use proprietary software for open source hardware? Is it worth designing open source hardware with expensive proprietary software tools? And this question is a little bit tricky. If you are starting a new product from scratch, obviously the answer is no, use open source. However, there are situations where you have an open source hardware product started 10 or 20 years ago with some proprietary tools, and it might be very difficult to switch from them to new tools. Can you build a sustainable community if your contributors have to pay gazillions for software licenses just to modify, study, and contribute back to your open source hardware project? And the answer is easy. No, definitely not. If you want a community, people should be able to edit the projects. And in order to edit them, they need the software with which these projects have been designed. So definitely consider using open source software tools for making open source hardware. And let's have a look. What is open source hardware product? It's obviously not just a single thing. There are several ingredients. The hardware is the most important ingredient, but we also need software firmware for this hardware, and we need documentation. And this means that we need a bunch of tools to create all these materials, to put them together in a product that can go to a market and other people can buy or make on their own. Let's start with the free and open source design automation tools. Number one on my list here is Kicad or Kicad. This is a very complex software capable of designing really sophisticated boards, but it's not the only one. We also have Jetta. We also have Fritzing for very simple schematics, which is useful for especially for educational purposes. There are a lot of other open source tools that get an honorable mention, but they're either not very well maintained or not very popular, so I won't discuss them in details. Let's focus on Kicad. This is a free and open source EDA software available as a GPL version 3 plus license, and it's cross-platform, which means it runs on GNU Linux distributions, on Microsoft Windows, and on Mac OS. As an open source enthusiast, I'm running it on my laptop, which I'm using for this stream as well, and it's with Ubuntu Linux. Kicad has an integrated 3D viewer, so once you design the board, you can have a quick look at how it would look like, a 3D viewer. You can design really complex boards. The boards that I design are just very simple boards, 2-layer boards, but with Kicad, we can do boards that are up to 32 copper layers. And this is not just a hobby project. Kicad is something very serious. It has a long story. And for the last 5 to 6 years or even more, it has a lot of contributions from CERN. So there are developers that are maintaining it, and they're getting paid to be developing Kicad. Kicad has been already adopted by the industry, so we can have have a look at some interesting made with Kicad projects. And I have selected several really complex projects which are actually open source. We have 2 laptops here. This one is MTT Reform. It was crowdfunded through Crowdsupply. It's made in Germany. This one here is something that actually I have. It's in the other room, and it's made by my neighbors, Olimex. It uses the A64 board, just like this board, which we'll have a closer look at. And also another really interesting project made with Kicad is a CubeSat. So as you can see, Kicad is something that's free. It's open source. It runs on Linux. It runs on Windows. It runs on Mac OS. And you can design really complex hardware. And speaking about complex hardware, let's have a closer look at Olimex A64 All-Linux Uno board. This is how I've loaded it in Kicad. It has 6 layers. Here you can have a look at the 6 layers and have a look at this density of the traces. This is just only the first layer, and still a very, very complex hardware designed with Kicad. So next time someone says you that there are not sufficient open source tools for designing printed circuit board, think twice, because here is Kicad and it's totally amazing, and you can do really, really complex printed circuit boards. And what about the cases? For me, the cases are the most difficult part, but we have so many open source tools for designing mechanical parts or 3D models, such as Openscad, which I like because it's kind of a programming and making 3D object, QCAD, FreeCAD, LibreCAD, SoulSpace, Blender. Blender is not exactly something that has been originally designed for this, but basically it's for making 3D animations and 3D models. So someone who has skills with Blender, which is a fantastic program, very complicated, but still a fantastic program, can adopt models designed in Blender and, for example, 3D print them. And documentation. The documentation is something that's often underestimated, but in order to have a successful product, you need documentation, and we can split it into 2. Documentation for instructions how to reproduce the hardware. Let's say I have designed this board, and if someone else wants to manufacture this board, here are the steps how to do it. And the other is, if you buy this board or make this board, how to use it, how to use the software for it, and so on. And there's so many open source tools which have been widely used for documenting open source software, which you can adapt and use for open source hardware. Here is a short list of them: Markdown files, LaTeX, even HTML5. You can do an HTML page with the documentation. We have MediaWiki. This is the wiki, basically the engine for Wikipedia. DocuWiki, Wikifactory, Read the Docs. A great tool is Pandoc, which allows you to, from Markdown and other specific languages for describing documentation, to convert it to other, like if you want to from Markdown to go to a PDF, Pandoc is there. And there is even a specification produced in Germany, a DIN spec, defining the standards for documentation of open source hardware. This is something that I recently heard about, but yeah, it exists, and people in Germany are thinking about standard ways how to do documentation. Now, this is the most important part, version control. I have seen so many amazing hardware engineers which are not familiar with the concept about version control, which is a de facto standard in the software world. So you need a good versioning to make a very good difference between versions of the hardware. And we have so many free and open source systems to do it, starting with Git, which is the most popular, and I highly recommend you to go for Git. Mercurial, which is another decentralized, just like Git, system for version control. Subversion, it's getting a bit old, but it's a centralized system for version control. Furthermore, we have so many popular services which are providing version control system as a service. GitHub, GitLab, Bitbucket, SourceForge, and not only Git, some of them are providing services for other open source version control systems as well. And if you, there are free for open source projects, and some of them have additional features for build tracking or documentation, which might be useful for certain projects. This is my first project. It was not on board for Raspberry Pi. After that, I did a lot, but this started in 2017. And Kicad has a steep learning curve. Git also has a steep learning curve. But I'm a developer, so I was familiar with Git. And Kicad was something new. I'm fortunate to have very good neighbors from Olimex here, because they're also having an office in my hometown in Plovdiv, Bulgaria. So they've switched from Eagle to Kicad, and they were kind enough for the local community to make workshops to show us how it works. That's how I started with Kicad, and with help with friends, I made my first board. And once I had it done, it was easy to make new boards. And here are some of the boards that I have created in the years after that. So just as a recommendation, don't be afraid, give it a try. And learning new things is always hard at the beginning, but once you get used to them, things are getting easier and easier. So speaking about open source, community matters. Community is something vital for any product. Keeping the hardware, the software, and the documentation in public repositories allows people to contribute back. And it's mandatory if you're making an open source project. Using popular tools and services such as Git and GitHub or GitLab makes it easier to attract more contributors, because people are already registered in these platforms, and they know how to contribute back. For example, how to make a GitHub pull request. Excellent documentation is always an advantage, because this means that people from the community can understand better what you're doing. And bloggers have the power to spread the word among the community and influence it. So if you're making a new product, contact bloggers. They can help you to reach more people. And people enjoy step-by-step tutorials in YouTube, Instructables, Hackster, Hackaday.io, just because this helps to get started easily. So how to build a community? I'm not an expert in this. I'm just sharing some tips and tricks. The first one is to use de facto industry standard version control system like Git. If you're using SVN, it's very hard to contribute back. So Git is something that I highly recommend you. Services like GitHub, GitLab, submit often. So when you develop open source, you should often submit the changes that you make to your project. And this helps other people to contribute back, to provide feedback. Be respectful and thankful for each contribution, because the contribution most of the time is coming from someone who's interested in your project, likes it, and want to share his experience, his ideas. Beware that hardware is hard. Like software, this is a major difference. It's really hard, because hardware prototyping and low volume manufacturing is expensive. Sourcing components, especially nowadays because of the global chip shortage, is very hard. Often you can't really easily build hardware at home. It's not like software. You download the software, you compile it, and you're ready. With hardware, it's not like this. You need specific tools, you need soldering skills. It takes more time. Debugging requires specific physical tools as well. And if there is a bug, you need to manufacture again the hardware. Often the testing of the hardware could be even dangerous. So yeah, this is a major difference between software and hardware, and we have to adapt the tools that we're using for software in order to use them for hardware and the workflows, but still it's possible to do it. So here are some examples of things that I have done, and I have received suggestions from the community. And here are Git commits, because I'm putting the whole Kicad project in GitHub in a public repository. People are providing feedback, and based on this feedback, I am making improvements. And here is a Git trailer with a description of what has been done and who has suggested it. So with hardware, it's rare that you get a GitHub pull request directly for modifying the Kicad project, but it's quite often that people come with ideas and say, hey, change this and that. And it's very important to give them credit because they're part of the community, credit for this suggestion. And Git trailers are really useful. And this is something that's commonly used in the Linux kernel development, but we can here, as you can see, we can adapt it and use this workflow for making hardware as well. And hardware modifications, yes, from time to time, people fork open source hardware and make their own projects. Here are a couple of examples. I made an infrared auto board in 2017, which I've showed you. A friend needed a relay on it, so he made his own modification. And here is a modification coming from France. I had a light controller for controlling 12-volt RGB LEDs. And this person had some ideas. He liked Kicad, so he made his own, forked the project, and shared it in GitHub as well. So speaking about road to market, because open source hardware is not just about a community. Yeah, community always matters. It's the major thing, but it's also important to have a viable business model because, as I said, making hardware is expensive and you have to cover the costs. Recently, I was involved in the Open Next project, which is a European project, and the Danish Design Center is working on an open source business model toolkit, especially for hardware. You can visit their website, and as far as I know, soon publicly they will be sharing more news about it. There are so many nowadays. There are so many open source hardware friendly marketplaces and crowdfunding platforms like Tindy. Electrons is something new. It's based in Europe, and it handles all the complications that we have here in Europe with value-added taxes and so on. And my personal favorite, CrowdSupply, which is a crowdfunding platform focused on open source hardware. Actually, Tindy and CrowdSupply are part of the sponsors of the Open Source Hardware Summit. So let's wrap it up with some conclusions. First of all, open source hardware is something really important. We should encourage more and more people to use it. The open source hardware certification program by the Open Source Hardware Association helps people and customers easily identify which is really open source open source hardware project. Now there are high quality free and open source software tools for designing open source hardware, such as Kicad. You can also adapt things like Git, and all the tools for the documentation for a hardware project. Established open source software development workflows can be adapted for hardware projects and products. Obviously, you cannot take them directly, but with just a little bit of tweaking, you can adapt and use it. Open source hardware is a viable business model already used by a lot of well-known companies in the industry, and now it's supported by several platforms where individuals or small companies can start making and selling things. And last but not least, actually the most important, that if we're speaking about open source, community always matters. And here are some useful links. I think we have some time for questions, like a couple of minutes.
Yay, thank you so much, Leon. This was such a great resource for everyone. Lots of people on the discourse are clamoring to hope that you share your slides so they can click on everything and check out everything that you mentioned. Obviously, talking about your tool chain is one of everyone's favorite things to discuss on the internet, along with Kicad versus Kicad. But maybe like a question that you could start off with is, given that a lot of open source hardware is about collaboration and community, like you said, which of these tools really support that, the collaborative aspect of it, especially for times when you're collaborating with people you've never met before online? Like what kind of version control works well with that? What are your experiences? Can you share more?
That's easy. For me, it's Git. It's Git. And services like GitHub or GitLab. So this is not an easy question because Git has a steep learning curve. So if you are new to Git, it will take some time to get used to it. It has it looks very complicated at the beginning, but you need to put some time for it, and this is going to pay off in long term because Git is a de facto standard It's very flexible. The decentralized nature of Git allows people from all around the world to contribute, no matter what kind of time zone are they in.
I feel like that's a great way to collaborate on lots of different types of things. But maybe you can also elaborate a bit more on, a bunch of people in the chat have been talking about mechanical design alongside electronics and firmware. And sometimes Git is not the best at dealing with huge binary blobs, which end up being a lot of mechanical design files. So I don't know that there is an answer to this, but any insight that you have into that would be awesome.
Well, binary blobs are always a problem, but like sharing the source code is not exactly a binary blob. So I recommend you to use tools which are more text oriented. This way you don't have the binary blobs, if possible, of course, it's not always possible, but ideally, my personal favorite is Openscad, and I know it's more for educational purposes, and it's my personal favorite just because I'm really bad at mechanical engineering. I'm a software engineer, I like to code. And with Openscad, you just code and the 3D object is visualized. So if we have more tools like this or options to export to more text-friendly files where we can compare, this would be perfect for using Git.
Oh, that's awesome. Well, there's tons of people who are chatting in the Discord. And we're getting ready for a break. I really thank you, Leon, for being available to switch around with Vibehuff, who's going to be speaking after the break. So everybody, while you're having a break, maybe you can drop by the DF Robot channel to discuss some of this stuff, or discuss with Leon in the Open Source Tools channel. The open source robots in DF Robot have like a lot of great tutorials also about using some mechanical design tools. And then after the break, we're going to have Vibehuff Shamra on distributed manufacturing, Helen Little on printing with waste plastic, and Radhakrishna Santa on open source microfluidics. So lots of super exciting stuff. Leon, if you can share your slides in your channel, that would be amazing because lots of people want them. Yeah, and we're having a break. See you all soon. Hi, everyone. We are starting up again, and we're going to talk to Vaibhav Chandra about distributed manufacturing, and just like a few reminders about things that we can do. We have an after party for the summit, which is going to be trivia. And if you're looking for teammates for your trivia team, there is a Trivia Teammate Finder channel on Discord where you can form teams. But not too many knowledgeable people on one team, thank you. I have to win. No, just kidding. So if we have Vaibhav, we'll start our next talk. Thanks all.
Thank you so much. Really sorry for the trouble. I was earlier, but really a pleasure to be here today and to share about the work that we've been doing over here. Okay. So I'm here to talk about a little story. I'm here to talk about Team 90. So just a quick background, we run a makerspace in India called Makers Asylum, which started out back in 2013 out of a small little garage to set up one of India's first community maker spaces. And over the years, initially it began as a space where people used to come together and we used to build stuff. It started in a small garage where about 30 of us used to have the key to it, and we would go use the space, prototype our ideas, and build things. But what started happening is a lot of people started to come to us to also try and use these new tools like 3D printers, etc. So we started working on different programs, various learning programs. Like we have this program called SDG School, where universities also started sending their students for a credit to learn about hands-on learning and making. And by the way, all the projects coming out of them apply for the OSHA certification. So that's also really, really beautiful. And over the years, many projects have been coming together that have all been applying for the, that have been getting the OSHA certification and open sourcing their projects and building this community over here. And then came 2020, the pandemic, and that's why I work as well. So I will go ahead and try and share my screen. Okay, I think my screen share is working. So little story about the pandemic. This is of our past spaces that I was talking about. On the top left, the garage. On the bottom right is our current space here in Goa. By now, moving forward. Sorry about this. Yes, there we go. So when the pandemic came, pretty much shut everything for us, just like every other part of the world. But however, being in space was also quite scary, and at the same time, continue to do what we love doing at Makers Asylum. So all of us decided that we're going to quarantine at Makers Asylum instead of going back home. So we did. Initially, there were about 3 of us, and slowly that number started growing. During this time, huge initial shortage of PPE in India, like many parts of and we did not know this at that time, but we were learning about how big the EU is. So we started a small initiative in India, 10,000 patient laser cutting. We built different models, started with various hospitals and doctors and asked them for their feedback, and were able to quickly come up with a design that worked. And we said, okay, now let's make 10,000 of them. 10,000 was a huge number, thinking of time when all were shut. So that means that finding material was a big issue. Moving places was a big issue. Manpower was an issue. We were just 4 in the lab, remember? Volunteers started flocking, and we had over 20 people inside our lab, living there, making face shields, doing them at the same time. We went through over 21 design iterations, and we saw aha moment when colleague Anul came up trying to make them using foam board, which was revolutionary stationery because stored as every stationery store across the country. When I was talking about the supply chain, so in India, all the trains and the flights and everything were shut. So the only thing we could use to move these face shields from the lab to the other places were ambulances or police cars. But that was also very, very limited. So how do you move more in a pandemic? And that's when the thought of open source once again prevailed. We open sourced the designs, started making videos, sharing them with every part of the country to start making them using local materials for their local hospitals. And we started joining the dots. So we started connecting hospitals, foundations to local makerspaces, and then sharing the designs and everything they needed to be able to make those locally for their use case. And very, very soon, over 42 cities, towns, and villages joined the force. And everyone from BBC News to all the Indian news channels started talking about this initiative. And pretty much in every part of India now, we had a lab that was active. And we ended up making over 1 million face shields in a matter of 49 days. Now, just to put that into perspective, 1 million in the time of the pandemic, from the first day of the lockdown, it took us 15 days to make the first 100,000 face shields. But then things changed pretty quickly. We were able to make the next 100,000 face shields within 7 days. And then eventually, as you can see, we were making 100,000 face shields a day. And the way this was happening is that over here, you can see the graph where the yellow line is Maker's Asylum, which was consistent and just holding the fort. But more labs were joining the force, and some of them were even faster than us. Some of them were using different technologies, and that really helped to increase the collective intelligence of this group. So we were not only just sharing, but we were also learning from the other labs, and together we were making them faster. And I think that's the true power of open source and distributed manufacturing at work. And very soon, everyone from the police personnel to the doctors across the country were all wearing our face shields. It was a completely interdisciplinary group, anywhere from chefs to doctors to musicians to filmmakers to engineers were all part of the collective. The youngest member of the M19 initiative was only 12 years old, and he made over 344 face shields with his family in Gujarat. This went on to become a very exciting case study on frugal innovation by the University of Cambridge and, of course, OSMS. And we did a lot of different use cases of these face shields. We went on to make superhero face shields for teenagers. We made baby face shields for newborns. We made active respirators with the open source community, along with AIIMS Hospital in Delhi. We made rebreather masks for senior citizens so they could breathe easily while wearing the mask. But while all of this was happening in India, Open Source Medical Supplies did a survey and a study, and 48.3 million units of medical devices, supplies were created by the maker movement across the world. So while we were thinking about this in India, every other maker community was thinking in a similar manner. And that was what was so beautiful about this open source and collective distributed network of labs and maker spaces. However, there was a problem. There was a problem of quality assurance and quality checks. And a lot of labs and a lot of maker spaces were not able to make the same quality as one or the other. And that still exists in distributed manufacturing. And while we were answering that question came wave two. Wave two was very crazy in India. During the second wave in India, we had a huge oxygen crisis. And that's when we looked at oxygen concentrators, thanks to, again, the open source global community. We studied all the existing designs from the Marut design to the Apollo design and learned a lot about them. But however, we realized that none of them were manufacturing ready or certified. So we immediately got to work once again in Goa at Maker's Asylum and started building them under the leadership of Anul. And very quickly, we were able to not only just prototype multiple versions of the oxygen concentrator, but we were able to solve a lot of the issues that were coming with oxygen concentrators in India, especially related to humidity, related to power cuts, related to electronics. And we were able to create the M1902, which you can see on the rightmost part of the screen. This is now also certified. While building this, one of the key focus that we were trying to address as part of this was how do you scale this in the distributed open manner? And over 30 organizations were able to take this and also go into production with these designs. This was also a big shout out and big thanks to, once again, the Cambridge University that has this center of distributed manufacturing that really helped us do this study around how do you scale an open source device or any device rather in a distributed manner, but at the same time, maintaining quality checks and quality assurances. And we're still building on this, trying to create a very exciting, simple framework for more people to use this and to be able to scale their ideas. That's the M1902 once again. One more thing that happened during the M19 initiative or while we were building these oxygen concentrators was that approximately 300,000 concentrators were also imported to India. But once again, a lot of them started breaking. And this is something that is very common. A lot of medical devices, when they're imported from a different part of the world to a different part of the world, they necessarily don't work so smoothly. And that's when a lot of doctors started reaching out to us to try and help fix them. So we once again used the same exact network of the M19 collective, this decentralized network that was working on the open source oxygen concentrators to host repair camps and try and fix the ones that were broken. Very quickly, within just 2 camps, we were able to service about 30 oxygen concentrators. And that's 30 less gone into the landfill, right? So that was what was beautiful about it. Currently, we're still doing more research around creating this decentralized network of not just building devices, but also repairing and reusing them, while we continue to teach and learn through our program at Makers Asylum and encourage all our students to also build and share via the open source ecosystems. Thank you very much. That's about it from my side. I'm happy to take questions if we have the time.
Thank you so much, Vaibhav. That's amazing. We thought 10,000 was a lot, but apparently 10,000 is not a lot. Incredible scaling. So a question for you. How did makerspaces get cooperation with local authorities for resources such as ambulances or for transit?
So what happened over here with us in Mumbai was when we were in Mumbai, very quickly people started to notice the work that we were doing, and we were able to get in touch with the ministry and also the police. So once we got the permission, we were able to share that further with the other makerspaces as well and send them a letter which sort of helped get them the basic support that, you know, these guys are working with this foundation. They already have support of the Mumbai police. So please share the same to them, and sort of escalated and really got the community rolling at that time.
Amazing. Yeah, so it seems like you really had a snowball effect going on there. What's currently happening with all of these efforts?
So, like I said, currently what we're trying to do at the moment is look at the repair and reuse side of things. So while the, and also actually the second thing that we're trying to look at is the power, because as you just saw what happened to me over here, we lost power in India, and I was not able to join the call on time. Similarly, there are a lot of power cuts that happen over here in different parts of the country, apart from the major cities. So one of the things that we're trying to address with the M1902 as part of the collective is on alternative power sources for the oxygen concentrators. That's one. The other thing we're doing is reuse ecosystems, that how we can actually fuel that and continue to share that knowledge so that people can repair, reuse in a sustainable manner across the country.
Yeah, awesome. Yeah, repair and reuse is such an important part of all of this. Another question for you. Can you like talk about what you think the limits are for community manufacturing? You know, are there limits? And if so, what are the bottom and top bounds for those limits?
So one of the things that we realized, which we're still trying to build upon, is the quality assurance and quality check parts that I talked about. That definitely is a limiting factor, because what happens is that, let's say if Maker's Asylum in Mumbai got certification for the oxygen concentrator, that same thing does not follow to all the other labs. The certification does not follow. However, we can maintain certain checks on our own to be able to make sure that they all get the certification as well. But there is that limit that makes it so that you need to be able to create in a certain amount to be able to validate or make sure it's worth it as well at the end of the day. So that's one, I would say. On the other side, I would think that the different kinds of materials that are available in different cities also creates a little bit of fluctuation in the way that things work. However, that can be solved through creation of a platform that allows us to use similar materials to be able to apply for the same certification. And that's what we're trying to do right now.
Oh, cool. Interesting. I think that it relates to maybe a follow-up question, which is about quality control. For distributed manufacturing, it seems like a big part of it is like the big differences that there are with quality control when you have so many different community members participating. And so do you have like maybe some really insightful takeaways you can share? Like how do you communicate quality control to all of these different people in the community? What are ways in which you like can draw them together? Talk to us about this extremely exciting topic, quality control.
Quality control. Yeah, it is definitely a very exciting topic. So what happened during the face shield part was that when we were building them, obviously this was like an extreme crisis situation. And the point was to be able to make as many as possible super fast, but also remember quality. During this time, what we were doing to communicate was like day and night calls, trying to make sure that everyone's on the same page, but that doesn't work really well. So what we're trying to do now, and what the University of Cambridge is trying to help us out with, is building a simple app that requires each of the labs to take photographs through the different processes to be able to check that. Similar to actually what happens with a lot of apps, for example, there is Urban Clap in India, which I don't know the different names of ones outside, which requires like certain quality checks to be maintained using photograph and upload and say that yes, this matches the certain check. If not, if you use something else, then you have to basically call or reach out to one of the validating labs or hubs to say that I've made this change, what do I need to change? So again, using GitHub, using other ways to be able to poke back and ask the different labs to be able to say that, yes, I've made these changes. Is this okay? So I can proceed.
Oh, cool. So it's kind of like a way in which you can create a platform for everyone to communicate with each other and kind of evolve what the expectations are, taking photos as a way to communicate along the way. That's awesome. So
that's one part, but
yeah.
Like there is not always one proper thought. It's an evolving
I thought
community.
everybody that was speaking at the Open Source Hardware Summit was going to have solved everything that we had in the world, all these problems.
We're all learning as we go along. That's the beautiful part about this community, right?
Yeah, totally. Yeah, so how did you get other people involved in the community? So as you grew, how did people find out about you? Like, what were ways in which you did community organizing and engage people?
Okay, so this is slightly embarrassing, but we used to make daily update videos, and we used to bang tables and make really fun daily update videos that were talking about what is the number for the day, how many face shields did we make today, what are the other labs that joined the force, what exactly happened. At that time, it was really effective. It was bringing more and more people every day. Literally, initially one lab was joining. Eventually, there were 10 to 15 labs a day joining. So it was like a snowballing effect, like you talk about. But at the same time, those videos really helped because it helped invite other people into the community, and they also felt like they were part of this. And just as a single lab, like our numbers maybe were like in the beginning 1,000 or 2,000 face shields a day. But when you joined all the numbers together, then it started sounding really big, because we were going from not just making a few thousand face shields at Makers Asylum, but as a collective, we were making almost like I said, towards the end, 100,000 face shields a day. So
yeah, exponential scaling will surprise us every time.
Right. So that really helped like create momentum in sort of the labs joining and wanting to be a part of it.
That's incredible. Well, this has been an incredible project. There's lots of people who have questions for you, especially if like you can share your link slide, maybe in the Discord channel, the community-led distributed manufacturing Discord channel, to continue the talk. Next up, we're going to have Helen Little. Helen Little is going to talk to us about another big problem of plastic waste and printing with recycled plastics. Great to have you, Helen, and take it away.
Hello, thank you for that introduction. Let me share my screen. Let's see, I'll just do that entire screen. All right. All right, hopefully everyone can see my screen. So hello everyone, my name is Helen Little and I'm from a company called Re3D, and I'm here to talk about a 3D printing material testing procedure. So looking at an overview of what I'm going to talk about today, I'm going to go through the background motivation behind creating this material testing procedure, and then I will go into depth about what the procedure entails. So how to test extrusion, how to test optimizing for different print geometries, how to test for material properties, and then finally all the documentation resources about this whole procedure that exists. So first, background motivation. What's the point of having a 3D printing material testing procedure? So I work at Re3D, and it's a full service 3D printer startup. We manufacture large format industrial 3D printers at an accessible cost. So you can see this person on the right side here is to scale to our 3D printers. So when I mean big, I mean big. And really our ethos is to enable people to have access to manufacturing at scale using additive manufacturing. So we have a ton of different 3D printers that do that. But another part of our company that's really important to us is the sustainability aspect of additive manufacturing. So we asked ourselves, what does it look like if you took plastic trash and put it into a granulator or a shredder to chop it up into little pieces, and then take those pieces and feed them directly into a 3D printer without having to transform it into filament or anything like that. And then you can 3D print a product out of those granules, and then a customer can use that product, and once the product reaches the end of its life cycle, then it goes back into the trash and re-enters this infinite loop to create this circular economy. And so that is what brought us to pellet 3D printing. So on the left here, I have a picture of some 3D printer filament, and typically filament is about 10 times more expensive than plastic pellets. That's because of the added costs of manufacturing the plastic into that filament. So it's a lot cheaper to use pellets instead. But if you go even further, what if you can print directly from trash, which is potentially free or even has a negative cost associated with it, depending on maybe there's costs associated with storing that plastic. And this is really important especially as you increase the size of whatever you're 3D printing, because the larger the object is, the more the material costs matter. So this is also like an economic scalability issue, and not just a sustainability one. And that led us to make our 3D printer, which is a pellet 3D printer. The framework is very similar to the filament 3D printers we make, but the really key part here is that the extruder is different. It can accept pellets and flakes and regrind and different little particles and then extrude out. And then beyond the extruder, it acts a lot more like your typical Cartesian 3D printer. However, there are challenges when it comes to material testing. Some of y'all may have tested filament in the past, and usually filament it's designed for 3D printing. Usually the manufacturer has tested it, they put additives in it to make it work well for 3D printing. So sometimes there's some testing involved, but it's usually not as much as pellets. So pellets are often designed for other manufacturing methods, such as injection molding, and they're not tested in a 3D printing system. So, it's a little bit, there's a lot of things that need to be optimized if you try to print with a new material. And then when it comes to trying to print with plastic regrind waste, it's the Wild West, right? Like that plastic can have all sorts of different types of plastics in it. It might have contaminants. It might have all sorts of different unknown properties that need to be figured out in order to actually 3D print with it. But, if we can't figure this out, it would be really amazing, because there are a ton of cool applications that we could use this 3D printing for. So I have just a few here. This is definitely not an exclusive list. So things like utility solutions, fixtures and jigs, architecture and furniture, education, and then prototyping for product launches. So there's a whole host of industries and applications that we can apply this to, and they all have different needs, which means that conceivably there are countless materials that it would be really useful if we could figure out how to 3D print with them at scale. And this is real. At Re3D, we've been testing dozens of materials, and through that testing have been able to establish print settings and improve our hardware in order to actually 3D print with these materials and make these really cool objects. So when you try to 3D print something, there are a lot of things that are happening simultaneously that can affect the success of the print. So the first thing is your material properties. So what material are you printing with? What are its melting temperatures, viscosities? What is the physical form of it? Is it like a cylindrical pellet? Is it spherical? Is it an irregularly shaped flake? That can all have an impact on printing. And then we have the hardware. So what are the specifications for the extruder? What are the dimensions for the extruder? What are the sort of ancillary features, such as like, do you have a heated bed? Do you have part cooling? All these things on the hardware side can affect the success of your final print. And then there's also the slicer settings. So these are settings such as the temperatures that you set, print speed, print resolution. There are a whole host of different settings that can be optimized in this realm to ensure a successful print. And then finally, you have part geometry. So that can have a huge effect on how successful your print is. The geometry can be designed for specific types of 3D printing or for use with specific materials, depending on the needs. So all of these are happening at the same time when you try to 3D print something. So if something goes wrong in the testing, it is oftentimes difficult to pinpoint what aspect among these host of factors is actually causing that. And odds are it's probably a combination of multiple factors, which brings us to the challenge. How do you solve a complex multivariable problem such as material testing a new material for 3D printing? And the solution that we've come up with after, I don't even know how many hours of material testing, dozens of materials, is we've created a procedure that isolates the variables in a systematic order to optimize all the factors at play. Which brings us to our material testing procedure. So this is really high level, breaking it down into the different sections. And the idea here is First, subjecting the material to the most basic of tests and making sure that the most basic needs are optimized and confirmed before gradually subjecting it to more complicated and demanding demands from the material. So first, we start with extrusion. Can the material even extrude out of the extruder? Then once we've established we have good extrusion, we move on to print optimization. So what kind of print geometries can we actually achieve with this material? And then once that is optimized, we can move on to material properties. So this is more for industrial applications of getting information on tensile strength and those kind of things to determine and quantify exactly like what the properties of your final print are. So launching into the actual procedure, we start with extrusion testing. So how do we test if a material can actually extrude? The very first thing we do is we dehydrate the material. Most polymers many polymers are hygroscopic, so they absorb water from the air. And if you try to print with wet plastic, it causes all of these print quality issues. And that's really difficult to try to troubleshoot other issues with the print if you're having to contend with issues because the material wasn't dehydrated properly. So I have some examples here of for a low fidelity drying solution, you can use a hot air food dehydrator from Walmart or something, or you can go the more industrial route with a desiccant dehydrator. And then if you want to be really rigorous, you can have a moisture analyzer that can analyze the exact moisture content of your sample. So this is the very first thing you do. It helps make sure that you're starting like at a good place with your dried material. The next test we do is we conduct particle analysis. We use an open source software called ImageJ that is free to download. And what this software enables you to do is to take a picture of your particle sample, and the software will count the area of your particles and give you particle size and shape data. So this is super useful to really quantify your particle sample. And this graph here shows how we used ImageJ to compare different processing methods on rPET flake and how that affected the size of the particles. It also serves as a great way to identify, oh, maybe these particle sizes are way too large to print with, or there's too many large particles, or there are too many small ones. So once we've established that, we can actually put the material in the extruder and try to extrude. So this is when we establish the initial temperatures for the material to extrude. So if it's too cold, the material is not going to extrude out. If it's too hot, the material will have too low of a viscosity and it will ooze out of the extruder. So this is just establish initial temperatures so that we can actually have some material extruding. The next test we do is testing for extrusion consistency. So that is referring to if you keep all the variables constant, can you ensure that you have a consistent amount of material that comes out of the extruder? Because if it's not consistent, that means that you will have it won't be reliable for your printing. You may have holes in your print, or it may be over extruded in some areas. And if you have inconsistent extrusion, that can indicate a whole host of issues, such as maybe it has issues with feeding, or your nozzle is clogged, or there are contaminants in the sample, or maybe your temperatures need a little bit more optimization, like they're too low or they're too high and you're having material bridging. And the way that we check extrusion consistency is like really quick and dirty. We basically extrude a certain amount of material for 5 trials, and then we mass the extrudate, and then from that calculate the standard deviation of that mass. And so this will really identify like huge changes in extrusion consistency, because ideally, if you extrude 5 times, each time you should extrude the same amount, right? So this is a really helpful thing to check. Another thing that we test for is the maximum extrusion rate. So this is how much material an extruder can push out within a given amount of time. And this is a super helpful metric to talk to customers and end users about, because usually people ask, how long does it take to print this object? Well, if we have a maximum extrusion rate, then they can say, oh, since this object is 5 kilograms, then if the extruder runs at 1 kilogram per hour, then at the minimum, it will take 5 hours to print our part. So it gives you like a nice rough estimate. And the way that we calculate the maximum extrusion rate is we first determine the maximum extrusion speed by basically increasing the speed until it can't extrude that fast anymore. And then we do the same thing with extruding a certain amount of material and then taking the mass. And then once you have the mass, you can just divide it by the amount of time it took to extrude, and that will tell you the extrusion rate. And we have like a spreadsheet calculator where all these formulas are already input, and it's just a matter of putting in the data and it automatically calculates for you. So if a material succeeds in extrusion testing, then we can move on to actually trying to print some geometries with it. And the idea here is to start with the simplest geometries first, and then slowly work up to more and more complicated geometries. So the first geometry we start with is a calibration cylinder. So it's a cylinder with 2 bottom layers and then a single perimeter outline. So it's hollow, and then there's no top layers. And what this tests is bed adhesion because you have some bottom layers. And it's also really good for testing extrusion rate and calibrating that, because you can take a pair of calipers and measure the layer width of that wall. And if it's lower than expected, that means you're under extruding. If it's higher than expected, then it's over extruding, and you can account for that in the slicer settings to really dial in that number. And it's also helpful for further optimizing the extruder temperatures, because the temperature range at which you can extrude is usually larger than the temperature at range that's ideal for printing. So maybe it extrudes fine at a certain temperature, but when you actually try to print something, it's a little bit too hot or too cold, and it causes issues with the print. So once the calibration cylinder is established, we move on to our next test print, which is our MOI. And this is basically like our standard print that we use across different materials so that we can compare the behavior of different materials against each other. This is just what Re3D uses. I know a lot of people tend to like to use the Benchy, so that's another good option. But basically, like having a standard thing that you can use across multiple materials so that you can actually compare them is really helpful. And then the other option I want to share about is the NIST test artifact. This is an open source geometry that is available for free download on the NIST website. And it essentially has a ton of features on it that will test certain things about your printer. So it has small features. It can test bridging, stair stepping, stringing, and hole geometry. And this is really useful if you're trying to do an application with high resolution and more complex geometries. So once you actually have some print settings and geometries tested, then we move on to material properties. So we have an ADMET universal testing machine, and what we'll do is we will 3D print these tensile bars according to the ASTM D638 standard, and then we can load those tensile bars into the machine, and the machine will pull them apart and get data on the elongation and the tensile strength. And so this is really helpful to get quantitative data on how strong your prints are, or maybe how flexible your prints are. And this is really useful for a like more industrial, more rigorous applications. And finally, documentation. So this won't be open source unless there is documentation on it that is open source and available to refer to. So Re3D, we have a knowledge base that is essentially like our wiki. And on there, you will find a material testing procedure all written out, basically outlining what I talked about. And we also have a ton of supporting documentation in the form of knowledge base articles that will help with troubleshooting any part of the material testing procedure. So let's say you're going through the material testing procedure and your material is not adhering to the bed. Well, we have an article on that will basically tell you these are all the things that can cause poor bed adhesion, and these are the things that you can do to try to address that. And the link is at the bottom there if anyone's interested. I also, every single month, will write up my R&D updates from the month and post them on our forum on our website. And that includes if I ever do any kind of material testing in-house. So I'll write up all the results of that, all the settings I did, all the different tests that I had to do, and put them on the knowledge base. So or in the forum, sorry. And so if you really want to deep dive into that, that is also another really great resource to refer to.
Awesome. Great. Next up, we're going to have Radhakrishna Sanka on open source microfluidics. If you were worried that earlier Leon didn't cover CAD tools for microfluidics design, fret not, because we're going to learn about the humorously named Fluigi CAD. Thank you, Krishna.
Hi, everyone. Yeah. So Fluigi is like a play on Luigi, and my advisor was a big fan of Mario, so that's how it ended up. But today I'm here to talk about like the entire open source CAD ecosystem that I've been building throughout my PhD, and I'm really excited to like talk to everyone about this. So just to give you some background about me. So I started doing some electronics in my undergrad, like, analog, digital, name it. Then I went out once I graduated, built some cool electronics and software systems for some space-related applications. Then I came back from the master's to Boston University, tried doing more electronics, got bored, ended up doing some photonics stuff, and then finally ended up doing my PhD in a synthetic biology lab. And instead of doing anything in biology, I started doing work in like microfluidics and how to engineer them much easier. Now, for those of you all who don't know anything about microfluidics, it's fairly simple, as just its picture says. They're basically small plastic devices where you can insert tiny volumes of fluid into it. And, these devices can manipulate and sense those fluids, and that's essentially one of microfluidic devices. Now, if you're thinking about where you use them, everything ranging from your glucose sensors, if we ever manage to miniaturize our COVID testing, PCR microarrays, and if you've seen these things in like the Smithsonian or magazines, wearable devices, which can be used to like monitor what hormones levels you have, like what your blood pressure is looking like, all kinds of crazy stuff. So, and that's what microfluidics are, like in diagnostics. But you might be wondering, why is Krishna, like in a synthetic biology lab? Why do they care about microfluidics? Well, we think of microfluidics as a lab on a chip because you can basically do all the operations on a chip. Now, in the 3 videos you see on the right, imagine each one of those droplets to be a biological sample. And these videos are like slowed down by about like 200 times, which means that by the time you blink an eye,
your slides, I think you're sharing not the screen that shows the slides. We just see the overview. Maybe you could switch back or share the presentation part of the screen.
Oh, shoot. So sorry.
Yeah, no worries.
Screen. I'm gonna share the entire window. That way it'll probably just work. Can you see the screen?
Perfect. Awesome. Thanks so much.
Yeah. So why do I care about microfluidics? It's because we think of microfluidics to be like a lab on a chip. Now, if you see the 3 videos on the right, you'll actually kind of see. You'll actually imagine each one of these droplets to be like a single biological sample that you're experimenting. Oops, sorry, got canceled. Imagine each one of these droplets to be like a single biological experiment you're trying to test. And that means within the blink of an eye, you can actually run about like 1,000 tests. And this is something that is unheard of in the field of doing any kind of biological engineering. And if some of you are biohackers in the room, you might be remembering all those nights you were pipetting small volumes of fluid from one well to another. And that's the hope. We want to accelerate how fast you do this. Now, microfluidics have been around for like the last, 30, 35 years. So you'd imagine every, pharmaceutical biology lab to look something like this, huge data centers where you're just generating more and more biological data. But, the reality is kind of looks like this, with the hodgepodge of lab equipment. You see a microwave there. I'm not even sure what they use a microwave for, to tell the truth. But the reason why this didn't really happen was because creating microfluidics is a multidisciplinary process. Most people who make these devices have a PhD in something. and spend their entire PhD or spend a lot of time learning how to do these devices. And the second part is that there's a fractured supply chain. It's not easy to make these devices between all the different kind of materials you need to have. And so, if you didn't have like $1 billion, like me, I didn't have $1 billion, you were like, how do we fix this problem? The answers are, for me, was let's build design automation tools that'll get rid of like this multidisciplinary expertise requirement, because I didn't have any. So I needed to figure out a way to make this easier for myself. And the second part was, let's make this open source and maker friendly, because that way it's easier to source more components. We can easily make devices, and everybody else can replicate making these devices. And so what we basically needed was this entire open ecosystem for making this stuff. And so the first problem was, making this stuff hardware, maker-friendly hardware, right? And the big problem was standardize this entire hardware design. Now, the thing is that in microfluidics, it's rapidly evolving. Based on what applications you use, what manufacturing technique you have, between industry and academia, you have the most favorite manufacturing method every 6 months. And that was becoming a problem, because in my lab, we were saying, oh, let's get rid of all this expensive equipment and let's use something as simple as a CNC mill and duct tape to actually start making like microfluidic devices. And I was like, okay, I really need to get my A game up, because nothing is constant in this field. So what I basically went around and did was, okay, let's rethink how we draw these devices, right? So rather than using like SolidWorks and making these designs, I basically said, let's think of this entire design to be like components and connections and layers, just like how we have in electronics. And then what I said was, because each and every one of these components will have a specific manufacturing protocol, we can basically track which manufacturing method is manufacturable by. And that way we were able to like make sure that you could create a design and ensure that it's manufactured by a specific technique, or whether it's laser cutting or CNC milling, or like some kind of photolithography method. And so with that, we took all of this information, and then what I did was we created this tool called 3DUF, which is an open source interactive design tool, which is available online right now, to actually go ahead and create designs. And it basically captures all the manufacturing protocols which are related to each one of these components, and made like a DIY place and connect kind of a tool, which even like high schoolers can use to make microfluidic device designs. Now, what this design, which over here would have taken like a couple of hours to make in like, SolidWorks or AutoCAD, took me around 20 minutes to actually do, with all the mistakes happening and me making changes midway. So with this entire tool, you'd be like, okay, this is cute, it is open source, but did we actually make anything useful with it? Well, useful is a hard thing to beat, but we made some really cool applications. Like in 2017, some of my undergrads started working on this project called Mars, where they wanted to make small lab automation microfluidics to automate the protocols which you do in synthetic biology. And more recently, some of my undergrads who are working on this right now are making this super portable mRNA encapsulation device, which in principle would make mRNA encapsulation possible anywhere in the world. So you could actually do distributed biomanufacturing. Now, the second part of this was I needed to eliminate this expert training business, right? Like, I didn't have like 3 degrees in material sciences and everything. I kind of knew ins and outs of different stuff, but, I was no expert. So I was like, okay, what are the tools we need to create this entire ecosystem? Now, this picture, which I showed you initially for like, okay, here's a microfluidic device, a simple device where you can put tiny volumes of fluids and manipulate stuff around. Now, the thing was, I was kind of cheating over here, because in reality, for every picture that looks like this, you have this entire chaos of a setup that actually makes that one tiny chip go. And so if you actually had a design center like this, 90% of this would be filled with like pumps and instruments for actually doing measurements and actuation, rather than the actual biology itself. And so people in academia were like, can we take any ideas from like the semiconductor world and really, really integrate all this stuff into like a single device? And they did a pretty good job. So over the last, 15 years or so, people have been like outdoing themselves to make better and better devices from like the year 2002 itself, I guess. So they made all these devices, but the issue was, like all of these were like one and done. They never made a second version of these devices. So now the big question was, and if you wanted to use a tool like 3Duff to create them, good luck. I wouldn't want to do it, and it's my tool, right? So we were like, is there an easier way to actually design these devices? So we looked at electronics, right? And as you all already know, I'm basically an electronics guy trying to tell microfluidics engineers how to do stuff. So I was like, okay, if I wanted to create a new electronic IC, I would use something like Verilog, a high-level description language. It'll compile down to like the actual gates of what needs to get done. And then, I make an ISIC out of it, or I put it in an FPGA, and I'm done, and I'm done and happy. So my advisor was like, okay, maybe we can describe how, like liquids interact. Sorry, that's a super bad impersonation. I'm not good at these things. But that basically became the genesis of this design language called LFR, which I worked on throughout my towards the end of my PhD, which is my thesis, to figure out a way to like actually describe these microfluidic designs. And so what I basically did was I kind of copied Verilog and took out all the electronics pieces and put in like all the microfluidics related keywords. And basically now I had like a design language for describing microfluidics. And not only could I just, put in all the different microfluidic related terminology, I could also reuse some of the ideas from Verilog for like describing, operations, describing complex logic for, in our cases, for like how we distribute fluids and how we valve things in and out. I could also, eventually describe super complex logic devices in microfluidics, which, were also one and done devices and which nobody ever wants to recreate again by manually. So now with this entire ecosystem of, this design language, compilers and everything in there, using the manufacturing library in 3Duff, I created this other tool called Neptune, where we could basically, a cloud-based IDE, so that for folks who are not super savvy, which are like the microfluidics engineers or the biologists doing this, could quickly go in, create a description in LFR, and compile the final design outputs. So now what I have is that if you have an idea for creating microfluidic devices, you can use one of my design tools, whether it's Neptune or 3Duff. Then that in turn would use like different languages involved, different algorithms that we've been building to generate like the final designs and CAD files, which you need for actually manufacturing these devices. And you have like a microfluidic device on hand. Now, the best part about all of this is that because everything is open source, if you're like a microfluidics engineer, you come up with a new kind of component design, new way of characterizing it. You can basically plug in all your data. You can plug in all your logic into the design tool chain. And if you were an algorithm designer, you could actually extend the language to actually do more computational design automation kind of work. And that was one of the big things in the academic space, because there were like 20 groups doing different things. Nobody was actually integrating anything together. So we would always start from like square one every single time. But the real question for me, and the real reason, is that even though we could do all this lab automation, that's what's required in my PhD, these are the kind of stories which really made me want to do this, like why I spent so much time building this stack. So in this picture is Karpai village, from a place where I was kind of volunteering with this organization, health center in this village. Now, in this area, like there's one doctor for about 5,000 patients. And 90% of this population, tribal population over here, has malaria. And everybody is below the poverty line. So one of the big questions that they were facing was, like, is the malaria parasite getting drug resistant? And the problem was that how can we actually test this? Because, it wasn't easy for them. These are just doctors in like low resource clinical settings, right? And so, like me being in Boston, in the mecca of biotech, this seemed like pretty simple question to answer. 15 minutes later, I realized that two people using some of the tech from a guy working across the street and some other paper, we could actually create like an integrated device with a bunch of engineering could eventually do this test. But the thing is that this device is never going to happen because for most researchers, including me, this problem is so alien and so not in our in path for our funding, we would never actually work on it. For startups, the saviors of the world, this is not going to be a lucrative exit, so they won't work on it. And for the community, the doctors over there, maybe the biohackers in the area, they would probably be confused about how to even go about making these kinds of devices. And so that's kind of where, I started putting together this small community called Distributed Diagnostics that would, create like use all the free CAD tools, put together all the DIY manufacturing techniques we've been doing in our lab, and create a community that has some tools to actually start solving problems which they're interested in. And that, that's about it. But I'm happy to answer any questions if you have any time. I unfortunately can't see how much time is left here.
We actually have a few minutes maybe to discuss some stuff. So maybe you could give us a first, just for people who've never used microfluidics before, and maybe aren't ready to start designing their own devices, what's like a great place for them to get started?
Yeah, so some of my undergrads, the ones who worked on like the design automation kind of a thing for synthetic biology, they put together this great wiki with like videos, resources. Those videos were so good. I was like, oh my God, you guys spent so much time on these things. But that's a great place to start. And I have a lot of long tutorials. You actually just have to bear with me talking over like how to design microfluidics.
What is the URL for that wiki? Is it distributeddiagnostics.org?
No, I'll be putting that wiki link right now.
Oh, awesome. Thank you.
Yeah.
You can also follow up after in the Discord. Everybody has questions.
Yeah. So I put it in the studio link over there.
Yeah, I'll post it. Awesome. Yeah, and so, sorry, I interrupted you.
Yeah, and I think that's a great place to start. I also have a lot of tutorials around this. I'll be putting up more URLs for like all the detailed tutorials on how to extend.
Right, maybe even at like a higher level. Can you explain for someone who like really doesn't know, like what even are microfluidics for? Why is this useful?
Yeah, so think of it this way, right? Like if you're doing any kind of biology or chemistry research, the fundamental thing that you do is you need to mix a couple of fluids together, or you need to manipulate some fluids. And so what microfluidics kind of do is they allow you to automate that whole process, because let's say if you gave me a pipette, none of my friends who are like actual biologists would trust me to even pipette the right volume. But if it's a device, they'd be like, you know what, the device will take care of making sure there's the right volume that's mixing, it's mixing at the right ratio. And
so what you're saying is if you wanted to do a lot of diagnostic tests with just one drop of blood, you could do it this way?
So, that's how, this is what Theranos said they would do, but Theranos with Theranos. But yeah, but that's basically what we're trying to do, right? We want to make biology research more reproducible. And that's kind of why we want to do microfluidics, because, the dirty little secret is that most biology research is not reproducible. And when you're doing synthetic biology, it's so hard to engineer those systems that you need to make sure that every protocol is captured to the dot and, nothing actually changes. So having those really precise reproducible conditions is important. And the second thing is because microfluidics actually use like micro and nanoliters of volume, it means that like the reagent cost is going to be a lot lesser. Like, for example, some reagents which we buy are like $500 for like 10 ml. And so if you use nanoliters of it to do the same experiment, one, you have better sensitivity. Two, you have cost savings, and you could use the 10 ml for like the next 6 months rather than for like a week.
Cool. That's awesome. Yeah, I feel like there are a lot of people who are engaged in open source hardware from the electronics part, and maybe some who are engaged from mechanical design, but bio and laboratory testing kinds of things are really maybe something that a lot of people are recently wanting to get into. So I think a lot of people are super excited about any links or resources that you can share about the kind of work that you do.
No, definitely. Feel free to hit me up on the Discord. I work with a lot of like community biolabs in the Boston area, Bay Area, and stuff. So it'll be exciting to just talk to more people and connect with them. And we're always looking for open source contributors. We have so much work and not enough people to do them. So
Amazing. Yeah, maybe you have some community biolabs that you want to give a shout out to right now.
So I've been recently talking to Braid Theory folks, and there's Boss Lab in the Boston area, then Counterculture Labs, and I'm so blanking out on all the names I know right now.
Here in Seattle, Sound
Yeah,
Bio.
exactly. There's so many folks around here, and they're all so exciting, like to work with. There's a question for, are there non-health or human applications for microfluidics? There are some environmental applications. We had one person come into the distributed diagnostics board who wanted to like check different environmental applications. Like, for example, monitoring to see, if there are like heavy metals in the environment, or also like separating out different types of, different types of fungi and bacteria in the particular ecosphere. So there are all kinds of crazy things you can do. Think of it this way. If there's something you want to do with fluids, like some kind of a liquid, and you want to automate it, microfluidics is one potential way of doing it.
Cool, cool. Well, this has been really great. Thank you so much. And with we're going to move on to the break. We have like a while for break now, so if you want to grab breakfast, lunch, dinner, midnight snack, depending where you are in the world, and when you come back in about 40-ish minutes, we'll have amazing talks on open source hardware public policy, modular open source hardware laptops, the Open Hardware Observatory, and equity-driven design. And while you have nothing to watch in the break, we encourage you to maybe hang out in any of the Discord channels, find your teammates on the Twitch trivia for the Twitch trivia after party. There's a voice chat if you want to hang out in voice chat. And we also have, for example, if you wanted to check out Leon's Tindy store, it's in the Supply Frame Hackaday Tindy channel, open source robots at DF Robot. Yeah, enjoy your break, and we'll see you shortly. Hello everyone, welcome back from the break. Just to be clear, we're starting now, and for the next 2 hours, we're gonna have some back-to-back amazing talks. And we're gonna start with open hardware for science with Allison. We're also gonna have modular open source hardware laptops, the Open Hardware Observatory, equity-driven design. So for the next 2-ish hours, we will be here and we're sticking to the schedule that's online. So when in doubt, check the schedule that's on the site. So I'm really excited for Allison Parker's talk and for the insights that she's going to share with us about open science hardware.
Great, thanks, Nadia. All right. Hello, thanks for having me. I'm excited to be here. I'm Allison Parker. I'm a senior program associate with the Science and Technology Innovation Program at the Wilson Center, the Woodrow Wilson International Center for Scholars, which is a think tank and a nonpartisan policy forum. We tackle global issues through research and dialogue. And as a partially federal institution, we sort of see ourselves as a bridge between academic communities, community-based communities, and public policy communities, in particular the federal government in the US, especially being situated here in Washington, DC. We are tackling now in a project that we're calling Think Tank, that's funded by the Sloan Foundation. We're tackling how the things of science, the hardware, the physical tools that generate data or contribute to scientific processes, how they're accelerating and broadening science. And so we're looking at these questions in particular, taking sort of a landscape view of what's happening in low cost and open source hardware for science. So a lot of what I'll talk about today will touch on both sort of low cost tools as well as open source tools, but we also try to sort of emphasize the particular value of open source. And we engage with public policy audiences. So a lot of what we're working on is thinking about, what is the role of public policy, what's needed in the federal government to support alternative approaches to doing and supporting science, and thinking beyond the tools themselves. How do communities like this one and the paradigms that the hardware exists in, how do these communities interact and sort of further the conversation on open science and on, more effective and more inclusive science? So today I wanted to sort of just give an overview, introduce you to some of our ongoing work, talk about the relationship between open source hardware and public policy. I'll bring up a couple of sort of case study examples, but really my goal is to actually start some conversations with all of you, or continue in many cases, about how open source hardware contributes to science, and in particular, how engaging public policy audiences can sort of further that conversation and support the broader use of open source hardware for science. So I obviously
Uh-oh, maybe we have a Houston problem. Hopefully Allison will be able to come back soon. We're not totally sure what happens. But meanwhile, don't forget that you can sign up for Teams for Trivia in the Trivia channel. And, for the other people who want to do some badge hacking, discuss it with the people in the badge hacking channel. Okay, cool. Allison is online and coming back to StreamYard, so she'll be back with us shortly. You can ask questions also as they arise about the Think Tank project in Allison's channel, which is the Open Source Hardware for Science channel. She's on her way back. And it's a cool place to see also all of the different things. Sometimes now I feel like it's pretty hard to keep up with all of the different hardware that's coming out. So many different domains, so many different applications. Hooray, you're back. Thank
Sorry,
you.
man, I don't know.
You know, it's been like this for us everywhere for the past 2 years.
Yes, exactly. Shall I continue?
Yes, please do.
Great. Okay, so I hope you're all still there. And I hope I know where I left off. But yeah, so as a bit of background, I need to load my slides again, just a sec. I would like to, apologies. Okay, good to go now. Sorry about that, everyone. So as a bit of background, I wanted to show you some resources we've developed with the goal of like introducing this space to the public policy community to help communicate about this topic, and in particular, some of the tools that are out there and how they're contributing to science. So again, this is both low cost and open source, but highlight on open source. So here I have an interactive infographic that we call Science Stack that attempts to demonstrate the diversity of tools that are out there with research topic, cost, openness, the extent to, which is open source and beyond. And the goal of this interactive is to highlight how these tools are changing science and benefiting society. So check that out and play around with it. A second resource that we have created is called Open Source Science, and that's another interactive. And that maps interactions between open hardware and adjacent communities sort of in this open science ecosystem, and sort of demonstrates how interconnected everything is and how communities work together to sort of further the conversation in open science through connected stories. So I'll describe just a few examples now about how this conversation can play out in different contexts. We earlier heard about the M19 initiative, which was really inspiring, and how during the initial phases of the COVID-19 pandemic, how community-led distributed manufacturing and open source hardware communities and makerspaces, et cetera, sort of came together to design, manufacture, and distribute equipment to fill the gaps in shortages of medical supplies that we all remember so well. So as a result of this happening, we worked with the Engelberg Center for Law and Policy at NYU, and we put together a roundtable of representatives that were involved in the response. And this report that I linked in the Discord is the culmination of a set of roundtable conversations. And we explored sort of what worked in the response, what didn't work, and how open hardware can be more effective in future crises. And then another sort of topic that I'd like to touch on is thinking about the use of low-cost sensors for air quality, and how the use of low-cost air sensors has allowed for sort of the creation of sensor networks whose data has shown how air quality can change locally and over time. So basically contributing an aspect of our understanding of air quality that essentially cannot be understood through the sort of gold standard monitors that are usually used by EPA and state regulatory agencies that are both stationary and expensive. So the low cost and small size of these air quality monitors make it possible for communities to collect their own air quality data that can be a game changer for communities that want to document environmental issues and advocate for environmental justice. So just as one example, the low cost air quality sensor that called Purple Air costs about $250 and is certainly not equivalent to gold standard monitors, but does produce data that seems to be very highly correlated to gold standard monitors usually used by EPA and state regulatory agencies. And so, for example, during the California wildfires in recent years, Bay Area and other residents have monitored their air quality themselves using these Purple Air sensors, as well as other low-cost air quality sensors. and sort of crowdsourcing those results across the region. But this creates new issues, of course, especially in the relationship between grassroots communities and regulators and decision makers in the federal government and in state environmental agencies. And the data from these low-cost sensors, in order for them to have real impact, these regulators and decision makers need to sort of rethink how they evaluate the data from low-cost tools and think about how sort of technology agnostic standards and frameworks can contribute to a broader understanding of air quality. So sort of just shifting the conversation in how tools are used for sort of understanding local environments. So these are two just quick examples of this conversation between, grassroots communities, academic audiences, and public policy communities. And we brought some of this together with collaborators last year and the year before through a policy brief, which we called Open Hardware, an Opportunity to Build Better Science, which is co-authored with Shannon Jones-Megan and Jenny Malloy. And we worked with many of you from Oshawa as well on sort of making the case for a national science strategy that prioritizes open hardware to build a foundation to accelerate scientific progress, address global challenges, and further complementary policy priorities. So in this report, we address the need to build a stronger foundation for science through open hardware and other sort of open approaches to science. And it describes the unique benefit of open hardware, and as well as addressing some of the implementation challenges, which of course are many. And so through this work and through our conversations, we are coming to a few sort of big generalizations about the relationship between low cost and open source tools and the public policy community. And so I'll just talk about our initial thoughts there, but this is ongoing work and we'd love to talk with all of you about, again, just this relationship between open source hardware and the public policy community. And the first big thing that we've realized, which I think seems a little obvious in retrospect, but wasn't so much going in, is that there's no one conversation about open source hardware in the federal government. And that also on the flip side, that there are conversations that are very relevant to open hardware happening that, never use that phrase and are happening sort of across the federal government in a variety of different spaces and in the context of specific policy priorities. So, as I mentioned, there's this conversation about low-cost air sensors that's very active at EPA. There's conversations about distributed manufacturing in the context of supply chain issues. There are people thinking about how grassroots communities can contribute to disaster response. But these are all happening in sort of a very distributed way and without sort of connections, I think, to the open source hardware community and other open science communities that could really play a role. And on that note, we've really learned that in each of these conversations, there are communities that are really central to contributing to progress. And especially in open science circles and open science approaches, I think communities are the way that progress will be made in these spaces. In particular, in the COVID-19 work that we did, we really found obviously, and we heard about it earlier today, communities played such a central role. And what was most interesting to me in that effort was finding that communities were also central in sort of the more institutional response as well. So in our work with our federal collaborators who were active in the response to COVID-19, people within the Food and Drug Administration, the Department of Veterans Affairs, and other areas of the federal government and other governments. A lot of times they worked through sort of ad hoc communities as well, getting together with one another sort of outside the context of their normal responsibilities and sort of driving initiatives forward to make connections with grassroots communities that were making an impact in this response to supply shortages. And then finally, we are thinking more and more about how open source hardware sort of plays into the conversation about open science more broadly, and how there is a message that the benefits of publicly funded science should sort of extend to broader audiences through open access and open data. But that message hasn't yet extended to open source hardware, at least from our perspective. And so we think that open source hardware is particularly helpful in contributing to this conversation because it supports opening both the products of science, so thinking about documentation and designs, and like sort of products of science in the form of tools and tool designs, as well as the process of science. So bringing people in to build and use tools, more fully participate in science through things like citizen science and other or using tools for their own purposes, et cetera. There's so many ways that it sort of builds out both process and products of science. And so that's something we want to get into further, is the communities within the federal government and how it relates to the open science initiatives that are happening. So I will wrap up by just mentioning that we're thinking about how to bridge between academic community-based and public policy communities. And we will be planning a series of roundtable discussions this year that sort of focus in on specific problems and policy priorities, like where these conversations are happening in the federal government. We're starting this spring and summer with conversations about environmental sensors in the context of environmental decision-making, and another focusing on the intersection of open source, cybersecurity, and AI. And so would love to talk with all of you. I'm interested in your thoughts about sort of the best topics to tackle that would have the most impact on the sort of broader open source hardware conversation, as well as those topics that we think could make the greatest contribution to sort of furthering effective policies and really contributing to better science. So yeah, I'd love to talk to you all in Discord and maybe in the future about topics that you're interested in. Maybe if you want to work together on a roundtable that focuses in on a topic within or a policy priority within the federal government that could make some progress also within sort of the open source hardware community. So please get in touch and let's keep talking further, and looking forward to hearing your questions. We might have a few minutes and I'll be around on Discord. Thanks.
Awesome. Thank you, Allison. There's a ton of questions for you, in fact, on Discord. A lot of details about some of the stuff on your talk. Maybe we can also just mention that this year the Gathering of Open Science Hardware is happening in Panama at the end of October. And if you want to go, you need to apply at the GOSH website, which is gathering2022.openhardware.science. And applications for that are due at the end of the month. So one of the first questions that came through was a lot of people were fond of the White House outreach Maker Fair and other open science events, and they were wondering if you were talking to the Office of Science and Technology Policy about maybe reinstating some of those gatherings.
Yeah, that's a great thought. And we've seen so many ways that the relationships that were built during that time have sort of continued on and led to some other, productive work. So I think I agree that was a really great initiative and would like to see more of it. I haven't seen initiatives like exactly focused on that so far. We are working on getting sort of better integrated in OSTP and making connections there. I do think that is a space for these conversations. So I guess I don't have a specific answer.
Maybe it's worth highlighting that OSTP is part of the executive branch. So as things change politically, things also change in OSTP. So everyone vote in your local election.
Exactly.
Other questions that people have also have to do with like regulations that help bring hardware to more widespread use. So what does it take for regulatory changes that could enable distributed manufacturing for consumer goods, things that we can maybe trust a little bit more than just like a kit or something that we hack together ourselves? Are there ways in which we could think about regulatory frameworks for distributed production of open hardware?
Yeah, that's a Great observation, and I think that's something that we will need to continue to tackle. I mean, it's a big question. And I think the first step is something that we highlighted in the sort of COVID-19 response conversation, which is that, of course, all the regulations are built for companies, like big players in the space, sort of long-standing relationships there. And so I think there's starting to be conversations about how to open that up to, bring in sort of grassroots communities, more distributed manufacturing, but it's kind of a long road. But I think the COVID-19 response really does highlight the benefit of doing that. And I think that was clear and sort of heard, at least by some in the federal government. So would love to talk to whoever's question that was about like specific regulations that we could maybe explore further.
Yeah, people have questions about it for the US, but also internationally. So great to hear that Allison is going to be on the Discord to continue answering all of your many questions about calibration, air quality, etc. But next up, we have Jake Reed, who's going to talk to us about Open Systems Assembly Protocol. Hi, Jake.
Hey, everyone. Hi, Nadia. Let me just share my screen. I think it's screen one. Yeah. There we are. Okay. So, yeah, my name's Jake Reed. I'm super excited to be here at OSHWA in 2022. I'm right now a PhD student at the Center for Bits and Atoms at MIT, which is actually where Nadia came from also. She's one of our alums. So today I want to talk about the Open Systems Assembly Protocol, which is something I've been working on for the last 2 or 3 years. It came from machine design and machine control, but in the future I'm thinking it might be a cool way for us to generally sort of build a commons of modular, interoperable open source hardware bits. So yeah, back in 2013, I started working in the sort of CNC machine space as an intern at Other Lab, where I worked on this machine, the Other Mill, which has now become part of Bantam Tools. And I was an architecture student at the time, but they hired me back on to do something I was totally unqualified for, which was design this metal laser cutting machine. So I did this back in 2016, I think. They're still available. It's a great machine if you want something somewhere between a plasma cutter and a really high performance metal laser. They're out there. And then now at the CBA, I'm working on this thing. This is called Clank. Clank is a fully FDM 3D printable modular CNC machine. So we have a bunch of fab labs all around the world, and we have always wanted to have sort of one common motion platform that we could put lots of different tools on. So when we install a fab lab, we normally bring 5 or 10 different machines. There's 5 or 10 different interfaces, and there's 5 or 10 different processes. And instead, and of course, everything's very expensive. Clank costs about $500. And also, maybe more importantly, we thought this would be a cool way for us to do sort of collaborative development of machine platforms. So if we bring the motion system, someone else can design a tool, and then we get to figure out how to put that stuff together. And that's really what or where OSAP sort of came from, the problem that generated this project, is that when you think about everything that's required to make a machine work and produce a part, there's a huge amount of layers of software, all the way from really high power software like CAD and CAM, all the way down to a bunch of real-time firmware and different types of physics. This is sort of related to the Fluigi CAD problem, is that when you approach an open source problem, you often have, or an open source hardware problem, you often have to solve like entire stacks of kit. And we want to do this in a distributed way. So we have this kind of problem, which is we need specialization of engineering with coordinated operation of different components that people make, but we want to do it in an open way where there's no explicit coordinated development. So we think this is really important if we want to go from accessible fabrication to accessible automation. So not just looking at open source projects as like standalone CNC machines, but things that are like sort of pipelined workflows, things that look like factories that start to be made out of hundreds of different machines. So actually, I'm sort of like the spiritual student descendant of Nadia. And back in 2013, when I was an intern, she was working on her PhD, and together with Elon Moyer, she wrote this piece of software called Gestalt, which is a cool way to, I would say most importantly, introduce the idea of object-oriented hardware, where you, every time you want to add a new piece of function to your machine, you snap on another module to the end of a bus. And then there's a Python script in the computer up there that sort of remotely operates all of the different modules. So the idea here was really important, object-oriented hardware, but it was sort of limited in that it centralized control into one Python script. And so it was difficult to write, especially low-level control loops. And then around the time I started at the CBA, Neil was, who's my advisor, was having a sort of obsessive phase with data flow and JavaScript. And so he was writing this thing called Mods, which is a sort of workflow assembly tool, which lets you take almost any input on one side and produce almost any output on the other side to do almost all of CAD, or sorry, of CAM, and then later also a little bit of CAD as well. And so when I started working on machine controllers, the idea was really to collapse sort of data flow into embedded object-oriented hardware. So this is Clank, and yeah, it is on clank.tools if you want to build one. And this is just one of them. This is the sort of tall version. Right now I use it as a printer most of the time. And there's an interface that runs in the laptop. There's a motion planner that coordinates sort of look ahead for the global control. And then each little other element is responsible for its own local control. So there's 4 Z motors, 2 Y motors, 1 X motor. The end effector is made up of 4 modules, which we'll talk about later. There's a bed heater, and then there's load cells. And then when we look at this as a network, this is sort of the diagram of it. So we have 7 motors, these 3 other things, a motion controller, and then there's a UI and a Node.js script. And the way OSAP works is you sort of take everything which is a memory-bound computing context. So everything that looks and feels like a module is a context. And it's responsible for its own little local environment. And then we attach networking links with these structures I call virtual ports and virtual buses, which are just nice little ways to wrap up whatever link layer you'd want and include it in the network. So as far as OSAP is concerned, the WebSocket and the serial port are the same thing. And any bus is the same thing. So a CAN bus, an RS-485 bus, Wire, or Arduino's I2C library all look like the same thing. So we can use sort of whatever link layer we'd like. And then to actually coordinate programs with this, there are additionally software modules inside of these contexts. And then basically there's a routing scheme that lets us get from any software module to any other software module. So if we want to jog the machine, for example, there's a button in the UI that we give it a route to a velocity controller later on in the motion controller. And we can route these things all the way down into sort of things that are far away in the network. So then this is the oh my God, FBM printing head extruder. It has an extruder motor and a heater module, and then there's 2 additional things. One is a filament sensor, which can measure the width of the filament and the rate that the filament is traveling. And there's a load cell, which gives us sort of a pressure analog. And so with this one, we really need to coordinate a low-level controller. We want to measure that actual filament rate and the thickness, and then control for actual flow output. And so because we can sort of route things from anywhere to anywhere in the graph, we can pull our sensor data into the flow controller, and then have the flow controller do math in an embedded context, and put an output back down into the extruder motor. So we get to coordinate low-level control loops without relying on any high-level script, like a Python script or a piece of JavaScript. So yeah, as I mentioned, these are contexts with software modules where we store the software modules in a sort of explicit tree like this. And then the strange part is that we use an addressing scheme that's path addressing or source routing. So rather than trying to have unique identifiers for every resource in the network, instead we describe paths between resources, and things are addressed relative to one another. So it's sort of like telling your neighbor to go down the street and take a left, rather than telling them to go to 34 Madison Street or whatever. And then some of the software objects are these network drivers. And so we add an additional packet instruction that tells the packet to go over the network. And these serialize into really lightweight packet headers. And then because everything is just sort of step after step, it's really easy to write very small firmwares that operate this network. So we don't need complicated routers. So we can put this in sort of almost anything. So programming these messy systems can be messy. And so for this, I tried to take a stab at making a sort of UI for this. Because they're graphs, we can render them as graphs, which is awesome. So we can actually do some programming without doing any programming. So there's no coding, but you're writing programs. And there's a discovery layer in here as well. So when I plug these two things in to my computer, they're being discovered by a sort of little network traversal algorithm. And then I can render them as they appear, and I can pull routes from outputs to inputs to connect, one button over here to an LED somewhere else. And then these also work as internal sort of data flow programming languages. So that's was just writing a new program that just lives on that one device on the right. And then I can add a UART. So this is just a wrapper on the Arduino serial object to make a new data link there. And now I'm coordinating these two things without the second USB. And I'm also doing this all live, so I can sort of hot plug everything and mess around with it. Yeah, it'd be cool if you could see where they are and actually project the UI on top of them, but yeah. And then this runs without the browser at all also, just to drive that home. This is going on really in the embedded system. So it's roughly embedded data flow everywhere, hot plugging below it. So I wanted to show a little bit of scaling. So this is a sort of messier system. As I'm plugging things in, they're popping up. And then I can, how are we doing on time? I can pull one output to this button all the way on the left. I'm going to draw it out to all the other LEDs in the rest of the system. And as I'm doing this, it's finding paths through the network in order to coordinate how to get things from one end to the other. And I can make mistakes also. I accidentally plugged the wrong thing in over there. And instead of having to go and look at my code, I could just look at the graph and say, oh, I've actually misconfigured this. And then also graphs are sort of automatically reclaimed. So I've unplugged it on the left. I've removed all the state from the browser. Now I'm plugging it in all the way on the right. And it's going to draw the same graph, but sort of coming at it from a different angle. So it doesn't matter which device you start with. There's no inherent hierarchy. Everything is like everything is everything and sort of anything that you want it to be. And then I thought I would do one fun, tiny sort of like interface code. So this is an IMU device from Adafruit. And I thought this was fun too, because at first I was like, oh, the X in the sensor is probably the X in my rendering engine, but it's not. There's actually a little bit of orientation trouble here. But this is a way to configure this, is to just pipe the X into the Y and mess around with it and see what's wrong. And you get a sort of immediate feedback when you're building the program. So how do you write this stuff? Basically, OSEP is a software API for a network interface. So you describe in software what your network interface is. I use these things called endpoints that have callbacks when you get new data that you can write to. And you can put routes on them. So if there's a route attached to an endpoint, whenever you write to it, it's going to try to publish that data on that route, probably to another endpoint. You can make, yeah, there's BNO 055. You can make virtual ports in Arduino just like this. I wrote these sort of helper classes. So if you have an Arduino sketch with a serial port on it, you can just one line make a virtual port. I'm working on the wire one. Multi-host buses are tough. And you can write whatever weird link you have just by attaching a bunch of callbacks to it as well. And then finally, hopefully I'll have time for questions. I think I will. I did want to also talk about why I'm really motivated behind this project recently and why I'm starting to try to make it public and get other people to hang out and work on it with me. I recently read this really cool book called Working in Public, written by a woman named Nadia Egbal, who worked at GitHub for a long time and studied open source software. And the thing she comes away saying is that when we think about open source software, we normally think about sort of Linux and LibreOffice and Apache, big standalone projects. And she's saying in reality, we need to think of open source as a sort of commons of functional modular units. So she's saying, let's look at NPM, which is Node's package manager, and pip, which is Python's package manager. And she's saying that the things that most people consume that are open source software are actually products that are made from modules that are open source. So when you use an app, probably 90% of the code base is actually open source, but we don't normally see that. Open source users are sort of open source developers. And so really critically, the way that we integrate our modular contributions together is super important to the success of an open source endeavor. So right now, I think the dominant sort of mode of commons production in open source hardware is that we have Arduino libraries, breakout boards, and then dev boards. And none of those things are function on their own. They're components that we use to build function. And so we all end up doing this sort of breadboarding exercise, which can be confusing because the elements we get from the different commons need to also work together. And so we're sort of always recreating work doing this. And also none of this scales beyond one microcontroller. Yeah, DevBoard Industrial Complex was Zach Frieden. I don't know if any of you know him. Yeah, so the proposal is that with OSAP, you can basically take all the complexity of your little module and then wrap it up into your module, which has a firmware that people can look at, don't have to look at. And then we put, network interfaces on everything. Everything has a USB port basically already. Most things have serial ports as well. And then instead of integrating things with code, we integrate things with graphs and network applications. So that's it. Hopefully we can answer some questions. I don't want to do this thing, which is try to make a new standard. But I did want to sort of, I guess, poke everyone and see what the feeling was like about this. So yeah, I just published osap.tools, where there's sort of more writing on this, and then there's a link to an example project that you can build. And yeah, Clank Tools is also online. So that's the talk.
Awesome.
Nadia is also on my generals committee, everybody.
Yeah, we're gonna make this straight into a very, very intense Q&A. Now, maybe there's a ton of questions about details, like how does port forwarding work? How do you imagine doing power, especially for mobile devices? But maybe before we get into that, there's a lot of people at the Open Source Hardware Summit who build hardware. And what exactly is your ask? You have this system and you have a standard. And so what is it that you want people to do next? Ideally, this is the perfect world. Right after this, everyone is going to do what exactly?
I think, yeah, that's a great question. Try it out, see if it's useful for you. Let me know if it's interesting or if it's just a total dud. I don't really know. We're isolated here in academia. I use it to build machines. It's been really useful for me. I don't really know what types of applications people want to build. In my head, it's a way. So Adafruit and SparkFun have Quick and Stemma, which feel to me sort of in the same direction, where they're saying, okay, let's get rid of this complexity of figuring out pinouts every time we want to do a project, and just build a world where people can plug stuff in and throw it into a sketch. Those two are still limited by sort of the one microcontroller boundary. And so, if you have two Arduino projects that you have been trying to get to do stuff together and you haven't been able to do that successfully, see if you can use OSAP to get it to do something successfully. I think there's sort of this fever dream of everything's a module and wouldn't it be so cool? And this is, I'm not saying that I have the answer. There's so many questions like how you can do it. Yeah, like what are the standards? How complex does it have to be? Does it include power management, or is that an application on top of it? I don't really know. I'd love to hear like what people think about that. Yeah.
Well, awesome.
And sorry.
No, I was just going to start saying that you should answer everyone's. There's a lot of people who have questions on Discord.
Totally, yeah.
And so everybody, let Jake know what you want to build with modules all the way down. What if everything could just be done for you in a network rather than all of this configuration that we have to do every time we want to switch tool chains? It would be amazing. Yeah, so Jake, adding another point to the secretly Canadian vibe of this conference.
Yeah, secretly Canadian. I know. I showed Arthur to my brother last night, and he was like, "Oh, Ontario Secondary School Assistance Program, right?" Like, oh no.
Cool. Well, next up we're going to have Lucas. Lucas is going to talk to us about how to actually ship an open hardware laptop, which might include some lessons that we weren't expecting.
Okay, hi everyone. Let's see if this works. Can you see my slide? Yeah. Okay, perfect. Yeah, I'm Lukas Hartmann, the founder of MIT Research in Berlin. We designed and shipped an open hardware laptop with a tiny team and an initial budget of 150,000 euro around. In this talk, I'm trying to extract some key lessons from the whole undertaking, some unusual practices that work for us and that might be helpful for your own projects. The first lesson is make reproducible hardware. We funded and launched the MIT reform through crowd supply. This is the campaign page today. And this is the MIT reform, how it ships today. The trackball version, running Debian Linux. Why do we call it reproducible? Because all the PCBs are open hardware under CERN OHL, and we have free and open source firmware in the system controller and input devices. And we also publish the sources for the mechanical parts. That means you can not only study the device, but you can also reproduce and improve it independently from us. Here's another version of the laptop with a multi-touch trackpad. As you can see, we made some unusual choices. The device is quite thick and has Ethernet and other full-size ports. If you flip it over, you can see that the underside is transparent, inviting you to open it and explore what's inside. Here's the motherboard design in Kicad, which is our favorite open source electronics design tool. It probably gets mentioned a lot today. You can see that the design is certified open hardware by OSHWA. The keyboard and input devices, trackball and trackpad, are designed in Kicad as well. It's okay to simplify. Because our core team was only 3 people, and the laptop is a very complex device, we had to make compromises or be stuck forever in the so-called development hell, and we would have run out of time and money. So we made some unusual choices and compromises to be able to actually ship this thing. For example, we really wanted a mechanical, low-profile keyboard. We decided to go with Keil chock key switches, which were still up and coming in 2019. This is our keyboard layout. And if you look closely, you can see that it uses only 2 different keycap sizes, 1U and 1.5U keycaps. Here you can see that this means that the stagger in our keyboard is slightly different than in traditional keyboards. The bottom picture shows that the traditional layout that you're used to is slightly irregular. We went with the layout on the top because it would have been much more complicated and expensive to procure all the different keycaps needed for a traditional layout, and we would have required mechanical stabilizers of different sizes for all the bigger caps. The idea was taken from the Commodore's SX64 keyboard. Here you can see on the red line, with those red lines, that Commodore used the same trick to save parts in the 80s. Sometimes it's worth to look at old hardware for new ideas. local small batch assembly. Because we were dealing with many unknown factors, we decided to do our own assembly in small batches in our own studio. So we decided to design everything in a way that we can hand assemble, which was very valuable in the prototyping phase. For example, we mostly avoided components below 0603 size or BGAs, wherever possible. These are various versions of the motherboard that we all hand assembled here. We have very basic stenciling equipment and an infrared oven to reflow the boards. This way, we can quickly iterate on revisions without spending too much money and time on external services. And very importantly, we ensure that other people can also build or repair these parts without special equipment. So if you combine the first 3 lessons, which were publish all the designs as open hardware and keep the components and assembly simple and produce in small batches, then you can make co-creation happen. I will show you an example. Norman Feske of G-Node Labs was one of the first people to receive the laptop, and he immediately looked for a way to make our trackball move more smoothly. He found a very nice solution of drilling holes and inserting 3 steel ball bearings in the 3D printed cup. The ball then rests on these smooth bearings instead of the 3D printed cup. A few months later, Reform owner Hayden Krupfel picked up the idea and posted his modified design files in our MNT community. We reproduced Hayden's idea in our lab and found it superior to our own solution, so we adopted it in the middle of production. There have been several other people in the community improving the laptop's firmware, Debian integration, and more. Work together. The current version of Reform ships with the NXP IMX8M system on chip that you can see here on this boundary devices module. This chip is well documented, well supported by open source drivers like Etnaviv project for the GPU, and energy efficient, but too slow for some tasks like heavy JavaScript applications or video editing. We were expecting follow-up processors from NXP by now, like IMX9, but they just did not appear, maybe because of the chip crisis. So we decided to design adapters for SoCs, system on chips or system on modules that would be considered competitors if you had a closed mindset. Here's RCM4, an adapter for the powerful Raspberry Pi Compute Module 4. And here it is installed in the Reform motherboard during bring up. So why not join forces with other strong communities? In our case, Raspberry Pi and Pine. The most important thing is to get useful hardware and choice into the hands of people. Increase freedom through design. For example, by modularity. As mentioned before, the laptop is designed so that the main system on chip and memory can be exchanged. We also have open hardware modules, one made in Altium and the other in Kicad, that people can use as templates. So 2 of these modules you see here are also open hardware. Here is the somewhat dense 8-layer Kintex 7 FPGA module made in Kicad. This module can boot Linux on a soft RISC-V system, for example, powered by Litex. Another example is the keyboard. It is a self-contained USB input device. And you can also put it in an enclosure to use it independently from the laptop. FDM printable parts. FDM 3D printing is becoming more and more reliable and precise, while also cheap and environmentally friendly. 3D printers are everywhere. So instead of having to ship replacement parts around the world, people can just print them locally. Here you can see we switched to PLA in the production of the trackball housing. We even print early case prototypes in PLA here. This is a very early validation prototype of MNT Reform. with fully 3D printed case. Standard components like batteries. We didn't want people to rely on us to source and replace batteries for their laptops. And we wanted to make sure that no one would put themselves in danger by experimenting with burning lithium ion cells. So we picked the safer lithium iron phosphate chemistry, also called LiFePO4, and decided to go with a standard form factor called 18650. This way, reform owners, but also we as the manufacturer, can pick from a wider range of suppliers that offer the standard format. That's very good in case of shortages. Standard fasteners. This is not very exciting, but instead of requiring special custom screws, we use standard M2 screws almost everywhere in the device. You can download a laptop. One really nice result of all of these unconventional decisions that we made is that people can actually fork and recreate the laptop, the complete laptop, locally. This is Jacqueline from Australia, who built her own version of Reform and modified the motherboard and the keyboard in the process. For example, she added USB-C power delivery to the motherboard. This was possible because we published Kicad sources and documentation for the motherboard. Here's her motherboard in the middle of being hand-assembled. For the keyboard, she made a big edit and turned it into a split ergonomic layout. And this is a shot of her laptop in its aluminum case, which she was able to get made from our design files totally independently. So this laptop was completely made without our parts in Australia. Creative Commons unbrand. One more little problem we solved is that we didn't want people to use our brand logo on their clones and forks because we can only be legally responsible for products that we make ourselves. See also like customs requirements or WEEE. But we still want people to be able to signify which ecosystem the item is compatible with. So we created this unbrand that is similar but different to the original. This is released as public domain under CC0. Here is how it looks on a PCB. And to wrap it up, yeah, let me repeat the points. So our takeaways are: make reproducible hardware, like publish the source files for everything, not only PDFs with schematics. Simplify wherever possible. Make compromises, it's fine. If you work locally and make small batches, you can improve the product while you're still building the batches. So you don't have to get everything perfect on the first try. Embrace co-creation. That means work with your community to get changes merged back into your product while you're making it. Work together with your competition. Maybe they're not the competition after all. Embrace modularity so that people can mix and match parts and reuse parts of your product. Use standard components wherever possible. And if you want, create an unbrand that people can copy, but you are not legally responsible for. And thanks, that's it. So I guess we have time for questions.
Thank you. This was really great. People are so excited. They want everything. I really like your choices. They're really enthusiastic about the unbrand. So they have some questions for you, including what do you mean really when you say small batch? Is it like 1, 10, 100, 1,000? What do you think is small batch for different people?
Okay, so yeah, it depends on the product. So if the product is, for example, one large PCB or something, then a small batch we usually work in batches of 100. But for the laptop, we work in batches like 50, and the whole batch size, the first production batch size of Reform was 450 units, but we split this in like sub batches of 50, for example, and we incorporated changes during these micro batches.
Cool, cool, yeah. And I guess there's so many things that can be batched also in your hardware. There are the little parts and then the whole laptop. So it's maybe batches all the way down.
Absolutely.
Some people have just questions about the details of being an unbrand. Is it like, did you copyright the logo, or like, did you put it in the public domain? How would other people go about making an unbrand?
Okay, so the idea of the unbrand is that our main brand is copyrighted, like it's trademarked, because we need to protect it for legal reasons. For example, customs will check, what brands is on stuff, and WEEE requires you to put your brand on stuff because you're responsible, like, for the safety of the thing, and so on and so on. And so we were like, okay, what if someone else makes a fork and resells, for example, the hardware? They need to change the logo, but it would be nice if they could still, if they wanted, refer back to the original thing and somehow signal what it is compatible to, where it kind of belong, what ecosystem. So we have this kind of alternative brand that is public domain, and that doesn't mean that that is from us. That just means it's like kind of compatible on the spirit, or maybe uses like original designs from us.
Yeah, yeah. I think a lot of people have questions about just like any legal stories that come from having a public domain brand. And so maybe that's something that everybody will want to talk about in the Question Everything Discord channel. But we have other questions too. Some people are asking about like if there were design decisions that you started with that you then regretted, maybe because you wanted things to be hand assemblable, but then you changed your mind for things. So can you talk about maybe how over the course of the project you changed things about the design and why?
Well, we didn't change a lot about the electronics in the course of the project, but we made some manufacturing changes. So, for example, we work with SLA printing in-house on the trackball because we thought we needed the precision of SLA for the trackball cup. And we printed our own trackball buttons and so on in-house, but this turned out to be very messy and toxic. And so we outsourced the buttons to another company who specialized in SLA printing. And we changed the process of printing the trackball cup and the trackpad holder to FDM. So we are printing them still in-house, but now on, let's say, safer and more environmentally friendly technology.
Oh, cool. That's a cool way of changing. Yeah, in-house control can mean lots of in-house goo, I guess.
Mm-hmm. Yeah. So you need to make sure that you can really handle that kind of stuff.
You mentioned that you didn't change the electronics much, just things about the manufacturing. And people have questions about just like keeping track of changes across manufacturing different batches. Do you have like batch versions? Do you do a different kind of version control for batching when you do different manufacturing runs? Can you talk about that?
Yeah, so at some point we introduced a so-called badge on all PCBs that always looks the same. And it has like our SKU number and a revision number and a date code and so on, and a license, the OHL license in it. So we update that, and so then you can also see in which kind of Kicad file does it correspond to.
Cool.
In other projects we also made electronics changes because there were like just bugs in there. But and we will also do it in the next reform batches. We will fix some bugs.
Nice. That's always nice. Yeah, there's a question also just specifically about electronics design. I think it's maybe more about future feature requests for Kicad, perhaps. Somebody wants to know, well, you design modules in some proprietary software packages, but a lot of them also in Kicad. Is there anything that's missing from Kicad that you want to see? Is that why maybe you use other packages like Altium?
Okay, so here we only use Kicad, but there's the LS1028A processor module designed by RBZ in Spain, and they only use Altium for everything. That was just a compromise of our collaboration. They agreed to publish it as open source, so you can download the Altium files. But if we would have done it ourselves, we would have done it in Kicad. But it's always like, what people are trained in.
So we'll have to ask them to see what features they want. Maybe the features that they want is just that they want to watch Chris Gammel's Getting to Blinky. Well, thank you so much for your talk. Lots of people are excited about your laptop and have even more questions for you in Discord. You can follow up with them. It'll be awesome. Meanwhile, in another Discord channel, the Supply Frame Hackaday Tindy demo hour is ongoing. If you want any intros to people at those places, and they have discounts and project links for other cool stuff. And next up, we're going to stay in Berlin, duking it out with Canada, with Robert Nuis and the Open Hardware Observatory.
Yes, hello. Hi, Nadia. Can you hear me well? I hope so. So, as far as I'm concerned, I'm live. Yes, I hear that. Yes, thank you. Let me just also start here. Okay, so I will share my screen quickly. Bildschirmteilen. And that should do the trick. Right. Which screen can you see? Great. I thought I had this. Can you see PowerPoint slides by chance? Otherwise, I move them around. Sorry for that. No, we see nothing. Okay. Okay, we see everything. Great. So now you should see also my slide deck, hopefully. Yeah, quick feedback would be great. Otherwise, I'll just continue talking if I'm not. Yes. Okay. Right. That's the trick then. Okay, that's very easy, I think. I just have to change the. Okay, sorry for that. That's of course a bit embarrassing now. I just have to change the presenter mode. Yes, and now it should work. Okay, very good. So I wasted a minute, but I hope the next 10 minutes will be better. Yeah, I'm Robert Mies from the Open.
Hey, you are muted. We can't hear you. We can see your slides, but maybe you can also say that the screen share thing is cool, or move that notification away, and turn your microphone back on. We don't know what happened. Maybe. Can't hear you. Maybe you could.
I could.
Now we can hear you.
Okay, I have no idea what just happened. Anyway, so let me just say that I have been working for the Open Hardware Observatory in my free time. We all have been, and it's a non-profit association from Berlin, and it was founded in 2021 as a spin-off of the Technische Universität Berlin, so my employer, and the OpenNext project, which I've been working on as a project manager for the last 2 years, 2.5 years. So the main goal actually of OVO is to support, improve, and make known sustainable open hardware projects through our web platform. And you can of course visit us. I would like to encourage to do so. But we have some sub-goals which I also would like to mention. So we'll promote publicly available do-it-yourself and open hardware projects, even since a couple of years now, also before we were founded as an association formally. We certify and improve selected projects by skilled and experienced experts, and we create blueprints for selected projects and publish them under free licenses. All of this is in a bit of a prototype state, and just to say, so I'm an industrial engineer. I study in our groups engineering design, and actually our idea is that of open hardware is really that there needs to be more interaction, and there needs to be more sharing, and there needs to be sharing of documentation, especially for mechanical hardware. This is key, and this is very tricky. So that motivated us some years ago. We've been thinking, a lot of people have been trying to develop a GitHub for open hardware, and that's a great mission, and fully support that. So our vision was a bit different. We said we would rather create a Wikipedia for hardware in our frame, and that's because the motivation is really from Wikipedia to make available free and encyclopedic knowledge to everyone, and this is open content, and they have created more than 50 million articles created within the community, and you can see here the free world, the universe of free knowledge, the really free world, so to speak, maybe. And so within that frame of having different projects, developers, foundations, editors, readers, donors, we think that there needs to be also a similar kind of trajectory for hardware. And so we thought, let's contribute to this also for free technical knowledge. So open hardware, and actually, that's quite natural if you think about the fact that thousands of hardware projects obviously are created to serve unmet technology demand worldwide, and then there are only a few people knowing this. So that's pretty much also, to go into that a little bit, the starting point for us. So we see that these thousands of DIY and open hardware projects worldwide, they offer lots of different solutions for sustainable development, and actually they can help create small and medium enterprises and startups. That's also an important factor. And of course, they are developed by individuals, by companies, and especially communities. And we have different solutions in different domains. And that also means that if we want to change industry, and if we want to change something in real terms to create products, then like we've just seen in the previous talk, then we need companies. And this is actually where we started some time ago, and I would like to go step by step about the different things we did. So we started with different prototypes, to be honest, which I will just show you, and I will show you each time a little bit where we got and where we stand. So first of all, we created a search engine, and this search engine actually was jointly created between the Open Source Ecology Germany and the TU Berlin team here. Dietrich Jäger was at the time from Open Source Ecology Germany, and that's also how I got to know Martin Heuer at the time. And then we actually had an idea, so Unix developers can find open hardware projects faster and easier, and new projects can build on the experiences of already realized projects. So this is some time ago now, and it's not such a revolutionary idea maybe today anymore, although it still is, but not to you, who are more versed here in this summit. 12,000 project results were crawled in 500 technology categories on OVO, and so we crawled on Google, YouTube, etc. To be very honest, it was a lot of work from Dietrich Jäger at the time, who had a company here in Germany that was, or still has, that is well versed in search engines. Now the search still exists, and just to say quickly, it crawls the web, of course. It categorizes the search results and then stores it in a database, and it makes it accessible to a search interface for you. Then, let's say around the same time, we also created the Open-O-Meter. And so the OHO provided for the, as part of the OHO project directory, a solution to verify the Open-O-Meter at the time. So at the TU Berlin, a colleague of mine, Jeremy Bonmaison, and myself, we created this idea of the Open-O-Meter to say how open is hardware. And the OHO was at the time for us, you see it here on the right, the database where we kept our results that you can still see today. And there we have created 219 rated projects with descriptions and links for browsing, which some of them are not up to date. And then today, of course, anymore. I don't want to go too much in the past. I want to go in the future now, but this is important because from the idea of rating projects and looking at projects and the Open-O-Meter stemmed this idea that was heavily pushed by Martin Heuer at the time of making the DIN-Spec 3105 initiative. And so this was to define a bit more based on the OSHWA definition and open hardware, and also make an attestation procedure of open hardware. Attestation in this case means really to check documentation and also the licenses. In the year after we started this, we created the old certification platform, we called it, but it's not really the same as, of course, the OSHWA certification. It's a bit different. It's for open reviews or peer-to-peer reviews, and it follows the definition of OSHWA indirectly. It actually allows to assess hardware according to the DIN-Spec 3105, and was basically the instance to put that into action at the time. So we created a workflow for that, and you can see on the side a little bit how it works. You upload your bill of materials and your documentation, and then you can review it with different reviewers. I say a bit more in the next slide about the workflow. So in the end, in 1st of April, we decided, okay, we've been doing some prototypes now. Let's found OHO, let's say by then the results, we were also involved closely in the DIN-Spec 3105. So that also we feel like part of that. So it was the first open access technical specification by World Publishing at the time, or the DIN-EV, which also sponsored this effort. And also it was, by the end of last year, the case that we internally also tested this reviewing peer-to-peer procedure or workflow with more than 100 fully documented open hardware test projects, which were realized. And on the page, you can see it when you go there. And also we realized in the background a GitLab project management workflow, which made the whole process quite fast for us. To say a little bit more about this, but not too much for timekeeping. So the OHO team then, together with a wider network, of course, that we were part of only, developed the appropriate standards for open hardware. Then the idea was that the community comes and selects the excellent projects, and then reviewers, and then the reviewers examine the project, and then there's a way to appreciate that the release really is replicable, complete, and also has a license that allows for everyone to use it. There's a little tweak to this also. Eventually, we decided that we also should use this to improve projects, of course, and also maybe in an active way to bring in experienced engineers and create blueprints and parts lists. Like I said, to show you in the previous slides, that we also did our own projects just to try this out. But this could also be expanded upon in the future. So we call this the CAD center. And then finally, the last activity I want to mention to you is the OSHA data. You may know it if you've been following the OSHA activities. In mid-2021, the OSH Data Initiative, or also blog in particular, was handed over to our team by Harris Kenny. And yeah, so just a few words about OSHA data as well. What does it do? It studies brands, markets, and products and people who make open hardware work and shares its findings via blog and newsletter. So yeah, you can check our recent blog post, which we will also share with our newsletter on Monday. This is some work that has been coming out of the OpenNext consortium by the team led by Martin Hoyer. Also, so we've been working in different capacities together. I mentioned his name quite a bit now, I noticed. But yeah, so the next steps will be to continue reviving the OSH status annual state of Open Hardware report later this year. Yeah, after there was a bit of a pause last year due to the handover and reorganization. Yeah, so if we can share something, a post from you or your organization that could be interesting for the same audience here, please contact us. Just to maybe reflect on this a little bit, I didn't write this all down, but I think it's very good. The previous talks, they showed the difficulties with hardware, mechanical hardware. And I think there is a great sense of also change here needed. So in a great sense that also was mentioned by the talk previously by Jake Reed. So when big engineers design open source modules, reviews would be very important in the future, also for mechanic hardware. And yeah, we hope that eventually we can provide some really good solutions. And yeah, so a bit like in that talk as well, we are also working here with prototypes, I would say, at this point. We would like to demonstrate this more. So eventually we do want to create some revenue streams. We want to acquire a larger pool of expert reviewers, and we want to advance these existing offerings now for specific target groups. So this could be going in different directions: science, businesses, citizens, DIY, or also especially global South initiatives. I think today was really good also to see the diversity of hardware. Otherwise, on an operational level, of course, we would like to expand on our resources, in particular in sustainable development in Global South. But also, yeah, we've looked into open agricultural technologies recently. Open science indicators is a topic that we're very interested in. Also, DIY or open up equipment design, evaluation, and sharing is something that interests us. So I will close my talk here, and maybe with just a few pointers. So we would be really interested in the near future to work on European research and innovation actions also, or innovation actions more so with URU. We want to also get ideas. That's why we're here today. So if you have some good idea on right to repair or market research, or you name it, you would like to connect with us where you see our resources useful, please do so. And also, if you would like to certify your documentation release, please contact us. We may be able to help you improve it. Or if you don't, also tell us why. And then also like I said, you can contact us if you want to make a blog post. That's it from me. Thank you very much.
Awesome. Thanks a lot. This is a really awesome project, a really great initiative, understanding how different parts of things make up the ecosystem for open hardware. One question that I have is with respect to reviewing, for reviewing, how do you ensure that we're reviewing both best practices and that we're enabling the values of the community to come through? I think reviewing for engineering is one aspect of that, but there are also other ways in which technology can be appropriate or inappropriate. And I was wondering if you thought about that at all.
Yeah, could you repeat the main question again?
Just how do you make sure reviewers are not are being generative and not just like exclusionary?
All right. Yeah, that's a good question. So reviewing is a difficult process, and let's say we've more looked into the technicalities of it so far. And you're right, in practice there are many things to consider. So we would like to understand also better how this workflow does turn out in practice. And I guess the honest answer is that we have been using it ourselves so far mostly, so we would also need the practical exposure a little more. Yeah.
And there have been studies in the past that for community reviewing for projects like Wikipedia, that as time goes on, the projects can become more and more hegemonies where they're controlled by only a few moderators. But lots of cool stuff to dig into. There's lots of people who I think want to talk to you in the chat, so maybe you can hop on there if you have a second. Don't forget to say hi to also Supply Frame Tindy and Hackaday people who have also, by the way, the Hackaday SuperCon. And next up, we're going to have Alexander Adams, who's going to talk to us about equity-driven design of and novel sensing systems. Hi, Alex.
Hey, how's everyone doing? All right. All right, let's get started. I've got a bunch of slides, so I'm going to move pretty quick. This is a
I am also muted, sorry. We were just wondering where Alex went. He's, we missed, oh, here we go, you're back, thank God.
yeah, sorry about that. I hit the wrong button. Okay, so slides PowerPoint. Okay, let me just get this uploaded real quick. All right. Is there a way to share screen on here? Oh, there it is. You guys see my screen?
Do I have a joke I can tell? No, not funny enough. We are finding out what's going on with Alex, and hopefully he will be back shortly. We could also maybe take our 10-minute break now and then have him come. All right, we're going to have a 10-minute break. And so, oh, hello, Alex. We were thinking maybe we can take a break now while we figure stuff out, and then people can come back in 10 minutes. Yeah, everyone on live stream, let's say 10-minute break. We love you. We check things ahead of time, we swear. Okay, we are changing the schedule slightly. We have added Alex to be part of this segment. So I hope you all had a chance to grab a snack, use BioBreak, and try two with Alex Adams on equity-driven design. Hi, Alex.
Hey, how's it going? Sorry about that, everyone. Sometimes technology is not your friend. All right, so today I'm going to talk to you about equity-driven design of novel sensing systems for health. So again, my name is Alex Adams. I'm a research scientist at Cornell Tech in New York City. I work for the Precision Behavioral Health Initiative. Right. All right, so I'm going to do this talk in a slightly different order, kind of a weird order. First, I'm going to motivate the problem and talk about the prevalence. Then I'm going to talk about a project called OptoBeat, where we demonstrate equity-driven design principles. After that, I'm going to jump into the guidelines and the considerations that go behind this design principles. And then I'm going to go back to another project to talk about it more. The reason I'm doing this is for time's sake, because this is taken from a much longer talk. All right, so first things first, I want to kind of define some of the words and phrases I'm going to use throughout this talk. The first is determinants of health. So determinants of health are the conditions that surround a person, where they live, work, grow, their age, their income. So this is at a personal level. Then we have health inequities. This is more of a systematic level. This is unfair differences in health status between populations. Then we have the ending result of health disparity, of health inequities and determinants of health, which is health disparities. These are negative gaps in health segments of the population that are avoidable, unnecessary, and unjust. And these are mostly based on the determinants of health. So just to give you an idea of how big of a problem this is, so if you look at some chronic diseases here, so pediatric asthma, it affects 7.7% of white American children, while it affects 12.6% of Black American children. Diabetes is 13% white Americans and 3 times that high for Native Americans, 39%, 21.5% for Latinx, and 19% for Asian Americans. And hypertension is almost twice as high in Black Americans as it is white Americans. It doesn't just affect chronic health, though. This other things like insurance. You'll see that only 5.9% of white Americans are uninsured, while 16% of Latinx are uninsured, 14% Native Americans. This also goes to how well people actually feel. Their reported self-report on how they feel. It's 8.3% feel poor health in white Americans compared to 17% in Native Americans, and so on. Then there's treatment, mental health treatment in particular. So 18.6% of white adults get mental health treatment, while only 14% of Native Americans and 10% of Native Hawaiians do. So technology is not the be-all, end-all solution to this. So technology can also add to this problem. It can be not sensitive to different skin tones, like the pulse oximeter, which has recently had a FDA warning put out against it for not working on people with darker skin tones. It could be not sensitive to different body types. So if you all know the BMI sensors you buy at the store that tell you your body fat index, those actually don't work on obese people. They're made for normal body mass indexes. It can also not be sensitive to gender or sex. It can add to existing stigmas in the case of substance use disorder or mental health specifically. And it can be too expensive for a lot of people. And the price is probably the biggest inequity of all. So equity-driven design can enable equitable solutions. So basically, what is equity-driven design? It's a collaboration between scientists and domain experts in which you consider the determinants of and specific needs of a population it's intended for. It's intended to address both existing inequities and fill gaps in healthcare through filling gaps in technology. And it covers both mental and physical health. So a good way to approach an equitable design kind of scenario is to look at it through an ecological model. And this is Bronfenbrenner's ecological model. And what you'll see is that we actually start with the person in the center here when we're looking at the problem and all the different determinants of that person. Then we go to the microsystem where we look at where they live, where their housing situation is, their families, their therapists, their employers. That sits inside of a mesosystem, which is the interaction between systems. Going further out, we go to the exosystem, where we look at more of the community, social services, societies like AA or NA, and the neighborhood they live in. Furthermore, you're looking at the laws and attitudes of society and the economy, how the economy is at the time, culture and ideologies. And this all sits inside of time, where all these life changes happens, which we know affects health in so many ways. So I'm going to talk about two projects, specifically OptoBeat, which is a solution for pulse oximetry. It's a skin tone calibrated ultra low cost pulse oximeter. And I'm going to talk about Puff Packet, which is a discrete and automatic device for monitoring e-cigarette use. So, as I mentioned, pulse oximetry fails in people with darker skin tones. This has been going on for about 20 years. And unfortunately, it wasn't brought to light until the recent pandemic, in which respiratory illness became so pervasive. So why did it fail? Well, so let's talk about how a traditional pulse oximeter works. It shines a couple of different wavelengths through the finger. Those wavelengths are compared using Beer-Lemons law, and that gives you a ratio of oxygenated and deoxygenated hemoglobin. But what you can see here is that while they require this inverse relationship of absorption to oxygenated and deoxygenated hemoglobin, underneath all that is melanin, which is the molecules that change our skin tone. And that is not linear. It's not consistent. So how could we have a consistent measurement if we don't know that skin tone? So we started thinking about solutions. First thing we were thinking about is how to make this pulse oximetry even more pervasive, more accessible. So what we thought, we had a little computer with some lights and a camera on it in our pockets. And so if you look here, you can see the spectrum of the phone screen. And we can see that we have this inverse relationship with blue and red for oxygenated and deoxygenated hemoglobin. So this led us to build OptoBeat, which is, as I mentioned, an ultra low cost smartphone based pulse oximeter with skin tone calibration. So how does it work? So basically we have an app, it shoots light through a little clip into a plastic lens. It goes through some fiber optic cable into your ear and out your ear, into another lens, into the camera. So why does that work? It works because we can change the color of the screen to alternating colors, and the ear, which has lots of capillaries in it, which is inclusive criteria for measuring a pulse oximetry, and a shorter optical distance than the finger, which is what you're probably most familiar with seeing. So then we get that back into the camera, and we get basically a ratio of absorption. So our hypotheses were that we can also classify skin tone with a smartphone camera, and this can be leveraged to calibrate pulse oximetry, and then show that our pulse oximetry measurements are reliable down to even unhealthy levels as low as 70%. And this is a crucial criteria because other smartphone solutions have failed in unhealthy patients even below 95%, which really makes them not useful at all. So for skin tone calibration, what we did is we got some synthetic skin, some phantom skin that was made out of proteins and fibers and 3 different skin tones. And we printed out a skin tone color strip. And by taking an image of those two beside each other, we actually have a light calibrated ground truth. So we were able to classify skin tone actually quite easily. And the results were, so basically right here, what we did is we actually tested the pulse oximetry measurements in each skin tone. And these proved our point, our hypothesis too, that the pulse oximeters do not measure correctly in different skin tones. And here you can see with OptoBeat and with the ground truth gold standard pulse oximeter that the skin tones did have a huge change in between types of skin tones. All right, so we've done that. Now, how do we test without getting patients involved, really unhealthy levels of pulse ox, blood oxygen saturation? Well, we reoxygenated sheep's blood and pumped it through a system where we could let the oxygen slowly leak out and measure it over time. And we get this linear decrease in blood oxygen saturation. And it worked really well. So here's what the setup looked like. We have this synthetic artery and synthetic flesh. We did this with the different colors. We had some optodes in there and ground truth, and we pulsed blood through there. Over time, that would decrease, and as you can see, we got this great mapping with the regression. So then we want to show, yes, this also can work on human subjects. All right, so we tested it on ourselves, and we get signal. Now, in the future, what we're doing is actually trying to create a more robust in-house testing system so we can really build this out more. So we're actually now building a sort of DIY excorporeal oxygenation membrane. So this will allow us to not just wait for oxygen to leave the blood, but to actually control the levels of it automatically. So how is this all equity-driven design? All right, so we have the skin tone calibration to account for that, and then we made it ultra cheap, right? So the idea is that this could be costs less than $1 for me to make, so at scale would be even cheaper. And it could be pseudo-disposable even if you're looking at a very high infection area, such as when there's a pandemic breaks out and people are in a waiting room and they all need to get their pulse oximetry tested. How do we do that? So anyways, so let's go into the design considerations. And this is more general design considerations for equity-driven design, and some of which you just saw in OptoBeat. So the first thing I want to do is talk about sheep. So the first things we need to do when we're thinking about a problem is we think about bias. Is it going to have any bias to it, like a lot of computer vision programs do? Can we make it affordable and make it accessible? So not only can it be affordable, accessible because it's affordable, but accessible regionally, right? So one big problem is location and being able to get to the right services. And we need to think about heterogeneity, like how well is this going to work across different groups? I mean, just because it's made to include a group that was not included before doesn't mean it should only work for them, right? How do we make this work for as many people as possible? The next design guidelines are called CUPS, which is cost benefit, utility, privacy, and stigma. So cost benefit means that the cost of using it should be outweighed by the benefits it provides. Utility, this device needs to have clear benefits over traditional non-technological counterparts. Privacy, this is private data, it's health data, you got to think about that. And similar to privacy, but very different at the same time, is stigma. So it should be discreet for use and not look like a medical device. This is particularly important, as I mentioned before, with substance use disorder, which is another health disparity, and for things like other mental illnesses where people aren't comfortable having others know that they have it. So several years ago, my colleagues and I published this paper, called Mindless Computing. Now, this was about interventions and feedback mechanisms, but these are the modified principles from that are meant to be focused more on the actual sensing mechanism as opposed to feedback. So the first is reflexive, not reflective. So the input should be mindless. It's got to be easy to use, and I'll show you how we did that in the next project with Puff Packet. They shouldn't have to reflect on their behavior as they do in self-report. They should be able to get that input automatically. Triggers should be the main focus for design of designers for technologies. And this can be literal, like in substance use disorder, we can monitor the use and presence of substances, or figurative, like people, places, and things that are around someone when they are getting sick or when they are using a substance. And I'll talk a bit more about that in the next project. So this should work in parallel with their daily lives. They should not have to do another task. So most of our technologies right now are what we would call reflective. So you shouldn't have to stop and look at something or pick something up and do something else to sense it. It should work while you're doing stuff. And users also can change their behaviors without being aware of it. So asking a user about how they're feeling and stuff like that isn't reliable. Self-report is not reliable. It's particularly bad in substance use disorder because of stigma, denial, and intoxication. We have to leverage technology for new ground truths. All right, so now I'm going to get into more on health disparities. I'm not doing it on time. Substance use disorder. So this is a huge problem. It affects 1 in 12 people in the U.S. which have or have had substance use disorder. That's over 21.5 million currently. battle substance use disorder, and only 10% get treatment. Of that 10%, on average, 50% of them relapse in treatment or recovery. An eighth of them struggle with both alcohol and drug use, and 8 million have comorbid mental health disorders. This led to over 100,000 deaths between April 2020 and 2021. This is 30,000 more than the year prior. I'll let you guess why. But just to put this in perspective, at the peak of the AIDS epidemic back in 1995, there were 42,000 deaths, I believe. So this is almost 250% higher. So there's even inequity within substance use disorder. By psychiatric disorders, that's 44% purchase of all cigarettes. More than half people with substance use disorder and a comorbid mental disorder are men, and over 2 million middle and high school students currently use e-cigarettes, and 85% report using flavored products. So let's look at this ecological model again, but now specifically to substance use disorder. So we can look at this through stigmas and the ideologies. We can think about the people they're around, who's their sponsor, who's their family. We can look about what's going on in their life. And all these things are important to know because substance use disorder is very cyclic. You increase use because your tolerance increases and your dependence increases simultaneously. This worsens withdrawal. Your hangovers will get worse until you're actually getting physically very sick. Then this causes an increase in cravings because at this point you're getting to where this is the only thing that makes you feel good, which increases use, increases tolerance, worsens withdrawal, etc. Makes it very difficult. And just to understand a bit about cravings, that these are both physical and mental phenomenon. That could be unconditioned or conditioned. Unconditioned would be when you have the substance in front of you, and conditioned would be when you, say, walk by a bar that's one of your favorite places to drink. So to combat some of this problem with this disparity in substance use disorder, we created a puff packet. This is all open source on GitHub. Puff packet is a device that attaches to electronic cigarettes and monitors use through monitoring the electricity in the devices. So it captures not only puffing, duration, frequency, and then the intervals, but also location and activity. How does it work? It works by, well, two ways. One by monitoring voltage and the other by monitoring current. And basically, if you think about it, your inhalation is dependent on the voltage heating up, the current heating up the heating coil. So these two things, the heating coil's power and your breathing inhalation, are directly correlated. So once that happens, it causes an interrupt and wakes up, sends all the puffing information over to the smartphone. And this is what it looks like. Here you can see both models. You see long puff, short puff, long puff. And to test this, well, of course, we didn't sit around and take hundreds of puffs of e-cigarettes. We made a puffing robot, PuffBot. It proved that it works really well with a 50 millisecond absolute error. And what does all the data look like? It looks really interesting. This allows us to get much more intuition about how people are using e-cigarettes and better equips us to help them stop using it. So there you can see Cornell Ithaca, where Puff Packet was. Bill and Melinda Gates Hall is where the majority of the puffing went. We also did an 8-day study with one participant to see them using it, and you can see they mostly used it when they were driving or walking or stationary, not while they're cycling. So you can do a lot of different analyses with this. You're going to understand how puffs are distributed throughout the day, throughout the week. This is a very important metrics in cigarette analysis, and we didn't have such a thing for something that's less discrete as puffing on an e-cigarette. So the time to puff is an important metric. For example, if you can time to first puff, actually. So if you could increase the time before their first puff, then you increase the chances of them not puffing at all. So we've also recreated the PuffBot to a quick little puffer, just for your quick test. And then for the real big studies, we made Puff Daddy. Puff Daddy likes to chief on cigarettes and monitors volumetric flow and pressure. And the reason we did that is because with diaphragm pumps and PuffBot, you always get this cyclic noise, where with Puff Daddy, you get much more lung-like behavior. And to conclude, there's a picture of a Lego guy banging on a phone. All right. Thanks, everyone.
Awesome. This is all such important work, Alex. Thank you so much. We're gonna skip your Q&A and hope that you have time to join people in Discord for your Q&A just to win back a little bit of time. Trying to stay on schedule. Thank you so much. Next up, we're gonna have Andy and Kitty Quitmeyer, who are gonna show us open source toys for endangered animals. Hi. You're muted.
Hello, can you hear us okay? Cool. I'm gonna share a screen. We got this going on. Can you see a sun bear licking some tubes and stuff? I'm gonna assume yes. I haven't seen any chats that say we can't hear you. Okay, perfect. So hey, this is I'm Andy.
I'm Kitty.
Yeah, there's more visual references if you don't know who we are, because there's lots of animals you might get us confused with. That's Lupe the agouti, and this is Valencia the tapir. So we have a special guest star, Kitty's here, joining us today, who will be able to answer some questions at the end, because she's my partner, and we both work at Dynalab, and we've both been working with these really cool animals, and it's cool she gets to be here for this talk. We're both a little bit sleepy because we just we're on a layover in Atlanta from a big scouting trip to Sri Lanka. And so we're kind of out of it, but jet lagged, but it'll be good. So the main thing that we want to talk with you all about today is making toys for fun endangered animals. This is Valencia. She's eating this pineapple that's on a string. Can you all see, does the video play? I'm curious if the video plays or if you're just seeing a static image. Sometimes it does that. Okay, perfect. So I'll make sure to, because we got lots of fun, silly videos of our nice, goofy friends playing around with toys that we made. And so the talk today will be about making toys, making open source toys that we can share with other people who work with animals that are engineered for helping out these nice creatures. This talk isn't going to be as much about like showing you like, oh, here's what we did and here's how cool it is. It's kind of more of a call to arms, a request for other people working in open source hardware and software that this is a fun thing that you can do if you're interested. So a little more background on what we do. This is where we're usually based. This is Gamboa, Panama, right in the middle of Panama, right in the middle of the Panama Canal, and next to some really cool, amazing forest around there. And we have a little lab that we call Digital Naturalism Laboratories, or Dynalab for short. And we focus on making art and technology for interacting with nature and trying to do as much of this in the wild as we can, in kind of non-human controlled spaces where the animals that we try to work with, or plants or other living creatures, tend to live and exist. Our space is pretty basic. We have a house that we've converted into like a construction shop with 3D printers, laser cutters, prototyping workshops, electronics labs, a little art science gallery, and we focus on trying to, because we're kind of remote, we're in the jungle, and it's hard to get materials there. So that helps extra put an emphasis on trying to upcycle all the prototyping materials that we use. We try to actually use them from the community's garbage, and we shred them or 3D print them with pellet style printers. And so you've seen several other people doing cool different plastic works already at this event. And so the two main things that we tend to do at our lab is, one, help field biologists, and two, help animal rescues. So first, what does it mean we're trying to help out field biologists? Well, we do like design and consulting work. This was old computer vision work, working with ants, checking out who the ants are gossiping with at the watering hole. Other examples, this is an open source 360-degree camera trap. So most camera traps, you have one field of view. But what if you want to know about the agoutis who are behind the camera trap? So you could hack 360-degree cameras for checking out things like that. We also do field site maintenance. There's lots of field biologists who've come to lots of these really scientifically important field sites around where we live in Gamboa, Panama. But unfortunately, many of their field sites have fallen into non-maintenance from organizations that used to take care of them but don't as much. And so we go out there and try to help the field biologist keep some of these spaces accessible. We also try to sponsor Spanish classes and other community events to try to bring a lot of visiting scientific researchers from all over the world in closer contact with people in the community around us. We offer long and short-term residencies. We've done field courses out here. Some other things that we tend to focus on is making like mobile maker spaces. This is a project where we made a floating maker space in the Philippines called the Boat Lab. We've also done things called hiking hacks, where it's kind of like a mobile hackathon where we join up with a field biologist in their field sites and actually try to carry all of our tools and convert the workspace into a place where we can interact with nature and do things in different ways. And perhaps one of the biggest things that we do is Dynacon, the Digital Naturalism Conference. And this is a big event where we have over 100 people from all around the world who the goal is to have them living and working together in a semi-remote location for an extended amount of time, usually like 4 to 6 weeks, with the entire goal of figuring out new ways of interacting with nature. These can be high-tech ways, these can be low-tech ways, these can be fun jungle robots that climb up trees. But one of the key components of it is that everything that everyone does is documented and shared and reviewed by our own community and then published freely and openly. So all the projects are all shared completely freely on our websites and stuff. And we've had a Dynacon in Thailand, a Dynacon in Panama, and I've been lucky enough that 2 of the other chairs of Dynacon this year are Lee and Sid, who are also running this event right now. So that's super cool. And so we're actually going to have one in Batticaloa, Sri Lanka in July. So that's actually what we just came back from doing. And so that's a little bit back about all the other stuff that we do at Dynalab and where we want to try to interact with things in nature, but we also do a little bit of interacting with things that aren't as much in nature for different reasons. So we tend to work with this group called the APPC, which is a really wonderful, nice conservation organization. They rehab injured animals. The goal is to release all the animals after we rehabilitate them right back into the wild. The organization's over 10 years old. It's in Gamboa. They've rehabbed thousands of sloths. And we've released generally about 95% of the animals. They're kind of pretty awesome. They're kind of squatting in a lot of abandoned buildings at this hotel, just leaves in kind of disrepair. And so there's a tapir in just the backyard of a house that's been kind of fenced off. There's all kinds of different animals there. This is, again, the tapir. Here's some of our design clients. There's Valencia the tapir, Lucio the spider monkey, Inez the ocelot, and many more. There's which one's that? I think that's Pino, the tree porcupine. And so we work with a lot of these animals, but why open hardware for animal rescues? Well, there's a big need for it. Animal rescues have really limited resources. I mean, most of this whole animal rescue we're working with is just going by on like donations. Yeah, just strings and threads, just trying to get by. And usually the animal rescues are just trying to, they're prioritizing helping these animals. These animals will be horribly injured or terrible things will happen to them. And so usually it's more about like, we need to get this thing living and then be able to work with it. But unfortunately, some animals are so injured, they're never, even if they're kind of stabilized, they're never able to fully leave the animal rescue. And so that means that they have to stay there for a really long time. And unfortunately, enrichment, trying to keep them occupied while they're also stuck there, potentially for the rest of their lives, is usually a last priority because everyone's so busy at the animal rescue. The other thing, too, is everyone at Animal Rescues is generally non-experts. When we first started working at this animal rescue, we didn't know anything about tapirs. We were not tapir experts who started working with a tapir. We've had to like figure a lot of this stuff out by ourselves. And this is pretty much the same with most people who are working at animal rescues. Plus, there might be some people who are experts at something, but because you're not in charge of, like maybe I'm really good at sloths, but now we have a, 400-pound tapir we have to take care of. It's a little bit different. The other reasons the open hardware community should care about this is because it's fun. You all, in general, if you're here, you like to build things and play with things and test them out. And building things for a lot of these endangered animals, it can be kind of like you have a lot of freedom to play and experiment. You're not going to get judged if it looks kind of funky. You might get judged a little bit. When I made one tapir toy, it looked very ugly, but the tapir loves it. There's lots of applications for high and low tech kind of things. I mean, you saw there was a pineapple hanging on a string. There's no Arduinos involved with that at all, but it's still an effective type of hardware that you can make and also share different ideas with other people who want to build them. For instance, what type of string to wear? What are you building the base out of? What types of pineapples are you feeding to what types of animals? All this information can be documented and shared with other people. It's also a good way to escape, kind of anthropomorphism. You can take a break from thinking about how do things work for people and what do people want to do, and embrace the really weird challenge of like, well, what's interesting for a tapir versus, me, or versus a monkey, or versus an ocelot. And so the final thing is it's a really badass challenge because there are a million ways everything can go wrong. You have to weatherproof things. You have to tapir-proof things. You have to make it. It's very, very tricky. So let's get into more specifics about designing for captivity and enrichment. So here's an example of some otters playing a keyboard. Let's take a step back and just talk about captivity in general. There's many reasons that us humans are keeping non-human living creatures trapped somewhere, potentially against their will. One reason is we want to eat them. We're like, there's that chicken. I'm going to put it in a cage until it's big and then I can eat it. Other things can be for entertainment. Oh, we caught this whale or porpoise and we want to make it do backflips and then I'll clap and we make a bunch of money off of it. But there's other reasons too. For instance, scientists. A lot of scientists. This is one of our residents at Dynalab right now, Jorge, who studies birds in Panama, and he's caught an arisari that they put tags on and monitor their movements in order to help track them for conservation and other scientific data. And then the final reason that you might have animals in captivity is because they might get hurt or they're already hurt. Or you're helping protect them. For instance, we have Lucio the spider monkey. He was somebody's pet, right? 25 minutes left?
Yeah.
Perfect. And so like Lucio, for instance, was somebody's pet and chained to like a fence for like
a tree.
Yeah, a tree for like 5 or 10 years. It was super sad. But now we've rescued him. Lucio is healthy, and a lot of people ask us, why not just release Lucio back in the wild? Well, the problem is that Lucio is a spider monkey, and they work in large social groups. And if they don't have these social groups and we just toss them into the forest, chances are other primates will probably kill him. And so it's very sad, but Lucio has to kind of remain with us indefinitely. And so part of our job can be to try to make their welfare better. And so there's a group called the Shape of Enrichment that talks about different ways of doing enrichment, primarily focused at zoos, but all these are applicable to any animal that's in captivity. And they list some guidelines for what are the rights of an animal in captivity. There's freedom from hunger and thirst, discomfort, pain, fear, and the freedom to express normal patterns of behavior. And so that can kind of help us think about normal patterns of behavior are things that they can't really get because they can't just roam around wherever they would normally be in the normal environment. But we can try to recreate some of these things through toys and enrichment things that help improve their mental health, which then also helps improve their physical health. And so we can do, I can talk about some quick design guidelines we've come up with for enrichment in general. We'll start with the keepers and the animals, because we need to think about both of these. So for instance, the keeper design guidelines, you need to think about safety. You might have these wonderful sloths and everyone's like, oh my God, you hang out with these sloths and oh my gosh, can they get any cuter? Look at those three-toed sloths that Kitty's feeding. This one's just drinking some milk. It's a sweet little baby. That one's eating a flower. What? Oh my gosh, so nice. But sometimes they bite you. And so Kitty actually got a really terrible bite. These two-toed sloths have huge teeth. Fangs.
Big sharp fangs.
Blood everywhere. She has a scar right now. She's got pretty bad ass.
I always will have that scar.
Yeah. And that was because there was a sloth, that there was other external factors outside when we were handling them normally. This sloth was suddenly stressed out and actually bit her. And so we need to think about the safety of the keepers whenever we're making any of these toys, that, you know, they're not going to be endangered by trying to use it or giving it to them. All the toys need to be maintainable. You need to think about, like, so for instance, this is the ocelot's cage. It's basically a giant cat. And a giant cat has a giant litter box. And so how do we, you know, have something that, you know, recreates ways that they would normally go to the bathroom, but we can clean up easily? The answer to that is kind of, yeah, giant litter box, lots of sand that we rake, and you have kind of a Zen garden kind of deal. And so safety for the keeper and maintenance, you know, being able to clean your things are two of the key guidelines for the keeper side. But then for the animal side, you can think about, we need three things. We need the toys to be interesting. They need to be tough. They need to be durable, and they need to be also safe for the animals. In terms of interesting, it's tricky. What makes something interesting for a wild animal that's very unlike us? In biology, they have something called the 4 Fs, which are fighting, fleeing, feeding, and mating. And then in enrichment for like zoos and stuff, they talk about maybe the 5 Fs, which are like feeding, fighting and fleeing. You can call that play. Friends, which is like social interaction, figuring things out, or also the final F, mating again. And so examples of this are, feeding is one of the most common ones you'll see in zoos and animal rescues. You give the animal something they like and they munch it. And, you know, this is a triggerfish hitting something. Then there's also fighting and fleeing. This is kind of like things that try to like spark their interest in other ways. This is like a cat playing with some cool toy. Then there's also the friends aspect, which mainly you need to think about whether things are social. Some things are very social, like orangutans, and you want to design them to collaborate or do things together. Other animals are very unsocial, like red pandas that mostly want to be by themselves. You can even have companion animals as enrichment. So for instance, Valencia the tapir used to be very grumpy when she was first at the animal rescue and would smash out of her pen all the time and go roaming around Gamboa. But then they found her a best friend named Lupe, who's an agouti, and they fell in love. And now they both kind of like walk around and they live together and they have a nice time together. So it's not even necessarily a technology per se, but, you know, knowing about what kind of things you might be able to pair up with can be surprising. And then, of course, there's mating. You can learn about that if you go to Wikipedia's Panda Pornography webpage. But I'll go through this kind of quickly. But when you're designing these things, you can think about what are the senses that they're using. What types of habitats are they using? Are you trying to recreate the habitat, or are you trying to give a really novel stimuli? That's like nothing they've seen before, but the animal still wants to engage with and interact with. And then you can also think about different types of puzzles. This was one that we actually built with the Singapore Zoo and some of my awesome students when I was a professor. This was a puzzle for sun bears. It would use little motors to squirt honey in different tubes and capacitive touch sensors to sense the tongue of the sun bear so that it would always change where the honey was squirting. So it would always have to keep looking around. You also need to think about toughness, because you can build a really nice little tippy seesaw thing for your tapir that's bolted into the ground with big sticks of rebar, and you'll come and someday she'll just totally knock it over for no reason after it's been working for 4 months. She'll also decide she wants to chew through some big part of it for no reason, even though she leaves the other parts alone. So you have to learn a lot about these things. You also need to think about safety. If the animal can break something and accidentally eat it, it can be very bad for them. So like we use a lot of things that are super durable, like old tires or recycled HDPE. What can you do? I'm going to wrap up real quick. If you make an idea, let us know and we can try to help test it out. You can also volunteer for a local animal rescue and help make fun toys. And you can document and share. We have all of our documentation at richmond.tech, and that's us. Yeah.
It's incredible. It's so amazingly cute and valuable. There's a ton of people who just want to know more about all the animals that you shared because, you don't run into them all the time, unlike you. So maybe you can hop into Discord as you have been earlier. Thank you, Kitty. Thank you, Andy. And next up, we're going to have Catherine Wehe and Michelle Langhammer, who are going to teach us more about building our own photovoltaic energy systems.
Yeah, thank you. Hello, everyone. My name is Michelle. I will just quickly share my screen. Katrin is also here with me. Zack. Hope it will work out. So now you should see my screen. I hope so. Yes. So, hello everyone. Here, I'll present you the LibraSolar project and a little bit of the history behind it and the roadmap till now, how the project was developed and how the project is run till now and how it's running now. So our aim is how to enable anyone to build their own renewable energy system. For introduction, who is behind the LibraSolar project? You see here Martin Jäger. He's also here in the Discord channel. So if you got a question, he's also here. He's the main founder and main developer behind the LibraSolar project, and also the company funded behind that, so the LibraSolar technology. It's Katrin. Katrin and I, we studied together automation systems. So we jumped in the project in 2017. So these are the people behind the project. What is the LibraSolar project? So maybe a quick introduction and what we want to share with you today. So a little overview in 3 main clusters. So the LibraSolar project, open source building blocks for DC energy systems. So the main blocks are open hardware and software components. So the hardware components contains of solar charger, so basically DC-DC converters. Contains of a battery management system if you're using lithium-ion battery types for energy storage. Contains communication gateways, so also hardware to extract data or to control data within the solar charger components or the battery management, and the software part for sure, so the matching firmware for all the hardware components. But it's not just only hardware and software in this project, but also open educational resources. So we took also this project and developed OER content, so teaching and learning materials, how to develop and to produce these components, and therefore also to develop step-by-step guidelines. And for sure, in open source hardware, the content of a community-based development. So therefore, we have also a forum where we can exchange on specific topics and also the things behind feedback and requirement management. So this is a quick overview of the main components within this project. And to see what actually you can build off, we have this little slide to see what kind of architecture you can build off with these building blocks. So you see here like a DC energy system. So the aim is to build up small-scaled DC energy systems containing of renewable energy sources, for example, photovoltaic. But you could also use like wind power if you change a little bit the firmware behind the charger. And as I said, also like lithium-ion batteries for using battery management systems, and all connected in a grid, in a DC grid, to operate your loads, mainly your DC loads. But you can for sure also modularly add an inverter if you want to, if you want to power AC loads. But AC components is not yet part of the LibraSolar project. So everything running on AC, you would now, in the current status, you could not use the LibraSolar components. Maybe some key facts behind it. The performance we aim is like on like I said, a small scale system. So we are here in 12 till 48 voltage DC. So 12 volt, like the standard plump batteries, what you use, and 48 volt if you want really like to have multiple nodes of sources and storages and loads. Therefore, it's better to scale up the voltage till 48. And it's like up to 2 kilowatt what you can supply with. So like a little bit of hard facts. Communication standards, we also like use like LoRaWAN, Wi-Fi, CAN bus. Therefore, you can also like extend with different modules, different communication modules. Yes, so this is like an overall architecture layout, what you can build up with. To show a little bit a roadmap. So what was the beginning of the project and where is it now? We try to project this in a roadmap. So it all started 2015 with a little Arduino based, not just a charge controller, but it was like a PCB combined with a charge controller and a battery management system. So this was like the first hardware developed based on Arduino, already placed on GitHub, where it all started. And then we made the road. So we extended, or we differentiated the MPPT, so the charge component and the battery management system for modularity, which is also a key fact behind open source hardware. And yeah, therefore there was different development steps. So for example, in the charge controller, we had like up to 24 voltage, 20 ampere. Then we scaled it down to 10 ampere. Then we go again a little bit more up to 20 ampere. We had also like for mounting rails components. So different modules developed. The same on the BMS side. Like we had a big BMS with 15 cells where you can connect with. Then we also scaled it down to 5 cells, to 8 cells. And now the current status, the new BMS, which is developed, which we will also present in the next slides, is like up to 16 cells, what you can input, like where you can connect on the battery management system. On the firmware side was also interesting. Like I said, we started with Arduino, so really a low entry point when you just start programming, starting writing software. Arduino is really a good basement for this. Then we changed the microcontroller type to a STM32 microcontroller. Therefore, we use the ARMBed firmware, and now like changing it to the Sapphire platform, like for reasons, for example, like the Sapphire platform is a community-driven, also open source platform. Also, like big companies now investing in this platform, for example, Intel, and therefore, yeah, at the moment, like we really place the firmware and the platform on the Sapphire part. Documentation, like I said, GitHub, we used Markdown. We tried out different static site generator for our documentation, like Jekyll. Now we are on ViewPress. Yes, so this was a little bit the roadmap on this side. To give an overview on the charge controller, so what is the technical key facts on the charge controller? For sure, we have the power terminals to connect solar battery and the load. We have a UX connector. This is, for example, also with Olimex. You have here different modules where you can extend like different communication modules, displays, etc., where you can use the UX connector. We have, like I said, the Sapphire project running on the microcontroller. We have Kicad as a tool chain for the development. Like also the first hardware was designed with Eagle, but we saw also the power of open source software, of open source software tool chain behind it. So therefore we changed on Kicad. And yeah, also for communication is like a CAN bus. So the aim behind is to have a masterless communication in this network, and also to interconnect it with the gateway. So this like a little bit of facts behind the charge controller. And now the current development is like our battery management system founded by the N-Access Foundation. So use case is really like also off-grid applications. It's a community-driven development, so you're really here free to participate on the development here. And yeah, like maybe also some of you know, we have here chip shortage. So therefore, we try here to have 2 microcontroller options to overcome the chip shortage. Yeah. So this is from the technical side. What are the applications? It's like, yeah, mainly also the impact we see in the global south, so that people can use this hardware to build up their own off-grid systems. For example, we made here some research projects in India where we built like solar home systems, and also in Africa where we built up a grid. So really like field testing in this area. Yeah, so this was like for my part on a technical roadmap to show you a little bit the development behind it. And now Katrin is gonna present you the educational part we have here in this project. I'm gonna stand up.
Yeah, let's just quickly switch sides. So, I mean, for sure, many of you are developers themselves, so you know, if you know every screw and every resistor of your project, it's really easy for you to build it on your own or build the different prototypes, different versions. It's a different thing if you actually, as an expert, as someone who already built something, tries to build a different project. And even if you have access to all the schematics, to the BOM, to the software, to the and have the knowledge, even then it's quite difficult. And now try to imagine someone who has never ordered a PCB, who has never soldered something, and who has never I don't know, have seen an aluminum profile or something. So this is a really, really steep learning curve for them, and some may be thrown off and I don't know, never build it. And I think there are 2 problems in general with open source hardware projects. One is the more complex the project gets, the more knowledge is needed. You need to find different sources to gather this knowledge, to make yourself acquainted with all the tools and terms and whatever. And then also when many parts are involved in a project, it's not very clear. You don't have a good overview. You don't need know what tools do you actually need, the order of steps, what time is required, what amount of time is required to build it. So these are quite a lot of problems, and this is why we, as a group, decided to create some kind of instruction manual on open educational resource. Yeah, well, and we also got some funding, so this also helped with this. We got the funding from the Hamburg Open Online University. It's like a collaboration, like a roof organization, or some between different universities in Hamburg, and they try to support the creation of open educational resources. In really short, open educational resources, they help you to learn, to teach, and to research. They are learning, teaching, research material. They are freely accessible, openly licensed, Creative Commons license most commonly. And this is really important. They are revisable. You can change them. You can add to it. You can remix them. You can use them with your own materials. This all is free. This all is available. So it started actually out in 2016 as we were a group of students. And a little bit like Jerry Devos said in his talk, we were a little bit frustrated that the concept of open source was not a topic at all in our university education. So we wanted to bring this to educate ourselves, to use open source hardware, use open source software, and just to try it out. And yeah, so this is why we started the student group Collective Open Source Hardware. And we also wanted to build upon Martin Jäger's work and use his MPPT, his electronic parts, his PCBs, and build a whole system out of it, the so-called solar box. So this is the solar box. There already was a solar box made by Open Source Ecology. It was all totally open source hardware. But we adapted it. So we used Martin Jäger's MPPT and the battery management system, and then we built our own prototype on the right. So this is basically the box we built and that you also can build in some former iteration. Yeah, so we developed an OER, an open educational OER, and an open educational resource. And basically it consists of two parts, some preparation part where you get to know the tools and the environment, get to know about the project, read stuff about it, then you order stuff. And then, yeah, you gather possibly in a makerspace on a fab lab because, well, most makerspaces actually have all the tools required to build this, because not everyone is such a geek that has a garage full of nice stuff around. So yeah, so good place to start would be if you never made anything, if you're not a maker, go to a local fab lab, a makerspace, gather some friends, because building stuff with friends is always more fun than alone. And yeah, follow our roadmap, follow our manual that we at this point have not yet written, but we wanted to write. And so for the electrical part, we laid out all the different steps you need to build your PCB, and also for the mechanical part. So the mounting, the case, how to assemble the case, using readily available materials, and providing all the schematics, also the wiring, the electric, and so on. And actually, during the process of creating our open educational resources, some people actually asked us, yeah, are you really sure that people who are not experts actually will be able to build such a complex system? And well, what we always said is, yeah, when you think about it, people all around are building pretty complex stuff without being an expert, only using manuals. And yeah, they use it by going to IKEA and buying stuff and building it there. So this is actually what we did. So we laid out our roadmap. We laid out the basic construct of this instruction manual, and then we tried it out ourselves. So we were our own test dummies, and we got together. Yeah, we ordered stuff. Then we got together in a makerspace, in a local makerspace, the fabulous St. Pauli. We met up and started to build stuff, and it actually worked. So this was our outcome. So we were no expert at all, of course. Yeah, we were students, but we have never. For example, I have not soldered before, so I have not mounted something in an aluminum profile. So yeah, but what we also learned of this is, if you actually want to collaborate, if you actually want to participate in the project, this is not enough. So an instruction manual is not enough. You need to have the basic knowledge. You need to have the foundation. So we added, we got a second funding round, and we added to it a lot of educational resources. So you can learn on our website, learn.libre.solar. Link will be provided in our Discord channel. Well, you can, you can look it up and read a lot about embedded systems, about solar, about battery storage, about power systems. So a lot of information was gathered there. LibreSolar is an interdisciplinary collaboration. There are many participants involved. This is what we always try to involve other communities, educational institutions, and so on. And our lessons learned definitely are provide guidelines for new contributors. For example, coding style guidelines, so it makes pull requests way easier. Use Git-based platforms. Use Markdown for documentation, so people can actually easily add stuff and write their own annotations and enhance upon your educational resources. And also release early, release often. Even if it's not perfect at the in the perfect state, release it. Make sure to mark it with badges so people know, okay, so this is not the perfect stage, but so these are definitely our lessons learned if you want to create your own educational resource. And we are always happy to get in contact to help collaborate.
Awesome. This has been really great. This is a whole world of open photovoltaic opportunities. Maybe just one very quick high-level question, because we're a little bit behind in the schedule, but you guys work with high energy densities, and so there's like unique safety challenges involved with that. And are there any resources you can point everyone to just to think about safety when dealing with these high energy densities in open source?
Actually, when using 12-volt, the 12-volt DC system, it's really safe. So there's actually not that. I mean, you can burn yourself by short-cutting stuff always, but actually, this kind of, like just handling these kind of voltages, it's DC voltage, right? So handling these kind of voltages is really safe.
That's great. All right, reassuring. All right, well, thank you so much, Catherine and Michelle, and also Martin, who is in the chat. If you guys have, there's many detailed questions for you, and so for following up, thanks a lot. Next up, we're going to have Anuradha Reddy, who's going to talk us about naughty hardware, talking about crochet as a medium. Hi, Anu.
Hello. Let me share my screen. Is my second screen visible? All right. I think my screen is visible now. Can everyone hear me? Yes? Okay. All right. Sorry for the delay. Thank you, everyone. So let's just begin. I am Anuradha Reddy. I am a design researcher, so I'm a postdoc researcher in the field of interaction design, and I live in Sweden, and I work at Malmö University. And I also teach. I've been teaching for 6 years now, and I also make things. The things that I make are both as a part of my research and also things that I make outside of my work. But recently, these kind of worlds have been colliding, and I've come to start making things that are naughty, but also naughty, like playful. So the things that I make are like these. They look like something like this. And so in this presentation, I'll talk about these 3 designs that I've made and that I have in the past, and I have been able to certify them as open source hardware. What brings these three designs together is in this little Sierpinski triangle of mine is yarn, which is my main material, crochet being my medium, and my approach being computational thinking. And I will talk about all three of them. Let's start with yarn. So my first kind of provocation is that yarn is hardware, and to kind of allude to what Ashley Jane Lewis said in the keynote, that we need to learn from our past, right? So let's look at two examples from our history. So the first example I want to bring, or the first instance I want to bring up, is the time when NASA brought women into the labor workforce for sending software for the NASA space missions, like Apollo space missions, and these were called the community of women were called little old ladies, and they were brought into the factories because they had really great skills for weaving. The other example is the Navajo carpet weaving community, where Fairchild Semiconductors, this industries, had created a plant in Shiprock in Mexico, and they also brought these women into the workforce because they wanted their expert weaving skills. And if you can see in the image, you can see the resemblance between the carpet weaving, the kind of knowledge and the patterns that they kind of like that the community had, were directly kind of printed on what we call hardware or circuit boards today. So you can see that how what we call hardware is that we are deeply indebted to the kind of knowledge and our understanding of it depends on our understanding of yarn. So the other provocation I want to bring up is that yarn is programmable. And here I want to shout out to a physicist, Dr. Elisabetta Matsumoto. She talks about how knitting is coding and that yarn is programmable. So what she says is that with every stitch that you make, you can actually exploit the mathematical and mechanical properties of yarn. You can take advantage of its material. So she uses knot theory to kind of understand biologically inspired engineering and mathematics. And so what she says is that you can encode certain kinds of logic and information and ideas by using certain kinds of knots, right? And she also says something that knitting or working with yarn is also very similar to like using binaries, ones and zeros, but it also goes beyond that in a way, because yarn can also do much more, more three-dimensional things. You can talk about the floofiness of yarn, which is kind of difficult to talk if you're talking only in binaries. But for now, let's just stay with the binaries, right? Because that's where we can get playful with it. So here we can see on the right, there's a sweater. This is called the SOS sweater by Dr. Kristen Haring. She talks about in her talk about media history. She talks about media history through an example of kind of translating two kinds of things, Morse code to binaries, right? So here you can see how she takes something that's written in Morse code into dots and dashes, converted into ons and offs, and into binaries, and into knits and pulls. So P is Perl and K is a knit. So the idea is that you can basically work with two different kind of systems, and the result can be really interesting. So for example, in the sweater, so in the center, along the center, you can see the SOS. When you ask a person who knows how to knit and you tell them this is actually a Morse code, they might say, no, this is a rib knit. And they say that this is exactly what we do. This is a rib knit. So you can see that actually our worlds, we are actually doing pretty much same things, but we don't actually talk to each other so much. So we don't realize the overlaps. And I think there is a lesson to be learned in thinking about our practices about hardware and programming in a very interdisciplinary fashion. And I think it can also lend to a better user experience. So what does this have to do with crochet, right? So I think crochet is different because crochet, it doesn't deal with binaries alone, right? It's actually a series of knots, different kinds of knots, and a crochet pattern looks very much like this. And I think crochet is interesting and challenging because there are no ones and zeros here. There is, for example, for weaving, you have weaving, like you have like the jacquard looms, some kind of automation there. For you have knitting machines and you have embroidery machines, but for crochet, it's just, you know, doing something repetitively with your hand, which is, I think, more challenging and also quite rewarding. And I think I feel it's like the closest you can come to 3D printing with your own hands, and it's otherwise popularly known as amigurumi, which is like about making toys, soft toys. But I mean, if you think about it in a different way, what we are doing is also 3D printing. And I think it's also very slow, it's repetitive, and it's therapeutic in a sense that it can also be deeply empowering. You can make interesting commentaries on something that's extremely digital, our priorities and values about efficiency and things being fast and so on. So I think it is a really, it really counters our needs for efficiency quite nicely. And yeah, and this is kind of what I call crafting computational thinking. So the idea is that you can take any two domains and try to remix them. So you can take any element that's from one domain and try to map it onto another domain. And hopefully when you do that, I mean, it is definitely challenging. Like you can take two domains that are very close to each other, say like knitting and crochet, or it can be really far apart. And the farther apart the domains are, the more difficult it becomes and the more challenging it becomes, but also very exciting, because when you do hit that sweet spot, it's actually quite a joyful and rewarding experience. And I will talk about the 3 projects where I think I hit some sweet spots. So the first is the resistor cushion, right? So resistor cushion combines 2 worlds. The first world is of yarn and the other one is of electronic components, particularly resistors. So in the yarn world, we have needles, we have, needles which are really sharp, which are pointy, and we have a solution for that, which is pin cushions, right? But in the electronic world, we also have things that are really pointy and sharp, but we don't have any place where we can put them on unless we put them back in that little box. So I created something called resistor cushions, also because both yarn and resistors have this color coding, or yarn can be put into different colors. And another reason why this is kind of interesting is because resistors can be really hard to see, especially if you're slightly visually impaired, or you're having trouble. So then you can also see it in a bigger size. So so this becomes a practical product that anybody can make and use. And the second project is the world of yarn combined with digital key encryption. So this project kind of reflects on our lives, where we are now losing physical objects, and we are more like doing kind of digital key recognitions with like facial recognition or like fingerprint recognition. So I kind of wanted to counter that through yarn. So I was basically inspired by a yarn called Crypto. And this crypto yarn is basically just a variegated yarn, right? Like it means a multicolored yarn. And I went back to what Dr. Matsumoto said, right? So with every stitch that you make, you can actually encode or encrypt a certain logic into a device. So and I knew that if I crocheted keys, like keys that are just amigurumi toy keys, each of them would actually be unique, because no 2 keys will be the same, because the yarn has a special colored pattern. And I knew that I could use that for my for any kind of security detection. So I used machine learning to kind of teach my machine to recognize these keys, and then later I ported it into a Raspberry Pi so I could securely create my own smart home security system, right? This is the second project. And the last project is the Internet of Towels. And in this project, it combines the world of yarn and lenticular images and QR codes. So lenticular techniques are basically illusion techniques. So today we see them in toys, like the toys that where if you tilt the toy, you can see a different image. And you can try out these kind of techniques in different mediums. So for example, you can make it in paper, you can make it in crochet or knitting. It's called shadow knitting or crochet. So I thought, what if I can hide a secret message in a crochet towel? So and then I kind of tried to do the lenticular technique in QR code. I made a QR code pattern on Microsoft Excel because, yeah, why not? And I crocheted this towel. It took me 30 days. And I'm probably not going to try it out again, but I would say it was a pretty interesting process. So this towel, when you look at it from the top, you don't see any kind of, it's kind of like an abstract pattern. When you tilt it, it's a QR code. And currently this QR code links back to a tutorial, links back to the documentation for how to make an Internet of Towels object. And once I finished this project, I also created a little bit of piece of code where anybody who wants to make this project can upload their own QR, and the code will automatically generate a pattern for you. Right. So these are my 3 projects, and I just wanted to kind of talk a little bit about my process of getting the certification, because I know that for a lot of people who produce circuit boards, I think there's a lot of precedence, about what kind of licenses to use and so on. But in my case, I kind of had to figure it out on my own, because I don't think I don't remember seeing any other project that used Yarn and wanted to be, called hardware. And it was a bit of an experiment for me. So I wanted to share a little bit of my process. So the first thing I would recommend, so let's say you did try some of these, like a process where you kind of try to, mix 2 domains, remix some kind of patterns, and you kind of hit that sweet spot and you think, okay, now I can, call this open source hardware, and I want to, get a certification. So the first thing I would recommend is to read the OSHWA community definition of what is open source hardware, because there you can get a lot of clarity of whether your, whatever you design, qualifies for it or not. And the second thing is that I would encourage you to try incorporating locally available materials. But in the case of Yarn, I think that's what makes it special, because you can go to any Yarn shop and get material, and you can be pretty sure that anywhere it will be available anywhere in the world, right? So that's kind of a fun thing about Yarn. And then you need to be able to choose an open source hardware license for your project, and OSHWA does provide you some approved hardware licenses. In my case, I used CERN OHL. And and also if you're using software, like for example, I use Teachable Machine, which is open source. So like I would recommend using open source as much as possible, open source software. And finally, you need to provide documentation online. It can be really anywhere. And this, I was a bit nervous in the beginning, because I'm not a GitHub user as such. And it was a bit of a barrier, like a entry barrier for me. So then I just posted my documentation on Medium, which is like a long format blog post sort of a thing. And the other thing is you need to grant an open source license for that documentation so other people can use and modify it. So and finally, I just wanted to end by saying, where would I go from here? So something that I've been working on recently and thinking about is trying to bridge a connection between open source hardware and intangible cultural heritage practices like folk arts and crafts, musical devices, instruments, dance, weaving, and braiding. And I want to do this because I think these kind of vernacular intangible practices you can find them everywhere in the world. And I think everyone in the world, almost it's kind of a universal thing, everyone will find a way to relate to them. So I think kind of finding a way to bridge these kind of worlds will bring what we would like to see, right, in the future: equity, diversity, and more connections, ecological connections to our practices. So yeah, thank you. Please follow me on Twitter if you're on Twitter. Yeah, I'll end here. Thank you.
Awesome. Thank you so much. This is incredible. Some people in the comments said, it's really not that crochet is 3D printing, but with yarn, because crochet came first. So 3D printing is crocheting, but with plastic.
Right.
People were wondering what you're up to next.
Like I said, right now I'm focusing on a particular craft form from South India. That's where I'm from. So trying to connect back to my roots and bringing open source hardware into it. So the particular, this time it's not crochet, it's embroidery. So it's called Banjara embroidery. If anyone's interested, hopefully, I think I have some stuff ready. to kind of work on. And yeah.
Everybody's super excited to see your stuff. So if you
Thank
have
you.
time to chat with them in Discord, I think all they want to see is more of your illustrations and pictures of your work.
Perfect. Thank you.
Thank you.
Yeah.
Next up, we're going to have our last short talk of the day. Kristen Lundgren is going to talk to us about how you can make antennas. Can pretty antennas be practical? Thank you, Kristen.
Thank you. All right. So I'm going to, my talk is about designing cute formal antennas. So I'm first going to start by saying where I came up with that term. In other fields, the term conformal means conformal optics or conformal antennas is an optic or an antenna that conforms to another function. For example, in aerodynamics, an airplane windshield would be a conformal optic because it has to first conform to keeping the airplane up in the air, to the aerodynamic properties of the machine, before also having the optical properties that the pilot can see out of it. So cute formal antennas conform to the purpose of being cute. And why not? So a little background, I started using open source software probably in the early 2000s, sort of seriously when I was in graduate school. I started with Star Office back in Solaris. And some years later, I learned about open hardware and was really intrigued by the concept. And I did a little bit of Arduino. I've done some little LED projects, but despite a background in electrical engineering, I'm really not a circuit designer. So I've kind of just been on the fringes of the open hardware community, but not really contributing very much until recently. This winter, I was exploring a software modeling tool for computational electromagnetics called MEEP that I had used back from my graduate work. And it now has a pretty newish Python interface. Back when I used it, it was only Scheme, which is a Lisp family of languages, very different. So I was exploring it, and I started wondering what else I could do with it besides the solar cell modeling I had done back then. And I started thinking, antennas. Why not antennas? This is an electromagnetic phenomena, an electromagnetic function. So I started playing with that idea, and I decided to see where I could go with that. And so, unfortunately, life has been interfering with my fun making hobbies. So this talk is going to be more of a process talk than a results talk. So let me share my screen with you. Come on. We're working on it. There we go. Entire screen share. So that should pop up in a second. Are you seeing my screen? Let's hope so. So here we go. So pretty antennas. Okay, there we are. Perfect. Just popped up on YouTube. Okay, so first I'm going to give a little bit of background about the ISM frequency band. Industrial, Scientific, and Medical. That's what ISM stands for. And it is an unlicensed band. Unlike, say, 90.5 megahertz, the FCC would have something to say if you started broadcasting a pirate radio station. But these bands, there are multiple frequency bands worldwide. Some of them are common across most countries or all countries, and some are country specific. And the ISM bands include the band I'm going to talk about, 2.4 to 2.5 gigahertz, which is where Wi-Fi is, which is where Bluetooth is. Your microwave oven actually works on that frequency. And other frequency bands cover RFID, things like garage door openers, other remotes, radio astronomy, medical devices. So these are things that you can use without having to get a license from the FCC or your local equivalent. So if you're going to design a cute antenna, where are you going to start? First, you need to figure out what your application is. If it's Wi-Fi or Bluetooth, then you know your frequency range is going to be 2.4 to 2.5 gigahertz. So you would say pick a center frequency of 2.45 gigahertz. Because in electromagnetics, the frequency directly informs the size of your geometry. You have to know what your frequency is or what your wavelength is to know how big you need to make your thing. So first you would start off with just a standard antenna, a nice little square microstrip antenna, which is also called a patch antenna. It looks like a little patch. So you start with that and figure out kind of what size you would make that. So for the patch size, you want it to be a half a wavelength. So I'm going to do a little tiny bit of math, figure out what my wavelength is. I've got the speed of light equals frequency times wavelength. 3 times 10 to the 8th equals 2.45 times 10 to the 9th. That gives you a lambda of about 12.25 centimeters. So you've got your wavelength. This is the wavelength of your Wi-Fi, your router. If you have a regular Wi-Fi, not your 5G, that's a different frequency. And so half a wavelength, the size of your patch is going to be about 6 centimeters. So you start with that information. And then you figure out, how am I going to feed this antenna? I need to get some energy from something, from my router, say, to this antenna. So you're going to use a little microstrip line. I'm going to flip back 2 slides. There's the microstrip transmission line, the skinny waveguide. I'll wait for that to show up for a sec. So you want to figure out what size you want that to be. Okay, there it is. Flipping back, and the size depends on what material your substrate or your circuit board is made out of, its dielectric constant, and the thickness of the material. And frequency is sort of folded in there because the dielectric constant of the material depends on frequency. So you're going to go to your board house, whether that's Osh Park or someone else, figure out what material they're using and look at the data sheet. It'll tell you what the dielectric constant is. And you use that. In almost all cases, your impedance you want is 50 ohms. That's a very, very standard in almost everything except I think cable. I think cable uses 75 still, but I could be wrong. And there's microstrip calculators online. You just pop in your dielectric constant and your thickness and your impedance that's desired, and it'll tell you exactly what to do. For this, it's about 2 millimeters. It's a pretty good size. So I'm going to talk about the workflow I've been working with, and this is all open source software. So to get started, we've already done the first thing. We've picked our frequency. We found the size that we're going to use for our patch antenna and our microstrip. Then we're going to figure out what cute antenna shape we want to draw. We're going to draw that up in FreeCAD. There's a lot of exporting and importing to get between different softwares, because of course everything works in a different format natively. So we export that as DXF, open that in another software, KLayout, which is more designed for 2-dimensional circuits. And you can have multiple layers in KLayout. And you export that as GDS2, open MEEP, the electromagnetic simulation tool I mentioned earlier, and import the GDS2 file into there. You can simulate the electric fields, and you can look at images to figure out what the electric fields are doing, what the reflection is. You can view those results in 3D in ParaView. You can also export them as PNGs and make some animated GIFs. Iterate through this process. And then finally, FreeCAD or KLayout will export Gerber files for you to have a board made. So now I'm going to actually show you some software, just so you have an idea of what all this stuff looks like other than just a list. So here's my heart-shaped antenna. And this is FreeCAD, 0.19 version. And you see you can rotate this in 3 dimensions. You can make a part. If you're not familiar with FreeCAD, it uses constraints to draw a sketch. You set the constraints, the radius, the distance, the horizontal, vertical, parallel. things like that. So here's my heart shape. So then I'm going to go to the next software in my workflow, and that is K-Layout. It's down here. Open up. And there we go. So I made it stepped, just so it has fewer vertices. It's a little easier to deal with. You don't have to do that. And K-Layout also allows you to draw. You can create a box or a polygon. If you don't want to work with FreeCAD, you can draw, or you can edit. Here, I'll just draw a triangle. Why not? There, now I added a triangle to my antenna. That's a terrible idea, but I did it. So then once I've done K-Layout, exported that, I go into Meep. I've got a Conda environment, an Anaconda, that I activate. I just copy and paste stuff in because I'm lazy and I like to see what comes out. It's more fun than just running a .py file. But here you go. You set up some geometries, and I've got links to all of these software at the end, and I'm happy to talk more with you in the channel about how this works. This isn't really a Meep tutorial. This is the most complicated piece of software, I would say. So import, get your layers, set your geometry, set your continuous source, set up a simulation, run it. Here's a file name, output the electric field, and that's pretty straightforward. And I'm going to show some of the output. Here's a 3D. I outputted a VTK file from Meep, and I'm going to do this nice and slowly so you can sort of watch it, but you can see. And you can see that this is actually a three-dimensional object. You can see there's a little bit of a height, and that is the thickness of the metal. So this is the antenna itself, which is metal. And there we go. Let's see if this is any good. And I'm clicking on a different view, and I changed the parameters, so I'm not going to worry about that. I won't make you sit through that. This is a powerful viewing program. It shows a lot. And so now I'm going to go back to the slides, show you a few more things, and that'll be good. Here we are. Whoops, come on. Okay, this is the workflow. So here's what the rectangular patch looked like in ParaView. Waiting for the slides to catch up. Sorry about that, a little bit of a delay. And here is the electric field propagating through, let's see, I'm gonna get my mouse back, through the heart-shaped antenna. It starts at the left where the source is in the left-hand picture. Then in the center picture, you can see the electric field is propagating down the line where the microstrip is. And then in the right-hand picture, you can see that it's underneath the heart. So this is a slice of the simulation in the center of the PCB, the dielectric material underneath the heart antenna. Okay. Back to the slideshow so you can see it a little bit better. And then I made a GIF. I'll let this run a couple of times. So this is an animation of what's happening. And I'll just let this catch up real quickly. Okay, there we go. And then finally, I'm going to talk about how I would test these antennas once I make the boards and get them back. So you would get an SMA connector, I would say, these frequencies from somewhere like mini circuits. They're pretty common. And I have a handheld spectrum analyzer from RF Explorer. It's a neat little guy. And so this one has two antennas. The longer antenna is for low frequencies, and the short antenna is for higher frequencies in the gigahertz range. So what you would do is you would take this little guy, and you take off the shorter antenna, just unscrew it, and then you would just quickly put your antenna on, whether it's your rectangular patch or your heart-shaped antenna, and then just kind of put the part of the board with the antenna on it facing your router, and you can see what the spectrum looks like. You can see where the frequency, where it's picking up, which frequency and which frequencies it's sort of ignoring. And then you can switch over to the Wi-Fi analysis view, which tells you which channel it's seeing. And it does have some software for, I think, Windows that you can look at in more detail. It's kind of interesting. And that way you can compare your cute antenna with a standard antenna. And you can tilt your antenna around and figure out which directions are best, which give you the best results, and which are lower gain. And the rest of these are just links. Here's a link to the software resources I've mentioned. And if you're interested in antennas or RF engineering, here are a couple of really good resources to get you started. Microwaves 101 has everything from antennas to waveguides to how everything works. And antenna theory is, as you might guess, focused on antennas. Here is my contact information. I will post some of the code and the results on GitHub once I have everything kind of packaged neatly. Please feel free to reach out to me. I love talking about this stuff. It's sort of the area that I ended up working in and just being passionate about. So I guess I want to conclude by saying I'd like to encourage everyone here to follow your interests and follow your passions. Make your own path. Do what interests you and intrigues you the most, and have fun. Thank you.
That's incredible. Thank you so much. This is really great. I really enjoyed also the live demo aspect of antenna design. Maybe one just short question, which is for people who want to get into this and are experimenting with simulating and then testing, can you offer any advice or encouragement or things that they should look out for when they're first getting started with going from what the numbers say should happen versus what actually happens with the PCB?
Iterating with your simulation. The one thing I didn't talk about here that is my next step in simulation is to do a reflection simulation. And I'm going to click back to one of my slides. Let me share my screen again real quick. To answer your question, allow. Okay, share. And I'm going to go back to this image. So you can see my mouse, I think, or you will in a second. So as the wave from the source travels down the microstrip line, it gets here to the patch antenna, and some of it reflects.
Isn't moving for me, but I get it, I think.
Okay, it will in a second. There's a little bit of a lag I'm seeing on the YouTube.
It takes a second for it to go to the YouTube, but I am seeing you in StreamYard.
Okay.
Maybe it doesn't share your mouse.
YouTube, but anyway. So some of the energy reflects off the patch and goes back towards the source. And you can set a plane in MEEP to measure that reflected energy. And you can take what the source is, subtract the energy that comes back, and it will give you a reflection curve, or in RF parlance, S11. S is for scattering matrix. 11 means from port 1 back around to port 1. And so you're going to get a dip at the frequency that your antenna is radiating best, because it's not reflecting much, it's radiating at that frequency. And that will help you tweak where your center frequency is.
Cool.
So I will.
Cool.
We'll post some
Yeah,
stuff
golden
on that when I
tips.
get it done, but that's what I would do next.
Well, awesome. There are people in the Discord clamoring for you to collaborate with Anu on an antenna design. So maybe if that's something you're up for, chat about it in there.
Yes, she's
Thank
great
you also
with
for being the last short
Kicad.
talk of our conference today. Next up, though, we have a panel, and our panel is going to be on the intersection of open hardware and health tech. We have a bunch of exciting panelists. We have Robert Viseur and Beneger Fali on open source hardware for hospital practices. We have Samuel McDermott on open source hardware for blood smearing devices. We have Robert Ella Reed on open source hardware for respiratory support devices. And we have our own amazing Claire Cassidy, who is our Open Hardware Summit Talks Chair, to moderate the panel. So thanks so much for joining us, everyone, and good luck on the panel.
You're muted, Claire.
Am I? Oh, okay. Can you hear me now? I was just saying that it's been a long day, and thank you, Nadia, for holding down the fort and doing an incredible job. And we are here trying to do a big, exciting panel for you all as the end of the day kind of celebration. And how we've organized this is we noticed that probably due to gestures broadly, there's several very incredible health projects in open source happening right now. So we wanted to gather those people together and see what happens. Each of them will be speaking individually, and so you'll get to hear about their projects, but then at the end, we will be taking projects generally, and they can chat with each other, and of course, you can chat in Discord during and after. So first up, we have Bernier and Robert, and apologies, I didn't take French. I probably butchered that. But their project is called Long-Term Benefits. What long-term benefits can the health sector take from projects developed in open hardware to face the health crisis? So they'll be talking to you about that. Thank you.
Thank you, Claire. Well, hi everyone. Thanks a lot to the Open Source Hardware Association for giving us the opportunity to present the results of our research work. So it's about the projects developed in open hardware to face the COVID-19 health crisis, and what can the health sector actually learn from these projects to face a future crisis. So this research is part of the Fabric à Rêve project. It's operated between France and the French and Dutch-speaking parts of Belgium with the subsidies of the European Commission's Interreg program. So the project aims at developing new technologies, making it possible to copy in 3D any metal structure at low cost. So our research focuses on the territory's adoption potential for small-scale manufacturing technologies, also the exploitation of open source and open hardware practices, and the organization of the ecosystems around these practices. So this is what actually led us to analyze the projects developed in open hardware by French and Belgian makers during the COVID-19 health crisis. So I worked on this research with Robert Viseur, and he's doctor and associate professor at the University of Mons in Belgium. So in terms of context, well, we are, so I can share my slide now? Yeah, okay. Let me just there we go. It just takes a few seconds. Can you see it? Okay. Can you see my slides? Okay. Can you hear me now? Yeah. And could you see my slides or?
Yes, we could see your
Okay.
slides beautifully.
Okay.
You did
Okay.
perfect.
Okay. I'll just reshare them because I have a hard time seeing you. Okay, there we go. Okay, so as I was saying, well, and as other presenters explained earlier, so back in March 2020, when the COVID-19 pandemic led to the confinement of populations worldwide, well, it also led to shortages of medical equipment, such as face shields, accessories like syringe pumps, for example, and also more complex medical equipment, such as respirators. The makers, therefore, they mobilized worldwide using open source technologies to produce this medical equipment, from 3D printable personal protective equipment to more complex open hardware devices, actually often retro-engineered. So the makers, they actually tried to fill the need as best as they could. And these makers, they structured in collective and communities, and they set up alternative local production capacities. They also produced a reusable, mostly open source, digital commons at international level, and allowing makers to share knowledge and optimize those developments. So beyond this one-time nature of the response, this mobilization has activated transdisciplinary networks of local actors where Fab Labs played a key role. So these makers, they coordinate.
Yeah. We actually, apologies, it took us a minute to catch on. We actually can't see your slides now if they're supposed to be showing. They were showing originally.
Okay.
Thanks for bearing with us.
Okay. Okay. There we go. Can you see them now?
Yes.
Okay, perfect.
Perfectly. Yep. Thank you.
Sorry about that. There we go. And so actually, so as I was saying, the makers, they coordinated through the digital platforms to communicate and collaborate, and they exchanged the open source design and the best practices through those digital platforms. And in our research, we actually refer to how the makers they organized to actually work through this development of medical equipment. So our research focuses on the coordination mechanism, the digital tools, and the different types of makers actually mobilized during the first wave of the pandemic to clarify how they activated transdisciplinary networks of local actors, including Fab Labs, to share design and knowledge and optimize medical equipment developments in open hardware. So research is linked and in line with the Open Hardware Summit's thematics as we address the open hardware applications and practices, the role of open hardware in medical device production, and also the use of open source to face unforeseen events and come out of it stronger. So when it comes to the state of the art, we refer to the makers movement popularized by Anderson. An important reference in what we do is the article published by Robert and Amel Charleux in Terminal about the makers' production of those personal protective equipment. And the third place is such as Fab Labs, also often played a central key role in these productions. And here we are referring to COND with a structure of 3 levels articulating from the top large organizations, that is the upper ground. I'll come to that later. Then in the middle, the Fab Labs, that is the middle ground. And then the makers at the bottom level, that is the underground. And they use digital platform, allowing the centralization of knowledge produced. And this all takes place in the same innovative open source appropriate technology mindset detailed by Joshua Pierce's papers. It is about improvising ingenious solutions for, well, under adverse situation, crisis, etc. And I'm referring here to the frugal type of engineering, using digital at the strict minimum, that is low tech, easily reproducible, that is open source, and universal in scope and non-commercial in purpose. So our methodology, we actually used a qualitative approach. It is structured in three complementary steps. So first, we observed the mobilized makers in France and Belgium. Then we analyzed the digital platforms they used, for example, Riot in France and Slack in Belgium. We focused on the textual content of the online discussions rooms they shared, and we extracted content and coded it to identify the most active persons to interviews. And so our third step consisted in interviewing these most active makers identified. They were either a part of fab labs, of hospitals, businesses, and with technical or non-technical profiles. So these makers communities, they used technologies and technological platforms to communicate through website and social network, also to share developments through messaging systems, and to make knowledge available through a storage tool such as a GitHub or a GitLab, for example. So here you can see that these platforms, they make it possible to actually compensate for the reduction of face-to-face contacts and to structure locally produced knowledge such as the sharing of designs. But also on the basis of designs proposed by more global platform. You can see them here on the left-hand side. So it's the case, for example, with the 3D printing companies such as Prisa Research or Dagoma or the MIT designs. Those were also used by makers around the world and shared through platforms. So these platforms, they have allowed, often at the initiative of core teams or animated by leaders or in fab labs or makers by themselves. And this allowed the distributed production at the underground, as I was explaining earlier. So you have citizens, students, pure, what we call pure makers. And those, the link with the institutional partners that are here showed as the upper ground, gathering hospitals, researcher, industries. The work between them was facilitated by the fab labs that you can see here in the middle ground. And the whole ecosystem functioning was key to successful open source equipment prototyping and production, and mainly to face also constraints such as homologations, technical constraints, etc. So for more complex devices, such as respirators, the design choices benefited on the one hand from pre-existing open source designs, and also on the other hand from the retro-engineering of commercialized machines. So they didn't start from scratch. The objective was to propose a good enough product with that would be inexpensive, simple, easy to produce locally, and also most important, repairable, with and also while they can preserve the patient's safety. So the projects we studied of varying complexity and maturity, they provide insights on the best practices to reach that level of development. So for simple equipment, the makers and the fab labs, they contribute to the resilience of territories by rapidly providing a distributed production capacity in the case of crisis. However, you have to be aware that their mobilization, they assumes the existence of a network of digital manufacturing third places, such as Fab Labs, as I was explaining earlier, and those are well established locally. Their activation when the risk of shortage has been anticipated, and also the pre-existence of digital collaborative platforms, because you could see like we showed the important role of the platforms. So for complex equipment, makers and Fab Lab, they could in the long term bring simplified designs that could be produced locally. So this also presupposes that sufficient expertise to make the right technical choice, also project management capabilities, and the application of standards are taken into account. And in a crisis situation, it's also important to be able to rely on local production capabilities. For example, we have seen over here in Europe the 3D printer farms, and also local disinfection capabilities for reuse. So for us, we think that the low-tech approach requires the availability of, as I said, different expertise. So engineers, makers, researchers, industrials, lawyers, and this means multidisciplinarity in terms of project management, functional constraints, and engineering. Or else then the constraints imposed by the medical context will not be met. That's where we saw unsuccessful projects with the respirators, for example. So in addition to the machines themselves, the supply tensions observed here and there, they have also led to a sustained reflection of the life cycle of consumables. So we are asking, so should we continue to purchase disposable accessories, or should we develop local production capacities, such as the 3D printing machines at the hospitals, for example, or invest in disinfection capacities that will extend the life of accessories while respecting hygiene standards? So we think that open source practices should be addressed for the environmental impact and for the resilience offered in the event of a major logical disruption due to crisis. And this would probably happen again, and we should learn from that. Okay.
Excellent. Thank you so much. Am I correct to think that
thank you.
that's going to be your talk? Robert is here as backup, right?
Yeah, and he will answer questions.
Perfect.
If we have afterwards. Yeah. And sorry,
okay.
I'm losing my voice a bit.
It's okay. It's the end of a long day. I think we all understand. Yeah. Okay. So I do have a question from Discord, which is that medical devices are regulated differently all over the world. Can you share ways that hardware makers can learn more about what to expect with regulation, or talk about regulation generally?
Well, regulation has been the biggest concern to address, because there are actually different types of regulations. There are the regulations that the medical sector just gives, but there are also a regulation, like in the case of the COVID-19 crisis, there were things that were allowed by the governments. For example, like makers could produce face shields, but at one point, like in France, they decided like to stop that because they considered it was too dangerous. Like if people using it would complain after towards the makers, and there were really different situations that we encountered encountered between countries, and also different, like for example, in countries like Spain or the UK or even in France, for respirators, where when the government was involved in the makers' mobilization, they were helping out, and they were helping with the test and with the validation of the medical equipment. So that was easier. But on a regular basis, a lot of makers, they explained to us that it would not be possible, because by the time they have to do the test, they find the money to actually do it. It's really complicated. So there's a need for a change of mentality also in the way that, open source and open hardware medical equipment should be developed with the help of the actual people who do make the regulations. And we have the testimonies of different makers who did send the devices they produced to underdeveloped countries. Like for example, they sent some to Brazil, they sent some to India, because at one point, like in at least in Europe, we didn't have this the problem of a lack of respirator anymore. So the makers, they saw that in other countries they still needed it, so they send them out, and there are not the same rules, and those devices, they were actually used and saved lives. So it's really something that is quite difficult to discuss, because there's a lot of ethical things with that. There's a lot of also, like if you provide a face shield to someone, well, that there's less chance that that person will be killed that if you put a respirator on that person, and if it doesn't work, then there's a lot of difference between the level of device that you are producing in the medical sector. They are, in Europe, I would say, they are not really ready yet for they do testing and they help with innovation, but there are still really strict rules in terms of homologation and testing, and it costs a lot of money, and that's still this COVID-19 crisis help make people aware of this, but it hasn't.
Bernier, you've frozen. Sorry. So we didn't catch the last little bit of that, but we got the message for the most part.
Yeah, okay, great.
Yeah, and thank you. That's an extremely thorough and useful answer. What I'm going to do now is I'm actually going to move on to the next speaker, but I'm going to save some of the questions that we got here, and we can try to pull them back in at the end. How's that sound? Good? Good. So next up, we have Samuel with Autoheim, automating blood smearing with open source hardware.
Hello, thank you very much for having me. I've really enjoyed today so far. So I'm going to talk a bit today about the project I've been working on for the last year. So yes, I'm Samuel McDermott. I'm a postdoctoral research associate at the University of Cambridge in the Department of Physics. And we've been developing ways to automate blood smearing using open source hardware. So the context for this project has been within the field of malaria diagnosis. So this is a pandemic that obviously has existed for a very long time. It's still a very deadly disease, increasingly deadly at the moment due to a whole variety of factors. but we've been looking at ways that we can improve one aspect of this, which is automating the diagnosis of the malaria. So the problem is I've been working on the OpenFlecture project for the last 3 years. In this project, we've been automating the diagnosis of malaria with this low-cost smart microscope. So this is a 3D printed open source microscope. And as part of this project, I identified that actually many of the manual blood smears from clinics that we were getting in Tanzania were particularly poor quality. And with all of these type of automation things, you have poor quality in, you're going to get poor quality out. And it turns out that it's not possible to automate malaria diagnosis with poor quality blood smears. In fact, this isn't even particularly unique to Tanzania. In some countries, up to 80% of blood smears are prepared incorrectly. But to understand a little bit more about this, it would be useful to talk about what is malaria, or how is malaria diagnosed. So a patient would typically present with a fever to a clinic. They would then have a microscopic examination of a patient's blood smear. So this is normally the best way of diagnosing malaria. There are rapid diagnostic tests, but microscopic examination is the gold standard. From the microscopic examination, you can identify a whole load of factors. So you can identify the species of malaria, the stage of malaria, and the density of the infection. And all of this information combined will help give the correct treatment. Now, in this stage here of microscopic examination, there are a few kind of smaller steps. So we'll examine them now. Firstly, you need to prepare the slide. So you just need to clean it, dry it. We want to collect a few drops of blood, and we will create a few different types of smears. So at the moment, we're interested in this thin smear here. And I'll show you what we are looking at in a thin smear later on. It's then fixed with methanol, stained, and then you can identify the parasites under the microscope. So for many of you may not have seen what a malaria parasite looks like. This is some stained blood. These are just red blood cells in the blue, and you can see these purple ones here. These are the malaria parasites themselves. So a technician will be able to see how many parasites there are in a person's blood and also identify what stage they are. So some of these are in different shapes and they correspond to the different stages of the parasite's life cycle. Now, when we want to create these blood smears to be able to look at them, there are commercial solutions available, and quite often in larger hospitals in richer countries, this is how this is done. However, they're too expensive for use in low and middle income countries, and also they tend not to be available either. It's very difficult to buy them, it's very difficult to service them, it's very difficult to kind of maintain them on an ongoing basis. So they're just not found where they're most needed. They also tend to be unsustainable. They require quite often custom use single plastics that you use once, chuck away. And so they're not a really useful solution. And so our project has been aiming, or the auto team has been aiming to make this high quality automated blood smearing available everywhere. So we use a whole load of important parts to make that happen. So we're using open collaboration technologies and 3D printing, and this will enable us to enable local manufacturing and to keep costs down. So what makes a good thin blood smear? So firstly, we want a nice monolayer of these red blood cells. So here you can see in this image, this is a really nice one where none of them are overlapping. We also want a Goldilocks density, so we don't want them too crammed in together, but we also don't want them so spread apart that you have to look through so many fields of view to be able to see them. And we want a nice even distribution, so we don't want them all squished together in one corner and all spread out in the other pair. And finally, we want to make sure that these red blood cells are not damaged or distorted. So this is the kind of traditional way that you would make a blood smear. So here we have our drop of blood. We have one microscope slide here and one microscope slide here. And we're able to change the angle and the speed in which we move this spot of blood. So here I am in the lab. So we place a drop of blood on our microscope slide. And then we create a thin smear. So we pull back and we push forward, and then we created a nice thin smear. Now this is okay when you're in a nice clean lab, you only need to make a handful of them a day. But if you're working in somewhere where you're very pressured to make lots of blood smears, you have a large number of backlogs, you've got to get them out quickly, you're working in particularly cramped, dirty, dark environments, then it's very difficult to keep maintaining a high consistency in the quality of your smears. And so our kind of solution to these is two devices. So firstly, we have this device here. This is the AutoHeme smear device. And firstly, it's important to notice that it's just a mechanical device. So there's no electricity required. And this is particularly important for use in rural clinics where there may be an interruptible power supply or no power supply at all. Next, we want to make sure that it's simple to assemble and maintain. So we're using kind of off-the-shelf components where we can, 3D printing, and we want to make sure that it's easy to clean and so on. Next, we want to make sure that we are being sustainable in our single-use components. So in this example, we're using a second microscope slide as our spreader rather than a single-use plastic. These can be reused, cleaned, and these are common in the facilities that we would be working in. Finally, there's one controlled variable in this setup, and that is that the spreader slide is held at a constant angle through here. So this is how it looks all together. So we can see, taking it apart, there's not a huge number of components in this one, and we can see that the spreader slide fits in here. Now this is this device in operation. So again, we follow a very similar procedure, so it's not a huge lot of learning curve. We place a drop of blood on our slide, we place our slide in the top, pull back, and just push forward. And that means for every single slide that a person is doing, it's going to be held at the same angle, which is really important. Our second device is AutoHeme Smear Plus. Now this is an electronic device. It has a kind of electrical and mechanical component. So, but it's kind of low powered, so you'd be able to power it off of a power bank or something like this. It's powered by Arduino underneath, and it has this NEMA 17 stepper motor. And this is the easiest way to make high throughput smears. As you just need to press the button and it's going to perform exactly the same repetitive smear motion every time. In this example, we can control the two variables, so we can make sure that our slide is held at a constant angle, and we can also make sure that it moves at a constant speed. And here it is to be put together. So it's a little bit more complicated, but at the core of it is an Arduino Uno, and we have our NEMA stepper motor, and of course all of the body is 3D printed as well. So to operate this one, we just place a drop of blood in exactly the same way. We put a glass slide in the top, push the button, and it performs the slide for you. So a technician is able to make many slides simultaneously, increasing their throughput, but also making sure that the slide is the same every single time. So we're going to end up with nice, consistent smears. So we performed some automated smear analysis on this using some machine learning image analysis techniques. So we can identify where the blood cells are on the smears and so on. And we can show for both the AutoHeme smear and the AutoHeme Smear Plus that we're able to get smears as good as an expert human, but importantly with consistency. If you want some more details about the kind of techniques that we use to test the devices, I will point you towards our paper that's published here. So now I'd like to talk a little bit about the design considerations. So firstly, it's 3D printed. This is because in low and middle income countries, 3D printing is becoming an important manufacturing device. You don't need a huge factory setup to be able to create things. We also want to make it easy to assemble, so it can be assembled with simple hand tools. We're using accessible and sustainable components. That ties into the kind of mechanical hardware, the electronics, and also using the glass slides as the smearer as well. And finally, we want to make it easy to use. So we don't want a complicated interface or things. We wanted to make it as easy as possible for people. So our software choices, all of our 3D designs are made in Openscad. The Arduino code, of course, is open source as well. We've used Git and GitLab to maintain version control. We've also used GitLab for a lot of automated CI and CD tools. So this means that the STL files are built automatically. So whenever we push new releases, they're built automatically. And that also ties into our documentation, which is also built in our CI. And for our image analysis, we've used open source image analysis tools. So documentation is very important. We have been designing our documentation for people who don't usually make hardware. So this will be people working in research labs, in universities, in research clinics. We use our GitLab CI and CD, so this is continuous integration, continuous development, to automatically build our documentation. So we use this technology that's been built by a colleague of mine called Git Building, and this ties in very nicely with GitLab's automated building tools. And this makes it really easy to download models from there and to automatically create a bill of materials.
All right, Samuel, I'm going to pause you real quick. We actually need to move on to the next speaker to stay on time. And
yeah,
if you're
I'm on my very last slide. So.
You're doing wonderful. Truly, I love it. I really don't want to stop you, but it does feel like we can share documentation in Discord. Yeah.
Yeah.
Okay,
great.
that works for you.
Thank you very much.
You so much. And I'm gonna move us along to Robert Reed, and then we will take questions. And if anybody has a burning question for Samuel that didn't get addressed, please drop it in Discord, and I'll make sure to ask it. And thank you, Samuel. Okay, Robert.
So thank you very much. This is really exciting. I'm going to speak very, very quickly so that we can get to the questions, because I think there are very interesting questions, and I certainly have questions for our other speakers who've done very exciting work. I'm the founder of Public Invention, which is a US 501c3 charity. We make a lot of projects or ideas to invent in the public for the public. So you can think of us as just taking free libre open source software ideas and applying them to open source hardware with a focus on inventions. And inventions are things that you would write an academic paper about or get a patent for. But of course, we don't seek patents because everything we're doing is open source. We've created some health things, but what I want to mention here is the Free Spirico Manifesto. Free Spirico is a project to create an ecosystem for certain kinds of medical devices around medical gases, meaning ventilators and oxygen concentrators, nebulizers, and things like that. The COVID-19 pandemic has demonstrated a clear and present need for complete, free libre, open source, easily repairable, widely usable, safe and effective respiratory support medical device ecosystem. We've created the Open Medical Technology Manifesto. I'd like people to consider signing it. I was informed by someone here that there's a different one that I was unaware of. I hope I haven't duplicated some work that they've done. Why can you imagine an ecosystem of these kinds of respiratory devices? Because they all have to control and monitor medical gases very precisely. So what ties all these together from a technological point of view is that all of them have to deal with air controlled in terms of flow, pressure, and oxygen content in a very precise way. So an oxygen concentrator, a ventilator, a BPAP machine, CPAP machine, PAPR, and a BVM monitor all have those things in common, tied together by some software and some standards that I don't have time to talk about. An example of this is that every ventilator can be placed on this diagram. And these modules exist in every ventilator. Right now, mechanical ventilators are not produced in an open source way, but they could be, and we're attempting to accomplish that. We have made an open source ventilator. It is not for medical use. I'm interested in talking about the regulatory issues that were raised in the questions here. We think of it as an educational open source platform now. It's called the Polyvent system. I want to mention Jake Reed, who has no relation to me that I'm aware of. He talked about a modular architecture in his talk. We're doing the same thing. He was using RS-485 to create a 3D printing CNC mill machine, which was extremely modular. Spirico is an attempt to do the same thing, but applied to the realm of mechanical ventilation and medical gases. So how realistic is this? We are making some progress. We can take the slides down now. That's the end of my talk. But I just wanted to show, this is the VentMon device, which we made. This is a standard 22 millimeter airway. It has a little bitty screen, but really it's a Wi-Fi enabled monitor of flow and pressure at human breathing pressures, which is tied to a data lake, which draws the kinds of graphs that doctors normally clinically see live when you plug it in between either a test lung and a mechanical ventilator for the purpose of testing it, or eventually a human patient. This is not an FDA approved device at the moment for that purpose. So this works, and was given, I got a couple grants I gave 30 of these away to the kinds of engineering teams that Mr. Visur and Ms. Fowley studied in their work. And not all of them were used, I have to say. It's kind of sad. Some of them just took it and put it on the shelf, but 6 of them used it really, really effectively. And it was a very, very important part of what they did. So I think addressing some of these questions and having conversations more valuable than me going on. So I'm going to hand it back to you, Claire. Thank you.
Awesome. Thank you so much. That was really wonderfully done. Your projects are fascinating. So what we're going to do now is we're going to open it up a little bit. And I'm going to start with a question that Robert Reed actually asked of Robert Visur and Ben Bernier. And it's how many of your projects are still in operation and how many are successful. There were emergency use authorizations by the US FDA. Do you know much about that? And you can chat among yourselves. You are all free to talk.
The emergency use authorization was a comment, not a question.
Actually, from the different respirators we looked at, in France, there's one that's called Macaire that has been developed in the area of Nantes in France by maker, engineer, businessman profile, and he partnered with different industries, with the military government, with a lot of makers profiles and different universities, researchers, and hospitals. And he actually worked a bit differently than the people who did just use the design by the MIT that was maybe interesting, but that was not really useful for patient, and that was a bit dangerous. So this project that was successful, what we noticed comparing to other projects is that it's that ecosystem that worked really well with collaborations and to actually develop something that was working, and they had the good contacts to make it approved by the government rapidly and tested on people. And to them, it actually took too long compared to the crisis situation, but at least it was successful. So.
Awesome. Okay, I have a next question that I think this even leads into, which is generally for each of you, what systems do you have in place for quality control? It's an issue that we've seen come up several times today. Who's going to be brave?
Are you going to pick someone to go first?
It's a free floor.
Okay.
Well, chaos.
If you do that, I'll talk too much, Claire. So you may have to.
I will try. I will try.
The VentMon is a quality control device. So in a sense, it's meant to measure the quality of other devices. We did extensive calibration testing with just a giant syringe, on this, and did what I would call redundancy testing. But I'd like to respond to some things that are in here. In the end, you can't trust engineers. Although we're very honest people, no one wants, to call their own baby ugly, right? So the problem is you can't trust engineers to evaluate their own equipment. And so what we really need is an open source mechanism of third-party testing, right? That's I think the real solution to this problem is that, I claim this is a good monitor of flow and pressure, and someone else should test it and say, yes, it is. It does what it says it does.
Samuel, what do you think?
I think it kind of comes down to two parts. So firstly, you have to have the quality control of your designs, but you also have to have it for your manufacturers. So if you are looking for a kind of distributed model that potentially would work for us, how do you make sure that people who are manufacturing it around the world are manufacturing it to the correct standards? And I think that's a question that's not been answered completely yet, but I think it's something that we should be thinking about.
So let me respond to that. So speaking only for the US, and I'm not a US chauvinist, I just happen to know about the FDA regulation. They do not validate a design. They validate a design in combination with a manufacturing plan, and you're not allowed to deviate from that manufacturing plan. And so if you are making a class 1 or class 2 regulated device that has to be manufactured that way, you just have to use a completely different model. Now, I personally am not attempting to subvert the regulatory regimes. Okay. Of course, what the US does not have to be followed in any other nation. So some low and middle income country can do whatever they want, but they're probably going to have their own regulatory regime, which must be followed. I believe that the open source community, even though the level of documentation and care that is required for medical regulation is onerous for the mindset of a hacker like me, needs to step up and start doing it. And we need an educational system where we can teach ourselves how to get this kind of regulatory stuff. So I don't think our approach should be, oh, we need to figure out a way around the regulation. We need to figure out a way to conform to the regulatory bodies.
Okay. Awesome thoughts. I'm going to do another question, and then I'm going to kick it off with Bernier and Robert Vizur. I'm not sure if you feel like speaking on the stream, but you're welcome to try. So the question is, do maker medical devices compete with or complement traditional proprietary devices? And I know this is a bit of a large question. That's on purpose.
I would not say that it's a competition, but it's just that what happens, what we analyzed with the different projects, we interviewed people that were prototyping and developing them, is that they acted in a crisis situation. But by doing so, they showed what the problem is right now, like in the medical sector, is that a lot of devices and a lot of equipment is something that is, well, not locally produced. It's something that is always, well, most of the time very expensive, or it's not repairable. It's not, and so well, working open source shows that things can be produced a lot more simpler, can be fixed on site, and does not need to be sent somewhere else, and is not that expensive. So it's just that it could help with the actual challenges we are going to face with the environment, with the medical expenses, with the waste and all that. So it's a way also that what we explained tonight is the importance of sharing design, of sharing knowledge, and that would also save a lot of money, a lot of difficulties to produce things locally. And I think it's just a different way of thinking, but the actual way the economic system is functioning, I don't think they're ready for that. But like we talk to people working in hospitals and stuff, and they would like to go for this, but like in hospitals, they are not ready. Like well, when it comes to spendings and contracts they have got and regulations and things like that. So.
Absolutely. I think you're speaking to the right crowd. A thing I'm fond of dissecting sometimes is an abundance model versus a scarcity model, right? And I think that comes into play here. So I'm going to ask one more question, and I'm going to start off with Samuel, if you're okay with that. And then we can open it up to whoever feels like talking. So the question is, can you imagine that open hardware could raise safety standards in health technology, even in the not so distant future? Is it helping move that along?
I think that's a difficult question. It's kind of a crystal ball type question, isn't it? I think what open hardware can do is it can enable more people to address these problems by making them more accessible. So for example, one thing that we're really trying to push with our blood smearing devices is that if you, and this applies across the board as well, if you create devices that people can make themselves, people can use, people can make relatively cheaply, then you're going to up the reproducibility that we see in science. So if people are able to perform experiments using the same equipment that someone else has done, and you can show how you made the equipment, how you put it all together, and you can copy that exactly, then the reproducibility in science is going to increase as well.
Absolutely. Yeah. Anybody else have thoughts?
Yeah, I agree. I don't want my mom ventilated with a closed source ventilator, but I have no choice right now, right? I mean, I would like the whole world to be able to see the software that is running there, but it's not possible. I believe long-term open source medical devices will be safer, but it's very important to understand the model will be open source design teams produce open source designs, and for-profit firms take those designs, go through regulation, and deliver them in a for-profit way. Okay, so it's kind of important to understand the model is not like people like me working in our basements, you know, making medical devices. What we may do is contribute to designs which eventually are vetted by for-profit firms. But though those designs may be taken up by very large medical firms eventually, they will resist it at first. And eventually we will have open source ecosystems of those designs.
And I would just add, like in the health sector, there's not only well, question about like the device and things that are actually used on patients, but there's also the waste treatment and things like that. And I think that's maybe less. It's asking less regulations, and they could start with that, with like the way they clean some disposals, and that could be reused instead of thrown away, and well, find out like how open source practices can help out, and then go further on things that they can validate, and well, after a while, that could be more open. There could be more open source practices done in hospitals and in other sectors of the health sector, actually. So.
Nice, lovely. That's very SMART goal oriented, right? Small, measurable, go from there. Okay, that is our time. There is a channel in Discord that you can talk to all of the audience members and they can talk to you. I think you all know where to find that. And honestly, this has been such an honor and so lovely. This is the first panel I've ever moderated, especially for the Open Hardware Summit. So thank you all so much. You were very lovely and I learned a lot.
Well, thank you.
Bye. All right. So up next, we're going to have Alicia Gibb with our final remarks. And I think that's it. I think we're nearly there, guys.
We're
Yeah.
nearly there. Thank you so much, Claire. You did an excellent job. So hi, everybody. This is our closing remarks for the Open Hardware Summit. I just want to thank everybody for being here, everybody who's been a part of this. It's been a long day, but a really fascinating day, a really important day for Open Hardware to hear everybody's thoughts and see our community be able to interact and get together in our Discord channel and on Twitter and all the other spaces that we're in. I also want to thank our sponsors today. So our sponsors, we wouldn't be able to do this without our sponsors, of course. So thank you so much to our sponsors, SparkFun, RepRep, the Chan Zuckerberg Institute, Helium, Edge Impulse DigiKey, Kickstarter, iFixit, Oshpark, Hackster, System76, DF Robot, LD Motors, ThingM, SupplyFrame, Tapster, Tindy, Hackaday, Ultra Machine, Crowd Supply, Timidim, Pulse Sensor, Great Scott Gadgets, Mach 30, Circlephone, Adafruit, Lulzbot, Shopbot, JLPCB, App and Glow, RPCB, InAccess, Olamex, Seed Studios, Blue Clover, PCBWay, DIA, Arduino, Jay Simmons, and Pinoco. Thank you all very, very much for supporting what we're doing here. Next up, for our update on Ashwa, it has been an incredibly busy year, an incredibly exciting year. We are really seeing open hardware being ported to all kinds of different places and being used in new, exciting ways. And what we're really seeing is an enormous foundation kind of being built under all of this community in a really fantastic way. So in 2020, we came to you at the summit in these same kind of opening and closing remarks with this idea that we had, that we wanted to do around an EDU initiative, a higher ed initiative, which would get university professors and researchers involved in open hardware, which would tackle the problem of having the people who have the funds aware of open hardware and understanding what the metrics might be to look like for deans and the higher ups at universities who are looking at, promoting within. And I am super, super excited to say that we recently just launched our Open Hardware Trailblazers in Academia Fellowship. This absolutely would not be possible without the Sloan Foundation. So thank you, thank you, thank you so much to the Sloan Foundation. We've gotten a really awesome grant from them, basically to help academics create a bunch of resources, sort of the meta layer of how to create open hardware in academia. So not actually doing the hardware itself, but thinking through all of the different layers of, okay, if I'm an academic, what do my fellow academics need to know about creating open hardware in this university structure and system? And one of the really exciting things that we hope is going to come out of this grant is a whole slew of fellows and future mentors and people that will be trailblazers, that will be able to say, hey, I was one of the people that wrote this library of resources over here and am able to share it with the rest of everybody. And hopefully, we're hoping that sort of lifts up all of open hardware and academia and makes it a real thing with a real certification from OSHWA behind it and resources that everybody else can use. We also created a State of Open Hardware 2021 report. And this report, part of this report was from our certifications. Part of this report was from the surveys that we have sent out over the last 10 years, surveying our community. You can view the whole report at the at stateofoshw.oshwa.org. This report is beautiful, so I wanted to pull out one of the images from this report, but we took different projects and certification, different data. We sort of cobbled all that together. We cobbled a bunch of data together about the Open Hardware Summit today. And then we also put in a section of the survey questions that we thought have been interesting. And we also included who we've been working with in terms of this foundation I'm talking about building, as sort of like a last list of our whole universe within open hardware right now. Other things that we have been doing this year, we've been integrated certifications into open hardware journals. We have created, we worked with the FPGA community and the OpenShift community to create a best practices for FPGAs. Our current best practices, or our general best practices, didn't quite meet the needs of that community because FPGAs are complex with where the software really ends and where the hardware really starts. So we kind of had to, you know, go to that community, ask a lot of questions. We ended up with the best practices. It's on our site. And we are continuing to do this with more and more communities and more industries, more fields that are out there who are applying open hardware and say, oh, wait, my community has this kind of weird thing. Because remember, hardware is anything with atoms rather than bits. So we are trying to cobble together like a lot of different types of hardware. We also added a professional development piece to the Ada Lovelace Fellowship for the first time, and this is super exciting. So our Ada Lovelace Fellows for the summit this year received a stipend to sort of make their open hardware careers come true. And they also received a series of mentorship videos from past fellows and from our past board members. So that was a really exciting thing that we also launched this year. Over last summer, we created a DI&J roadmap, which also included the move away from MASI and MISO and SPI nomenclature. And that is on our website under the resources tab. There's a resolution that you can sign for that. And then to sum everything up, we are also going to have a Community 2022 survey, which will be coming. So please look for that link. We'll try to get it out in all the places that we typically chat, Discord and Twitter, and possibly even your inbox if you're signed up for our newsletter. All of this is possible because we have the support of our members. So thank you very much to all of our members. You can sign up to become a member at oshwa.org/membership, and your membership does allow you to vote for your board seat. We also wanted to let people know about some of our sister organizations and what other people are doing sort of to create that foundation level of open hardware that is happening right now. So we've been working with GOSH and in close communication with them. One of the things that they are doing is the 2022 GOSH Gathering, which has already been talked about at the summit, which is awesome. You can apply. The deadline is April 30th. And they're also doing research and policy workshops, and the deadline to apply for those is May 8th. You can also find them on forum.openhardware.science if you've got questions and to join up with their community as well. Another space that we've been working with is the Open Hardware Diversity Alliance. This group is just getting started. We're hoping that there will be a series of events around open hardware. You can get involved by emailing info@diversityhw.org. If you all know about Nation of Makers, this is kind of that Venn diagram that connects open hardware with makers and maker spaces and hacker spaces. NomCom 2020 is coming up in June. You can see all the dates on their slide are the different topics that they'll be covering this year. So please check them out. There's also nomcom.org where you can learn more. And then finally, the Internet of Production Alliance. They are building out 2 meta standards, Open Know-How and Open Nowhere. And so this is another place where there's this whole Venn diagram happening within communities, and we just want to make sure everybody's aware of them. You can get involved by emailing info@internetofproduction.org. And then finally, for today, I want to thank our whole community, not just the other nonprofits I highlighted, but everybody who makes our community possible. Our speakers, our summit team, thank you so much for putting on such a wonderful event. I want to thank the board members at OSHWA. They do a lot of work in the background. I want to thank all of our volunteers, our ADA fellows, staff, and collaborators. And I want to remind you that you can join us for Twitter in about 2 hours. And there is the Twitter Team Finder channel on Discord that you can go to and find a team right now. And in 2023, we are going to have the Open Hardware Summit on April 28th, so mark your calendars. Of course, we're sort of, hopeful that maybe it'll be in NYC, but there is always the TBD, which is just a standard nowadays. And so we will let you know closer to the event if it will be in person or if it will be virtual. And thank you once again to our wonderful sponsors for making this day possible. Thank you so much all for being here. I appreciate everybody's presence. I appreciate everybody's comments and everybody's space in Discord and in Twitter and wherever you happen to be following us. So thank you all so very much.